e gravado pelo YouTube. Ao permanecer nesse local, o participante declara estar ciente e de acordo com a captação e utilização de sua imagem e voz na transmissão gerada e na transmissão e na gravação do evento, tá bom? Então, por favor, estejam cientes disso. This event is being broadcast live and recorded on YouTube. By remaining in this venue, participants acknowledge and agree to the capture and use of their image and voice in the broadcast and recording of this event. Okay? Shall we start then? Good morning, everyone. My name is Mauricio Bulgarian. I'm co-organizer of this workshop, and I have the pleasure of opening this session on behalf of Professor Marilda Sotomayor. I would like to welcome all participants to the fourth International Workshop on Game Theory and Economic Applications. This workshop is part of a major project led by Professor Marilda Sotomayor to create a center for research on game theory in Brazil. This is the fourth edition of workshops we have organized at USP. The first one was in 2002, then 2010, 2014, and this is the fourth one. All of them were very successful, thanks to the participation of many of you who are here today also. Modeled as a school of game theory, it aims to promote the field in Brazil and attract students from around the world to this area of research. Today alone, we are joined by two Nobel laureates in economics for their contributions to game theory, Robert AUMANN and Eric MASKIN, both presenting online this morning. Over the course of the week, we will also be joined by Robert Wilson online and in person here in São Paulo by Roger Myerson, Alvin Ross, and Paul Milgram. The scientific program is extensive. 6 advanced mini-courses, 11 plenary lectures, 14 semi-plenary lectures, 16 invited lectures, regular presentation sessions, poster sessions, and a round table. Today, we begin with Professor Pradeep DUBEY. Pradeep DUBEY's mini course, followed by the plenary lecture of Professor AUMANN and the plenary lecture of Professor MASKIN. This afternoon, we continue with Professor Michael Ostrowski mini course and a plenary lecture by Professor Marilda herself. The day closes with the opening ceremony at 6 p.m. I would like to thank our sponsors, Banco Itaú, the Brazilian Development Bank, BNDES, the Brazilian Federation of Banks, FEBRABAN, Sempre FEA, CAPES, CNPq, and FIPE. Their generous support, which made this workshop possible. I also thank the members of the program committee for putting together such a wonderful scientific program, and the local organizing team for their dedication over the past several months. I'm confident each of you will find much here to stimulate your research and spark new collaborations over these 8 days. I wish you all a wonderful workshop. Now it's my pleasure to introduce Professor Pradeep DUBEY, who will give the first mini course, Topics in Cooperative Games. As Professor DUBEY always says, there is no need to to introduce him, but I'm going to say a few words. Professor DUBEY is a fellow of the Econometric Society, a founding member of the Game Theory Society, and an economic theory fellow. He's a leading professor and co-director of the Stony Brook Center for Game Theory, a position he has held since 1986. Over the decades, under his co-leadership, the center has hosted more than 35 international conferences and 75 workshops, drawing over 2,700 scientists from around the world. In 2017, the 28th International Conference on Game Theory at Stony Brook was dedicated to him and his longtime collaborator, Yair Tauman. Please join me welcoming Professor Pradeep DUBEY.
Can you hear me clearly? Okay. First of all, it's a great pleasure to be here in honor of Professor Marilda Sotomayor's 80th birthday, but I don't think she's here. And, you know, she suggested that I do a mini course. Now, I took it to be something that I have to talk to people who know nothing about game theory. So I now see, I'm a little embarrassed to see professors sitting in the audience. So I apologize to you in advance. Okay, I'm going to talk today about a famous paper by Gale and Shapley. They wrote a paper in 1962 called College Admissions and the Problem of Marriage. It's a very funny title, as if college admissions have something to do with marriage. But you will see why there is, at some level, a similarity between the two problems. And the paper was written in 1962, and it became a bestseller as soon as it was written, because it has had a lot of applications. This morning I was in the bus looking up the latest statistics on the National Resident Matching Program, which is a program by which over 53,000 applicants are matched to about 7,000 medical tracks across USA and Canada. This is a very big labor market, which cannot be cleared by the standard notions of supply, demand, and prices. And one reason for that is that, you know, when it's apples, and a buyer does not care which apple he gets, they are all substitutes. But here, the 50,000 medical graduates are all different from each other. They have different preferences on the colleges, on the hospitals, and hospitals have different preferences on them. And something new is called for to clear this huge labor market, and it comes from game theory. And so let me now immediately get into the paper of Gale and Shapley. By the way, for more on this, I can't think of a better suggestion than the book by Al Roth and Marilda Sotomayor called Two-Sided Matching. And so let me just start. Now, how do I open slides? Just a second. So this, okay. And then how do I roll this up? No, I want to move. Okay. Okay, so I'll start with a very simple problem described by, I think the example is due to David Gale. This is matching boys as roommates. So there are many boys, and they have to be put into dormitories with 2 boys in each room. Okay, so the question arises, how should we assign the boys to the rooms? So we assume that the rooms are identical, but the people are not. Each boy ranks all the others strictly in order of preference. So in this example, there are 4 boys, yeah, and each one ranks the other 3 in his first choice for a roommate, second choice for a roommate, third choice for a roommate. And the question is, if you assign the 4 boys to 2 rooms, 2 boys to each room, what can go wrong? Well, I teach this course at Yale every spring semester, and I pause at this point, and there's an uncomfortable silence till somebody speaks, but I don't think we can do it that way here. So I'll just say that what can go wrong is that there can be 2 boys in different rooms who like each other more than their roommates. Then, having free will, they will disrupt the matching, and it won't be stable. So I'm giving an example, and I'm giving an example where there is no stable matching. There are 3 boys, alpha, beta, gamma, delta, and their ranking is expressed by that picture. Alpha likes beta most, beta likes gamma most, and gamma likes alpha most. Then I add that all 3 of them like delta least. So that completely describes their preferences, which I have written out here. Alpha likes beta most, delta least, so gamma must be in the middle, and so on. And the question is there an assignment that is stable? It's very easy in this example to see nothing can be stable. Now let me see if I can get this right. I'm not able to turn the page. Sorry. Oh, I see. Okay. So, you see why it can't be stable. Let me just go to this picture. Suppose there is any matching. Look at the roommate of delta. He likes delta least, so he must like one of these boys the most. And so he likes one of them the most. Let's say it's this person. Now, this person, oh, sorry, we do it another way. Look at this boy. One of these guys has him as the top choice. Suppose it's him. He likes this gentleman more than his partner. And of course, he likes delta least, so he also likes this guy the most, and the 2 of them will disrupt the matching. Is the argument clear? The roommate of delta is the top choice of one of the other 2 boys. Okay? That's this person. Okay, so he likes the alpha, look at the picture there, more than his roommate, and alpha certainly likes him more because he likes delta least. So no matter which matching you are talking about, it will be unstable. This is an example due to David Gale, and he then posed the problem of 2-sided matching. And this here, so this is, it can apply to medical graduates and hospitals, students and colleges, students and schools, and last but not least, men and women. I'm going to talk about men and women because once I start talking about students and hospitals, I'll at least fall asleep. We can remain more alert if we talk about men and women. So I'm thinking here now of N men and N women standing on opposite sides of a dance floor. Each woman ranks all the men strictly in order of preference. Different women may have different rankings. And similarly, the women rank the men. And we'll assume for simplicity that each person likes her or his last choice rather than to remain single. We'll drop this assumption later. So I will look, and we are also assuming equal number of men and women. And therefore, we can talk of a matching is the formation of N couples. And the question is, as before, what can go wrong with the matching, assuming that people have free will, that they can't be forced into having they can do what they want. Well, what can go wrong is that I may prefer Marilyn Monroe to my wife. By the way, I'm saying this purely for theoretical purposes. I may prefer Marilyn Monroe to my wife, but tough luck for me. She prefers her husband to me. Then there's not much I could do about it. But if I like Marilyn Monroe more than my wife, and at the same time she prefers me to her husband, then Marilyn Monroe and I can elope and disrupt the matching. Okay, so we ask now. I hope the definition of a stable matching is clear. I'll repeat it. A matching is not stable if there exists a man and a woman who prefer each other to their partners. Okay. So one can ask, is there always a stable matching? And Gale and Shapley showed that there is always at least one, and I'm going to give you the proof. So the proof, the idea behind the proof, not only will I show you there is a stable matching, but that there is a good algorithm for finding it. So it's not just existence. I could say that existence is sometimes easy to show. I can say there is at least one person in this room with the maximum number of hair. Such a person exists, but it's not easy to find. Here, we are going to find a stable matching by a handy algorithm, which I'll describe. So the idea of the method of finding a stable matching is that man proposes and woman disposes. There's an old saying, man proposes and God disposes. But here we are going to give woman the place of God. And it goes as follows. It's very natural. It's an imaginary algorithm. We'll imagine that on day one, let each man go and propose to the woman that he likes most. What should women do? Well, if a woman has got no proposals, there's nothing for her to do. But if a woman gets proposals, she picks out of those the one she likes most and temporarily accepts him. And as Gale and Shapley says, she puts him behind her on a string. It's like he's tied up, he can't move till he's released. So now, those men who have been rejected, they are free to move on day two. They go and propose to their next best choice. A woman now again looks at all the new proposals she's got, plus the man on the string, both could be empty sets, and picks the one she likes most. And if the new proposals, the new proposals is better than the man on the string, she releases the man on the string. She can keep only one at a time. Those men who've been rejected now go and propose to their next best choice, and so on. It's easy to check, and we will check that this process will terminate if there are n men and n women in at most n squared days. And you'll end up with a matching which is stable. So I have illustrated how it works for this example, but I hope it's clear. I don't have to go over it. Any questions? So let me just, before I describe the proof, let me make an observation. Consider this example, the 3 men, 3 women, and let's apply the men proposing procedure. So if you look at it, Mr. A will propose to Miss A, Mr. B to Miss B, and Mr. C to Miss C. These are their top choices, and that will be the matching in one move, and it will be stable. It has the property that each man has got his top choice and each woman her worst choice, but it is stable. If women do the proposing, then Miss A will propose to Mr. B, Miss B to Mr. C, and Miss C to Mr. A, and again it will end in one day, the women proposing procedure, and it will give a matching which is also stable but very different. And here each man gets his worst choice and each woman her best choice. So you see, men proposing is very good for men and very bad for women here. Even though woman disposes it, she's not in a privileged position here. And women proposing is good for women in this example. This is also a general feature in a sense that I will describe soon. Okay, so claim. This is the famous paper of Gale and Shapley. The claim is that the men proposing procedure converges to a stable matching in at most n squared minus 2n plus 2 steps, which is less than n squared for n bigger than 1. I am going to give the proof. So we observed three properties about the men proposing procedure. First, from a day that a woman gets a proposal, she's never without a partner. Why? Because if she rejects him, it's because somebody better came along, correct? So a woman is never without a partner from the day she gets a proposal. Second, if a woman ends up with someone, she must like him more than all the men she rejected before. Because every time she rejects a person, it's because a better man came along. Third, from the point of view of men, if a man ends up with any woman, that's at the end of the procedure, he must have proposed to all the women that he liked more, and he must have been rejected by them because he's proposing in order of his preference. So I hope these three facts are these three are properties of the procedure of the algorithm. Now, I say that suppose a date T has arrived, and we can say at that point that by now every woman has got a proposal. I claim that there can be no next day, because from the day a woman gets a proposal, she's never without a partner. Therefore, if every woman has got a proposal, she can never be without a partner. There are n men and n women, so all the men are exhausted, and no man would be rejected. So we conclude from this that there has to be a woman who only gets a proposal on the last day. Okay? No matter what the preferences are. Because the moment every woman gets a proposal, there is no next day. So it follows there has to be a woman who gets a proposal only on the last day, and there is at least one such woman. There could be many. Now, we are almost done. On each day before the last day, there is a rejection. What is a rejection? It's a pair of names. Let's say Carol and Bob, I'll call a rejection if Bob is rejected by Carol, okay? And no rejection repeats itself. Therefore, the number of days before the last day can be no more than the number of rejections. How many rejections can there be? A man can be rejected by at most n minus 1 women, right? And therefore, the number of rejection is at most n times n minus 1. And so that's the maximum number of days before the last day. And so we conclude that the number of days before the last day is here plus 1, and that's the proof that the algorithm always converges in no more than n squared days, n squared minus 2n plus 2 to be precise. The matching that you end up with is stable, and that's completely obvious. It took a little work to show that it converges in n squared steps. That it is stable is completely obvious, because consider a matching obtained at the end, and suppose John likes Mary more than his wife. Well, then he must have proposed to her, and he must have been rejected by her before he proposed to his wife. And if he was rejected, Mary likes her husband than all the men she rejected. Therefore, if John likes Mary more than his wife, we have proved that Mary prefers her husband to John, and therefore it is stable. This is the proof, beautiful proof of Gale and Shapley. Okay, I now have to get out of here and open the next slide. Oh, cancel? What do I do? I want to close this and open another. By the way, please feel free to ask questions. If you don't say anything, I'm going to assume that it is clear. Okay. So now I just want to show you some variations on the theme, which all I made assumptions for simplicity. First variation is that the number of men and women need not be equal, and the preference of a person need not be complete. So in this example, for instance, look at Miss A. She likes Mr. A most, Mr. B second, Mr. C third, and she does not rank the remaining two men D and E because she prefers to be single rather than be married to either of them. So now we are going to generalize the problem by looking at rankings which are partial, meaning to say that you prefer to be single after that point, and the number of men and women need not be equal. Once again, we can define stable in the obvious way, and the same algorithm proves that there is a stable matching. Okay, but in this, people will be left single. And in this example, I've carried out the women proposing procedure, where they are doing just the same thing as before, except that if somebody comes whom they don't like as much as being single, they reject the person. So a woman may reject people and remain single when you carry out this procedure. Okay. Sorry. Second generalization is many to one matchings, and this is an example with two colleges and many students, and the students are A, B, C, D all the way to N, but Mr. J is missing, and that's because when I was working it out, I forgot about J over here. So it was easier to remove him in the data of the problem. So here are many students that are two colleges. Each college has a quota, which represents how many students they can admit. So X can admit 6 students, Y can admit 4, and the students are more than 10, so some students won't be admitted. I have written out their preferences of the students, of the colleges, of the students. And you follow the same procedure, you end up with a matching. With Marilda, good to see you. Happy birthday, I said before you came. I'm saying it now. Okay. So, escape. Now again, I don't know what I'm doing wrong. Do I have to click this?
No. Just this one, the actual one.
The middle one, okay. This, by the way, is the title of the famous paper of Gale and Shapley. Oh, I have to show now another slide. I want to get rid of this. Okay, okay, thank you. Oh, so maybe this is okay. Just a sec. Why is this come back? Okay. I go back to that example that I had started with. We already checked that, so this was, I'm going to flip these two, they're not needed. We did this before. We already saw a matching where there were two stable matchings. In general, there can be many stable matchings. In this particular example, which is from the book of ROTH and Marilda Sotomayor, this is their example. There are out of 4 factorial matchings, which is 24 matchings, because for any rank ordering of the men, you fix the women and put the men in any order, there is a matching. So the total number of matchings with 4 men and 4 women is 24, of which these 10 are stable. Okay. So we are going to define the notion of the possible set for a woman or a man. So we fix a profile of preferences. We know that there is at least one stable matching, but there could be many. So let us define for a man the set of all women to whom he could be married in some stable matching. So, for example, if there were 5 stable matchings, we look at John, and if we look at all the wives he could have as you run across the different matchings. So here the first matching he's married to Mary, the second matching he's married to Carol, the third matching he's married to Mary again, but it's a different matching because some other couples may be different. So the set of women who are possible for John are these 4. And the theorem that, the second theorem of Gale and Shapley says that when the men proposing procedure is followed, every man ends up with his best choice in his possible set. So not his best choice among all women, but only women who are possible for him. At the same time, every woman ends up with her worst choice in her possible set. So this is the sense in which men proposing is good for men and bad for women. And the proof of this is also very simple, so I'm going to give it. So we are going to fix a profile, and we are going to focus on the men proposing procedure for that profile. And I observe that if John ends up with Mary for a wife, he must have proposed to and been rejected by all the women he prefers to marry. Okay, so in order to prove the theorem, I have to show that none of the men who reject John in the course of the men proposing procedure are possible for John. Okay, that's what we have to show. And we have to show this not just for John, but for all men, Bob, Harry, etc. All right. In short, I have to show that no man is rejected in the course of the men proposing procedure by a woman who's possible for him. So I'm going to, just for making it dramatic, say we are going to prove this by contradiction. We have to, so let's define a bad event to be something which we are claiming won't happen, that a man is rejected by a woman possible for him when you run the men proposing procedure. So if bad events happen, then there must be an earliest date on which a bad event happens. We shall call that date T. So we are now looking at the case where no bad event happens on dates 1 till T minus 1, and on date T, a bad event does happen. So let's put a magnifying glass on the bad event. The bad event is that a man is rejected by a woman who's possible for him. So let's say John is rejected by Mary, and we have to also assume that now Mary is possible for John. What does that mean? There is some stable matching where John is married to Mary. So, so Mary rejects John even though she is possible for John. And so now if Mary is rejecting John, it must be because somebody better came along. We are in the men proposing procedure. We shall call that person Bob. So now I want to look into the minds of Mary and Bob. It's clear that Mary likes Bob more than John because she rejected John in favor of Bob. What about Bob? He's married to Carol. He's married, somewhere in his ranking is Mary. He's married to Carol, and I'm asking, can Carol come before or after Mary in his ranking? Okay, and I'm going to, if, so let's just do this. So Bob rejected all the women that he likes more than Mary on dates 1 till t-1 because he was with Mary on date t. And so none of these women whom he likes more than Mary are possible for Bob. But Carol is possible for Bob. As you see here, there is a stable matching in which he's married to Carol. Therefore, Carol must come after Mary in his ranking. And so now we go back. If Carol is, so Bob likes Mary more than Carol, and Mary likes Bob more than John, and therefore the matching is not stable, which we claimed over here. And so by this contradiction, we have proved the second theorem of Gale-Shapley. Okay. Now, I want to think of, go back to looking at the matching. In the whole procedure, the men proposing procedure, depends on people revealing their preferences to the mechanism. So let's think of the men proposing procedure as a mechanism. The inputs are preferences of men and women. That's the inputs. And the output is a matching. Now, the procedure, the mechanism cannot look inside the mind of any man or woman and know what their preferences are. All it can do is to ask them, please write down your preference and send it to me. Once they report their preferences, that will be the input for the mechanism, and the output will be the matching. Yes, then the algorithm, the mechanism is going to do in its head the men proposing procedure once it gets all the preferences, reported preferences of the men and the women. And so the question arises, we have proved a nice theorem saying that this mechanism is good because it produces something stable, but that is under the tall assumption that people have stated their true preferences. If the mechanism, once it's instituted, creates the incentive for people to misrepresent their preferences, then everything we've done so far becomes nonsense, because it'll compute something good according to the reported preferences, but the reported preferences are not true, so it won't be good anymore. So in order to give some justification to the proposal, we would like to say that there is incentive for all the actors in the drama to report their true preferences. But this, unfortunately, is not true. If the men proposing procedure is followed, we can show easily by examples, that women may profit. There is, the passive side is women, the active side is men in the men proposing procedure. So for the passive side, it is possible to misrepresent their preferences and benefit. But, so that's sort of bad news. But there is some good news. And the good news is that for men, this is not the case. Indeed, for every man, telling the truth is as good. So we fix the preferences. So no matter what others' preferences are, a man can, in this mechanism, never get a better partner by misrepresenting his preference. So if you think of it as a non-cooperative game, where each man has n factorial strategies, because he can rank women in that many ways. So men and women submit their strategies, and each one has n factorial pure strategies, one of which is his true ranking. So in this game, people submit strategies, and the outcome is each person gets a partner. So this is a non-cooperative game, and it was shown by Dubins and Friedman, and I'm posting a handwritten proof of this result because there's no time. It's a little more complicated. Up till now, things were extremely intuitive and simple, but this result, the next result, which was proved more than 10 years after the Gale-Shapley paper, is by Dubins and Friedman, and it says that in this game I defined, it is a dominant strategy for each man to reveal his true preference. Okay. So this is sort of half good news, and why is it interesting? So I have my own take on it. When you talk of the, let's say, students and colleges, you can apply it to medical interns applying to hospitals, but I'll talk of students and colleges. If you take that case, the human beings in the model are the students, okay? The colleges are institutions, okay? And the human beings have privately in their minds a ranking of the colleges. Do colleges have a ranking in the same way? No, the colleges do their ranking slightly differently. A group of professors sits on a table, round table, and they examine the applicants. And so they don't have a ranking to begin with. They are in the business of manufacturing a ranking by a fierce debate among all the professors looking at the applicants. So they are not susceptible to misrepresenting the preference. They, through an open public debate, arrive at a preference. So the ones who are vulnerable to or susceptible for misrepresenting are the students. So that's one reason why we should have a method that is incentive compatible for the students. Those who can misrepresent should not want to. Second, it's also the purpose of the mechanism should be to maximize the happiness of the human beings, which are the students. So student proposing leads to, I described the second theorem, something optimal for students. So for these two good reasons, we should follow the student proposing procedure rather than the college proposing procedure, or the medical graduates proposing procedure instead of the hospitals proposing procedure. And I think for all the remaining questions, I direct you to talk to Professor Sotomayor on this, because she and Al Roth have, their book remains fundamental to this day, very up to date even now, and they have gone into questions of the practical applications of this model. Life is much more complicated than what we have described in this idealized world. For example, a college or a hospital may have a quota. It may have certain constraints on the students it admits. It may need to maintain a gender balance. Or couples who are applying want to be together, so they don't have a ranking independent of each other. Okay, these things are all missed in the model. And how they can be accommodated using still the overall idea of the procedure is a delicate art, both in a science, engineering, as Marilda would say, and for that you have to consult Professor Sotomayor and Professor Roth. I am only telling you about the basic work that happened before they came into the picture. Okay, so with that, I think I could talk about the lattice of stable matchings, but how much time do I have? Huh? I have only used 42 minutes. I see. I thought, huh? I have 5 minutes more? 45 minutes more? 41 minutes more? Well, then we can have a discussion. I have said almost everything I want to say, but let me point out one more thing then. I want to read out something first, which is a beautiful, this is the last two paragraphs of the paper by Gale and Shapley. So I want to read out what they wrote. So the second last paragraph I'm reading. Most mathematicians at one time or another have probably found themselves in the position of trying to refute the notion that they are people with a head for figures or that they know a lot of formulas. At such times, it may be convenient to have an illustration at hand to show that mathematics need not be concerned with figures, either numerical or geometrical. For this purpose, we recommend the statement and proof of our Theorem 1. Theorem 1 was that the Venn proposing procedure leads in at most n squared steps to a stable matching. Then they say the argument is carried out not in mathematical symbols, but in ordinary English. There are no obscure or technical terms. Knowledge of calculus is not presupposed. In fact, one hardly needs to know how to count. Yet any mathematician will immediately recognize the argument as mathematical, while people without mathematical training will probably find difficulty in following the argument, though not because of unfamiliarity with the subject matter. And they say, what then, to raise the old question once more, is mathematics? And then you can read what they've written. I'll read it. The answer, it appears, is that any argument which is carried out with sufficient precision is mathematical. And the reason that your friends and ours cannot understand mathematics is not because they have no head for figures, but because they are unable to achieve the degree of concentration required to follow a moderately involved sequence of references. Maybe they're being a bit too critical here. Anyway, this observation will hardly be news to those engaged in the teaching of mathematics, but it may not be so readily accepted by people outside of the profession. For them, the foregoing, that means their two theorems, may serve as a useful illustration. Okay. Now, there is one more result that I would like to present. I can go into the next matching problem, which is kidney exchange or housing market. But before I go to that, I want to mention a result on lattices. Let me see, of matchings. Okay. It's not here, so it must be in the other slide. Maybe I'll say it before I move on. Since I have time, I'm going to move to one-sided matching. But here is something that is true. If you fix a profile and look at all the stable matchings that it gives rise to, we can put a partial order on these matchings from the point of view of men and a different partial order from the point of view of women. We can say that a red matching is better for men than blue if for every man, his red wife is better than his blue wife, or at least as good. Okay? So if you look at the men, the wife of any man in the red and his wife in the blue, he should like the red more than the blue. If this is true for all, or at least as much. So if this is true for all men, and at least one man is better off, then we will say that the red is ranked higher from the point of view of men than the blue. Okay, so this gives a partial order. It can be that there are stable matchings which are incomparable, because John likes the red more than the blue and Bob likes blue more than the red. So you can't compare two arbitrary stable matchings, but so it defines a partial order. Okay. When you look at it from the point of view of women, it defines a different partial order. Already I gave an example of two matchings. One was good for men, the other good for women, and they were different. Okay. Well, one can show that this is a lattice, and here is how, given any two matchings, you get one that is better than both. Okay, I'm describing the lattice operation. So look at a red matching and a blue matching, both stable, for a fixed profile. Let each man look at his two wives and point to the one he likes more. it is easy to prove that no two men will point to the same woman. Therefore, the pointing will give a matching. Also, this matching that you get will be stable. And each woman would be getting the worst of her two matchings. So you see, the lattice is now completely well defined. I've even defined what is called the join operation and the meet operation for this by the pointing method. The men proposing procedure is at the top. It's the best of all the matchings for any man will prefer the outcome of the men proposing to any other stable matching. So it has a unique maximum and a unique minimum. The ranking of men and women run in opposite directions. Okay, so all that is we can show this. So a very well-known mathematician called Conway proved the following theorem, which is maybe of interest from a mathematical point of view. If you take any finite lattice which is distributive, then it can be represented by a profile on a matching problem and its stable sets. So it completely represents finite lattices which have the distributive property. Okay, this is a result of Conway. I think it's also in your book, isn't it, Marilda? Conway's famous result is probably also in their book. I'm sorry, I haven't read every word of the book, but I refer you to the book to now, having gone this far, since I have half an hour left, let me, so this is the lattice structure for the example here. The matchings are labeled 1 till 10. 1 is what you get by the men proposing procedure. The 10th matching is what you get by the women proposing procedure. And this is the lattice. 10, which you get by the women. So the partial order is according to the blue arrow. Things improve as you go up. So if you look at 5 and 6, they are incomparable to each other, the 5th and the 6th stable matching on the previous page. Here, these matchings are named by numbers. So this lattice is as follows. 5 and 6 are incomparable for both men and women. 4 is better than 5 and 6 from the point of view of men, but worse from the point of view of women. And you get 4 from 5 and 6 by the pointing method that I told you. Okay, so I've described this lattice. All right. And it's a perfectly general theorem. And now, we come to a second matching problem, which was formulated by Shapley and Scarf. They even published a paper on it, which is in the Journal of Mathematical Economics. And they raised this rather beautiful question. We have finite number of men, and each one owns a house or the kidney of his donor. Okay, so I'll talk in the language of houses. Each man owns a house. So Mr. A owns a house, and it's very good notation to say the house is not X or Y, but little a, so that you can identify the ownership at the house. So capital A is the owner, little a is the house that he owns. Capital B is another man, and the house that he owns is little b. Okay, so let us think of that notation. Now, so here there is something which is new, ownership. In the men-women problem, nobody owned another person. You owned yourself, that's it. But here they own objects called houses, and therefore, and they rank the houses. So Mr. B ranks the house of Mr. C the most, of Mr. A second, his own third, and D last. Okay? So people have rankings over houses. Houses, of course, are inanimate things. They don't rank the men. It is a very different problem from the previous one. There is ownership, and things that are owned are ranked by the men, by the owners. And now the question is, how should we think of a trade? So a trade here is to just permute the houses among the owners. Every permutation is a trade. They are swapping houses. So in this example, there will be 4 factorial, 24 possible trades. And we want to ask when is a trade or stable? So let me focus on this example first. Here is a proposed allocation, and we observe that if a coalition of B and C forms, the allocation is proposed, it's not carried out. That's why I have underlined proposed. Everybody is still sitting with his own house, and they're looking at the proposal and wondering if it's okay. Well, B and C could get together and walk off with the houses that they own. And if they trade among themselves, B compared to the proposal, B will be better off and C will be the same. And therefore, we say that the coalition B and C blocks the allocation A. So I now repeat this definition generally. Given an allocation, we say that a coalition will block it if the coalition can walk out. In this case, the coalition was just 2 people. If the coalition can walk out not carrying only the houses that they own, because that's all they have a right to. So they walk off with the houses that they own, and if they can trade among themselves so that none of them is worse off and at least somebody is better off, then the coalition will form, they will block the allocation. And so we want to define a stable allocation to be one which cannot be blocked by any coalition. Okay. Let me at this point make a footnote on the Gale-Shapley problem. There we considered only coalitions of size 2, a man and a woman, for blocking. You could have considered coalitions of larger sizes, but I leave it as a trivial exercise for you to check that if you allow coalitions of larger sizes, you'll get the same thing as you got with just coalitions of size 2 in the matching problem, in the Gale-Shapley model. Here, we have to consider coalitions of all possible sizes. Okay, so the theorem, there's a beautiful theorem here, 2 theorems. One is that there exists one and only one stable allocation, unique. And the proof is Shapley and Scarf wrote a quite complicated proof of this using some machinery that Scarf had developed for studying cores of games without transferable utility, so-called Scarf condition. Okay, they applied that heavy machinery to prove that there is at least one stable allocation, to prove half this theorem. And now I think both Scarf and Gale are no more with us, but I think they will forgive me if I tell you a story. This was told to me by Scarf. Scarf was giving this talk at Berkeley. At the end of the talk, David Gale comes up to him and gives a one-line proof of a stronger theorem, which is not only is there a stable allocation, it's unique. So the proof that I'm going to describe of this is due to David Gale. So I always wondered how come, and it was reported by Shapley and Scarf. So they wrote a long proof, and then they also wrote a paragraph saying, here is another proof of a stronger theorem. So how come the paper was, the editor could have said, then just give Gale's proof. It's proving a stronger theorem in 2 lines. Why are you giving this long proof? But I think, I think they were Shapley and Scarf. So the paper, the editor just accepted whatever was written. It's published, and you can read it for yourself. Maybe the justification was that Herbert Scarf was looking for applications of his general theorem, and here was an illustration of how it works here. It could also be done more easily here, but the interest was to show that his method applies to concrete problems, and maybe that's the justification. Okay, so that's a story. And I'm going to give the, so how much time do I have left now? Huh? 15 minutes. Okay, that's, oh, 2-5, very good. Okay, so first, so let me give a proof of this theorem. It's due to David Gale. So there are two questions to be asked here. First, believing in this theorem, if you believe this theorem, then we have a mechanism where people, if people report their preferences, then this theorem produces an output which is a trait. Okay, so we can think of the same incentive compatibility problem that we had in Dubin's-Friedman. Think of it as a mechanism. Nobody can look inside the head of a person and know what his ranking is. All the mechanism can do is say, please write down your ranking and send it to me. Yeah. So, and then the mechanism says, I'm going to follow this theorem and produce the unique stable allocation which comes out of your preferences. Well, if this is what the mechanism is going to do, then we better ask whether people will reveal their true preferences, because the mechanism is going to produce something stable according to the reported preferences. If the reported preferences are not true, it will produce something which is not truly stable, and the mechanism will dig its own grave, because you institute the mechanism based on the hypothesis that it is producing something nice, but once you institute it, it invites people to misreport, and therefore the output is nonsense. Okay, so in order for this theorem or the mechanism to be meaningful, we also have to show that it's a dominant strategy for each man to report his true preference. Once we agree that from their preferences, we'll use this theorem to produce a stable allocation. Okay, so let me first prove this theorem. I'll do the incentive compatibility probably next time when we continue, but I'm going to give you a proof of this very simple theorem. By the way, okay, so this proof is due to David Gale. And the proof goes as follows. Let me express this in terms of graphs. I'm going to produce a red graph, then a blue graph, then a green graph, and a yellow graph, and so on. So we start with a node, one for each person. So in this example, there are 6 people, and each one, there is a node, right? Okay. And we say, let each man point to the guy whose house he likes the most. If he likes his own house the most, he can point to himself. So each guy points to the house that he likes the most. And for this profile, you know, I've drawn the green graph, the first graph. Everybody points to the house he likes most. There are no ties, huh? It's a strict ranking. Now, since this is a finite graph, there have to be at least one cycle, because from each place you get out and you follow the row. You're bound to, if it was an infinite number of nodes, there may not be a cycle, but with finite nodes, there's bound to be at least one cycle, maybe many. So in this example, there are 2 cycles, B pointing to himself and E, D, and C form a cycle. So let's remove the cycles and let people trade according to the cycles. So what happens? So Mr. B keeps his house and walks out. Mr. D takes the house of C, C takes the house of E, and E takes the house of D. So the 3 trade among themselves and walk out. So we now look at the graph that remains. We look at the nodes that remain. They form a sub-problem. So here A and F remain, and we ask them to point to the person you like most among those that remain. So Mr. A would like C, E, F, but they have C and E have gone, right? If you look at the preferences of Mr. A, he likes the house of Mr. C the most, of Mr. E the second, but they have disappeared because that green cycle triangle has gone. So of the houses that remain, he can still point to the best among the houses that remain. You get a second graph. Again, it has to have cycles. Yeah. So remove the cycles. And this defines a total trade. This is due to David Gale, this method of pointing. Yes? This is what is called top trading cycles. Green is the top, blue is the second top, and the third top is A pointing to himself. So this completely defines an algorithm for computing an allocation coming from the top trading cycles, or the pointing, the graph that I constructed. Okay. Sorry, I'm going backwards. So I'm now going to, so we have to prove two theorems, that what you get by this method is stable and also it is incentive compatible. Okay, now let me see if I can do it without your help. Oh, I want to switch slides. Where is the other slides? These are, I sent more slides.
Did you?
Yeah, well, maybe you haven't put them on.
Perhaps not. Do you have a pen drive?
No. Well, I'll repeat this proof next time to warm up, but it's not here. How many of you, if I may ask, how many of you were familiar with the Gale-Shapley paper? Oh, I'm sorry for that. You had to listen to it again, but it's so beautiful. There's no harm, huh? Yes. Yeah, that's due to David Gale. It's in their paper. Yeah.
Lecture 2?
Lecture 2. Yeah.
Oh, lecture. Okay.
Yes. Thank you. That's it. Okay. So I'm observing something. If you take an arbitrary permutation, a permutation, by the way, is called cyclic. So look at an arbitrary permutation. I'm saying any permutation is made up of disjoint cyclic permutations. That's obvious. I'm giving examples. For any permutation, if you look at the permutation, the first initial order is A, B, C, D, E, F, and you permute. Now you let people point according to the place they have gone to. So A goes to the place, to the third place, which was C's place. So I let A point to C. And D goes to the second place, which was B. So D points to B, and so on. So here you get pointing. This has nothing to do with ownership of houses or preferences. You just can imagine a permutation by pointing, and it'll break up into disjoint cycles. So you see the permutation I wrote down is made up of 3 cyclic permutations. That's a well-known fact. So any permutation can be broken into cycles, disjoint cycles. Okay. What we are doing in Gale-Shapley is constructing disjoint cycles and a permutation, which corresponds to a permutation, but the cycles are connected to something called preferences. Okay, the cycles are coming from preferences. So, yes, do you see what I'm saying? Any permutation, forget everything else, is made up of disjoint cycles. When we have the Gale-Shapley model, we are going to construct a permutation, but it'll be dictated by something called preferences. That's what we did over there. Okay. Now, this was for an undergraduate course. I have already defined blocking, but I want to emphasize two different notions of blocking which are worth thinking. I'm going to talk of, so we have a problem, men who own houses, and each man ranks all the houses, including his own, strictly, right? That's a problem. I'm going to imagine two different notions. One I'll say is on Earth, where people are selfish, and the other, Mars, where people are not so selfish. On Earth, a coalition forms only if everybody in the coalition can be made strictly better off. On Mars, they are a little more less selfish. A coalition forms and does something, provided nobody is hurt and at least somebody is better off. Okay? Now, so there is no Mahatma Gandhi or Jesus Christ in the model. Nobody will get hurt to help somebody. Okay? But on Mars, they are nice in the sense that they don't mind staying where they are, provided it helps somebody. So I have two notions of blocking, and I want to define two notions of stability. Okay? So something is stable if it can't be blocked on Earth, where the possibilities of blocking are fewer than on Mars. And something is called strictly stable or strongly stable if it can't be blocked on Mars, where there is more blocking possible because you are allowing people to be slightly nice. Not very nice, slightly nice to each other. They are ready, even if they don't improve, to join a coalition, provided others are helped and they are not hurt. That's the notion on Mars. So we have two notions of stability. Okay. And here is an example which you can check yourself. I'll post these things of an allocation which is not stable on Mars, where many possibilities of blocking exist, but it is stable on Earth. So the two notions don't coincide. You can have a lot of stable things, many of which are not strongly stable. And here is an example. Now, I have described the TTC procedure earlier. I want to prove a theorem that the theorem that I stated, that that there is one and only one strongly stable allocation, and it's given by the top trading cycle. That's the theorem we are endeavoring to prove. And the proof is here. I think the proof is very simple once you remember the cycles. So there are cycles of level 1, level 2 to level K. Observe, this is what TTC gives you. Given preferences, it dictates a unique permutation because it dictates all the graphs. So when people point to their top choices, that's the first graph, and you look at all its cycles, and they are listed as cycles of level 1. Then removing them, you have got a new graph, fewer people who rank the houses that remain according to their preferences. That graph is dictated, so are its cycles. So you see the preferences dictate all these cycles and the permutation. Okay? I observe that each person in a cycle of level K is getting his top choice among all the houses of his level and below, because all those were available and he pointed to the best. So that's how we constructed the top trading cycle. Is this clear? Well, I want to show two things. If A is strongly stable, it must be the TTC allocation, and also the converse. If something that the TTC allocation is strongly stable, I have to prove both. So I'm going to prove one side first. I want to show that inductively, I want to show that if you take an arbitrary, strongly stable allocation, okay? I want to show that all the cycles of level 1 must be there. And then I'll show, as a second step, suppose all the cycles of level 1 to K are there, then all the cycles of level K plus 1 must also be there, in that abstract, arbitrarily given, strongly stable allocation. Okay. We're going to prove this, and the proof is simplicity itself. Okay, so why, suppose some cycle of level 1 is not in. So A is a strongly stable allocation, that's all we know. We don't know how it's constructed, okay? I want to show that all the cycles of level 1 must be there. Suppose some cycle is not there, okay? You can look at that cycle and look at the people in that cycle, they form a coalition, and let them trade according to that cycle among themselves. Each one is getting his top choice among all the houses, yeah? And so if it's not there, at least one of them is getting better off. And nobody is getting worse off. Therefore, that the cycle that's not there produces a blocking coalition on Mars, not on Earth. Yeah. Okay. Now we are almost done with the proof. Now suppose, so this is the next step, suppose all the cycles of level 1 to k minus 1 are in alpha, that is the abstractly given strongly stable allocation. I want to show that cycles of level k are also in A. So we are assuming what I have written, and we have to show. It's exactly the same argument. Suppose some blue cycle, which is level k, is not in A. I want to consider the coalition defined by that cycle, and they can trade among themselves. Since all the cycles of level 1 to k minus 1 are in A already, these guys are not getting cycles of levels 1 to k minus 1. The guys in the cycle here. And therefore, and they are getting their top choice of their own level and below, so they form a blocking coalition. And this proves that half of the theorem. The proof is extremely simple. Just visualize the cycles. Okay. So I have proved that if A is strongly stable, it has to be the TTC. The converse is equally simple, and I leave it to you as an exercise. Now, I want to prove, one second, I'm going back instead of going forward. I want to now prove incentive compatibility. And the proof is written. This proof is even simpler. Okay, so let's show that no man can benefit by misrepresenting his preference. Suppose Mr. Alpha states, if he states his true preference, he will end up, let's say, in level K. Now, all the cycles above his level are formed by the preferences of other players. They will continue to be formed no matter what Alpha submits, because they depend on the preferences of the other players. And therefore, all he can do is to go down from level K to something below, but he's already getting the best of level K and below. And so it's a dominant strategy, weakly dominant strategy, for him to reveal his true preference. That one picture proves everything. Okay? And with that, I have covered what I had to say on the Scarf-Shapley result. And do I have any time left? I'm done. Okay, so we've done two-sided matching and one-sided matching. The only thing I haven't proved is the Dubins-Friedman result. I gave proofs of everything else. At least I am under the illusion that I gave the proof and that it's clear to you. That proof of Dubins-Friedman is a little more intricate. Also, it requires no calculus. You don't need to know how to count. But it's a more intricate sequence of logical deductions. And I have written it painfully, lovingly by hand. I'm going to post it and their proof Okay, they wrote it in the case of students and colleges. I'm doing it for men and women, therefore I can simplify their proof a little bit. And I will make both available on the, however you say. Last of all, I must say, on a personal note, I was quite terrified when you said this is being relayed live. You know, I have a wife who's a well-known actress on stage and also a little bit in films. But my only role in theater is to be an usher, show people into their seats. And this is the first time I think I'm on stage, which is somehow being transmitted, you said, right? So it's quite an honor. I will surely look at myself and feel that I could have done much better. That's the disadvantage of taping it, but that's how it is. Any questions? Yes, I can't, I have lost my hearing aids, so you'll have to shout, or I can give you a mic, but try saying it. Yeah. You want me to give some sufficient conditions on the preferences so that the roommate problem has a stable matching, huh? I don't know anything about that. Do you know some results in that direction? I don't. Uh-huh. Oh, it can be Pareto optimal. Oh, well, I'll tell you what Lloyd Shapley said about Pareto optimal. Take all the goods in a society and give it to one Hitler who has strictly insatiable preferences. That matching is Pareto optimal. So what's the big deal about Pareto optimality? Pareto optimal only says, by the way, that the coalition of everybody can't block it. So there are many, what we have done is something which is a very small subset of Pareto optimal allocations, both in the two-sided matching and the one-sided matching. So since we can do something finer, Pareto optimal will trivially exist. Yes, take any man, give him his top choice, then take another man, give him his top choice of the houses that remain. You can do it with women or houses, and that will be Pareto optimal, right? And you can pick the men in any order and do this, you'll get lots of Pareto optimal. But that's not saying very much. Huh? Yeah. 2 minutes are left. Okay, well, I had planned to do two-sided matching in my first lecture and one-sided in the second lecture and do it slowly. However, I'm very happy I finished because I have a lot to say on the Shapley value and the core and so on and convex games. So I'll have time for them in the next 3 lectures. I was going to cut drastically over there, but I'm very happy that I'll have time. But you know, I have just one request. Please feel free to ask questions. It's rather odd to be talking and to a room that is silent. I don't know if I'm communicating or not. That's it for today. Thank you.
We are starting the next session. Please sit down and please keep silent. Professor AUMANN is ready to start.
Hi, Bobby. Bobby, now I call Professor AUMANN, Bobby AUMANN, as he likes to be called. I call Robert AUMANN, professor from Hebrew University of Jerusalem, to give the opening plenary lecture, The Evolution of Economic Behavior. You can start 45 minutes.
Okay. Okay. So I'm very happy to be here and to participate in this workshop, which was organized and the idea was of Marilda Sotomayor, who is a great game theorist, and she has initiated and organized several workshops of this kind. And I'm very glad to open this workshop on game theory and economic applications. Okay, so let's get started. Economic behavior, like all behavior, is shaped by evolution. It's biological evolution, Darwin's kind, and cultural evolution. And cultural evolution is mainly learning from experience, one's own and that of others. Yes, okay, sometimes you hear from other people that a certain kind of behavior is good for you. So in evolution, and sometimes you learn from your own experience. In evolution, the fittest survive. So one may expect economic behavior to be optimal or near optimal. Accordingly, mainstream economics takes optimal behavior, and the optimal behavior is also known as rational behavior. Okay, rational is to behave optimally given your information. Do the best you can, and takes optimal behavior as given. Okay, mainstream economics assumes that people behave optimally rational. Okay. On the other hand, behavioral economics has shown that people generally behave by rules of thumb, heuristics and biases, they call them, which purportedly often call for suboptimal behavior, not rational. Okay. Calling, so people, in fact, they behave not optimally. And that calls mainstream economics into question. And there has been a sort of a disagreement between behavioral economics and mainstream economics on that basis. But in fact, most of the rules, the heuristics and biases of behavioral economics have evolved. So they prescribe optimal behavior. Evolution brings evolution brings about optimal behavior. Most exceptions are in highly unusual scenarios, often contrived to elicit irrational behavior, never really occurring. So it's not subject to evolutionary pressures. If you've learned I'll give examples of this, I'll give a lot of examples. If you've learned, if you have a trick question or a trick scenario that never happened in practice, then people behave irrationally there because it has not evolved. Okay. Now, most exceptions are insignificant. So most exceptions to the fact that rules of behavioral economics prescribe optimal behavior. The exceptions to this are insignificant because they are unusual. The scenario, the setup is unusual. In practice, the biases and heuristics of behavioral economics almost always prescribe optimal behavior. Mainstream economics is rehabilitated, and it's rehabilitated by behavioral economics. Evolution prescribes optimality. Let me explain. Mainstream economics involves formulas they show in mainstream economics that certain kinds of behavior are optimal. Now, people do not, I don't claim that people think things through, but they have gotten used to the optimal behavior by evolution. Okay, they haven't thought it through. They haven't proved that their behavior is optimal, and they don't look for optimality, but they have found that the evolution has led them to behave optimally. Okay. We have examined 34 reports of behavioral economics, heuristics, and biases prescribing behavior that they say is irrational. And these reports include many classic examples of behavioral economics. In each instance but one, we find that the observed behavior that prescribed by the heuristic is either indeed irrational. The heuristic, the rule of thumb prescribes irrational behavior, but the scenario is contrived. And in naturally occurring scenarios, the prescribed behavior is, after all, rational. But in the scenario that is presented in the report of irrational behavior, that scenario does not happen in practice. Or else, the behavior is in fact perfectly rational, though superficially the prescribed behavior may appear irrational. On closer examination, turns out to be perfectly rational. Okay? Now, we said that that is the case in instance but one. And in the one exceptional instance, the observed behavior is indeed irrational, and the scenario is not contrived, but it's not subject to evolutionary pressures. You do it. The example is one in which one really has to make this decision, and it's not enough to bring about optimality in the position. So it's not always the case. I'm not saying that behavioral economics is always off the mark. It's not always off the mark. It's on the mark. But it is, in fact, prescribes usually in 33 out of 34 cases. I found that it is it's either indeed irrational, but the scenario is contrived, or it's perfectly rational. Now, the 34 reports we examined, here they are, and I'm going to go through them quickly. Overeating. Yes, that's a biological evolution. Okay. Hyperbolic discounting. Now, I'm not going to describe these things because it's going to take up too much of my time, but uncertainty, okay? Uncertainty, even if it's very small. The ultimatum game, the endowment effect, the probability matching, choosing a higher probability of getting killed in combat. Okay, there's a report of that that's really happened in World War II. Anchoring, bees, artificial flowers, and nectar. Reinhard Selten's umbrella. New York City taxi drivers not buying subsidized flood insurance. Focusing, generosity, the dictator game. Sunk costs 1, a basketball game. Sunk costs 2, season tickets. Sunk costs 3, boring movies. Mowing your lawn, avoiding temptation, discounts, framing, hypertension, left digit bias, beer on the beach, budget premium gas, Linda. We're going to start with Linda. Okay, paying not to go to the gym, framing, another framing effect, trading on the stock exchange, sunk costs 4, and sunk costs 5. That's the exceptional instance. We're going to get to that, I hope. The Christmas risk aversion and co-holding. Now, I'm going to present some of these examples. I'm not going to have time for 34 explanations, 34, but maybe in the question period, you can or you can ask me to expand on some of these reports, and we'll try to respond to your questions. Okay, so now we're going to examine some of the reports, and the first one, which is maybe the most famous behavioral economics example, is number 25 here. It's Linda. Okay. Now, in Linda, there was a survey made, and the question was asked among students in a university campus. They asked the question like this: Linda is young, single, outspoken, and very bright. As a student, she was deeply concerned with discrimination and social justice. Is it more likely that Linda is a bank teller, or that she is a bank teller and an active feminist? Okay. Now, it's obvious that she may be an active feminist, and there's a lot of hints in the direction of active feminism, but it's more likely that she is just a bank teller, because if she's a bank teller and an active feminist, then in particular, she's a bank teller. Okay. So the right answer is number 1. Okay. But 85% said 2. Okay. 85%, and these were not stupid people. They were students in a university or passers-by in a university, and only 15% said 1. Now, this is one of the first papers in behavioral economics. It's by Tversky and Kahneman in 1983. And this is a seems to indicate that people are irrational. Yes, people are irrational. In fact, I repeated their experiment. I gave a lecture a few years ago to a group from the business school of one of the major universities in the United States, Cornell University. Cornell University, with a group from the business school of Cornell University of maybe 50 students came, and I gave a lecture to them, and I presented them with this question, and not 85%, but 50% of second-year students of business administration said 2. Okay. Now, these are students of business administration. Yeah, okay, so they said something stupid, apparently. I'll tell you another story. My great-grandson, when he was 11 years old, he said to me, he came to visit me, and he said, "Great-grandpa, why did Napoleon wear suspenders?" Okay. Now, I thought and thought and thought about this, and I couldn't give an answer. And finally, and I was aware of the Linda report. I was aware of that, and I couldn't give an answer. I didn't know why Napoleon wears suspenders, and after 5 minutes, I said, "Okay, I give up, and tell me the answers." And the answer is to hold up his pants. To hold up his pants, yes. That is the reason he wore suspenders, and that's the reason that most people, or nearly all people, wear suspenders. So how come I didn't give that answer? Yeah. How come I didn't give that answer? And how come 15% said 1 only, and 85% said 2 in Linda? So what's the rule? What's the heuristic? What's the bias? Rule is take what you're told as relevant, okay? And this is one of the maxims of H.P. Grice. He wrote a book in 1989. He wrote a book, Be Relevant. Make sure that all the information you provide is relevant to the current exchange. Omit irrelevant information. So irrelevant information was that it was Napoleon. And irrelevant information was a long description of Linda. Okay? And it's people assume that you are giving them relevant information. And the relevant information in the case of Linda points to her being an active feminist. And the relevant information in the case of the information and the information in the case of Linda is not relevant, okay? Because no matter what, whether she's very bright or young or single or outspoken, it's a trick question, okay? And it was a trick question, and the people were tricked into giving the wrong answer, and I was tricked into not giving an answer at all. Okay, so that is the most famous example of behavioral economics, and it's okay. Now I'm going to skip this one. Because maybe I'll get back to it if I have time. Now, here's the ultimatum game. two players, the proposer and the responder, must divide 100 euros. If they agree how, each gets his agreed share. If not, both get nothing. They sit at computers in separate rooms and can't communicate directly. The proposal starts by making a numerical offer to the responder without words on the computer screen. The responder responds by clicking yes or no. Okay, so how much should the proposer propose to the responder? Okay, if the game is then over, the players get their payoffs and leave by separate doors. They never see each other, nor do they learn each other's identity. The subjects are students. They don't have a lot of money. Okay. So how much would you propose? Of 100 euros. So obviously, if you propose €1, then it's to the advantage of the responder to accept it. Okay. Okay, let's see what happens in fact. Most proposers offer around 35. Smaller offers, 20 euros out of the 35, are rejected by the responder. Now, why would he reject 20 euros? 20 euros is money. Okay. 20 euros is money, and it's not a lot of money, but it can buy you a few beers, and it's why does the responder reject it? Okay. Now the rule is don't let people kick you in the stomach. Okay, 20 out of 100 is a kick in the stomach. Reject low offers, lopsided offers. Okay. Now the analysis, the mechanism for executing the rule is feelings of wounded pride, insult, desire for revenge. You offered me some picayune amount, which is not enough. And if people kick you in the stomach, kick them back. Okay, reject. So he hoped to get 80, he'll get nothing. The rule and its mechanism evolved in natural scenarios where the negotiators know each other. If in such scenarios you accept lopsided offers, okay, highly unequal offers, you'll get a reputation for doing so. And in the future, you will get only lopsided offers. So rejecting is highly rational. Okay? In natural scenarios, it's highly rational. So it evolved. In the contrived artificial ultimatum game, reputational effects don't apply, as the players are totally anonymous. They don't apply. There's no reputation. You don't get a reputation for accepting 20 euros. You may as well accept them because you don't get a reputation. Nobody knows who you are. But the rule and its mechanism evolved in natural scenarios where what you did does get a reputation, does get known. The rule is rational, in spite of its irrationality in the contrived ultimatum game. Okay, the ultimatum game, there is where there's a negotiation and the two people don't know who they're negotiating with, this never happens in the real world. In the real world, you get negotiations and you know who the other people are. And if you accept lopsided offers, you'll only get lopsided offers. So so like in Linda, the behavior is indeed irrational, but the scenario is contrived. Now let me go to co-holding. Okay. The behavior is that many people hold credit cards with negative balances on which they pay high interest, while simultaneously holding totally liquid savings accounts with positive balances on which they get low interest. This seems irrational. Why not pay the credit card debt with withdrawals from the savings account? Okay, take out money from the savings account and pay the credit card interest. Pay the credit card debt. So you don't have to pay a lot of interest. You get very little interest on your savings account, and you have to pay a lot of interest on it. So why do people pay a lot of interest on their credit card debt, but they keep their money in the savings account? Okay, that's the co-holding puzzle. The rule that explains this is spend with credit cards, save with savings accounts. It's best to separate clearly between spending and saving. If you pay credit card debt with savings, you incentivize yourself to spend more and save less. Okay? Okay, because you'll always remove money from the savings account to pay for your credit card debt. So you're giving yourself an incentive to pay to buy more and save less. It's penny wise and pound foolish. Now, here, unlike in Linda, the supposedly irrational behavior is actually rational. Now, in Linda and in the ultimatum game, in Linda and in the ultimatum game, it was actually irrational, the behavior. But it was a contrived situation. It never happens. This does happen, and it's rational. In spite of the fact that you're losing on interest, you're incentivizing yourself to spend. You're incentivizing yourself to spend less and save more. And the overeating, that was the first in my list of examples. The behavior is that obese people often overeat, okay? And that's irrational. It's irrational to overeat. When you're obese, it's irrational. The rule is eat when you're hungry. That's the rule that evolution brought about. Eat tasty food. The analysis is that though we need food for energy, growth, and various vital bodily function, that's not what makes us eat. We eat because we're hungry and enjoy food. Hunger and food enjoyment are mechanisms that evolved in order to motivate us to eat, like the feelings of wounded pride, insult, desire for revenge, and honor that makes us reject lopsided offers in the ultimatum game. Biological evolution has not yet had time to take into account the sedentary nature of much of modern life. Evolutionarily, obesity is highly uncommon. Now, we know it's not highly uncommon anymore today, but that only happened in the last 200 years. That's not subject of biological evolution. So the rule is rational in spite of its irrational consequences for the obese. Okay? New York City taxi drivers. The behavior is that New York City taxi drivers set themselves a goal of how much money to earn every day. When they reach the goal, they go home. In good weather, it takes time to reach the goal, so they work comparatively long days. When it rains, there's a lot of demand. They reach the goal quickly, and they're able to enjoy a good rest at home. This is clearly irrational. It's irrational because they could rest on the days when there's not a lot of demand, when it's not raining, and make money when when it's raining. Yeah, so it's clearly irrational. When Maya Bar Hillel told me about a few years ago, I was really puzzled. It was the first convincing example of truly irrational economic behavior in the real world that I'd ever seen. It's what people actually do, not a survey. It's what they do. It's not a laboratory experiment. It's what they do in practice in the real world. It's not exceptional. It's not contrived. It's systematic. Did not know what to make of it and started to doubt my thesis. Okay, when Maya told me about this. More behavior. It ain't so. It's not true. It doesn't replicate. Okay, this was published by Kammerer, Babcock, Lowenstein, and Taylor. Taylor got a Nobel Prize in 1918, I think, for his work on behavioral economics. This was in 1997, they reported this in the QJE. Almost, 18 years later, Farber in the QJE, in the Quarterly Journal of Economics, found that it's not true. They don't behave this way. The rule is make hay while the sun shines. That's the rule, and people and the taxi driver really behave that way. My hat is off to Maya, who graciously informed me of Farber's paper. Maya is a champion of behavioral economics. More analysis. Though Farber's numbers differ very substantially from those of the 1997 paper, the latter is more nuanced than I'd realized. It does differentiate between more and less experienced drivers, okay? As Taylor puts it, well, cab drivers have to learn to overcome this bias over time. Okay? The Taylor himself said that, and the conclusion is that evolution works. The cab drivers did not figure this out rationally. They learned it. This is a beautiful example of our central thesis. I don't have time for the last for the housing, the Danish housing market. Well, I'll say it very briefly. The Danish homeowners are less likely to list their homes for sale when current value is below purchase price. And this is an example of sunk cost, okay? The purchase price is a sunk cost, irrelevant to the utility of a sale. And over here, what's happening is that people do this because they sell a house only about once in a lifetime. So they have no experience with this. They have no experience, and if they had experience, they would. But this is a very rare. It's true that it is not artificial. It's not. But it again shows that evolution works because this is not subject to evolutionary. Okay, I'm going to leave this out. I urge you to look at more examples of behavioral economics. I think they all fit. The summary is that behavioral and mainstream economics are perfectly consistent. Indeed, because of evolution, most economic behavior is rational. The exceptions are where evolution does not operate, like in unusual or contrived scenarios. Okay, obrigada. Thank you. Now, there are 10 minutes left to this talk, and I would like to invite the audience to pick from this list. Okay, you can pick one or two examples over here, and let's see what happens in these examples. Now, are there any? Do they have, or are there any other questions? Yes. So I'm ready to accept questions, and I'm ready to accept to try to analyze these 34 reports. Okay.
Okay.
Open for questions.
Any questions?
Can he explain
And-
the choosing a higher probability of getting killed in combat?
What is
The 7.
what's the question?
Can you explain
Could you
the
repeat the
7
question?
choosing a higher probability of getting killed?
The chairman should repeat the question so that I can understand it. I didn't get the question.
The
Hello?
number 7. The 7.
Which number?
Number
Seven.
7. 7.
Number 7. Okay, choosing a higher probability. That's a very interesting question, and we will try to answer this. This is number 7.
Any other question?
Yeah, okay.
Okay. Thank you very much, Bob. And
The bombing mission. Okay, so I'm gonna tell the story of this. During World War II, a squadron of American bombers based on the island of Saipan was assigned the mission of flying 25 bombing sorties to Tokyo, 2,000 miles away. Because of the great distance, most of the weight that the bombers could carry was needed for fuel. Very little could be used for bombs. The mission was very dangerous. In similar previous missions, only a quarter of the airmen survived. Okay, that's in 25 sorties. And I don't say that only a quarter of the planes were shot down in the 3/4 of the planes were shot down every time, but in 20 times or more, 3/4 of the planes were shot down altogether in 20 times. So maybe one per sortie, one out of the one out of the squadron. Okay, and previous only survived. As the mission was about to begin, an operations research officer arrived from Washington with a brilliant proposal. Half the airmen to be chosen by a lot would fly just once. Okay, just once, not 25 times, but it would be one way. Okay, so he would crash his plane in Japan and get killed in the process. Thus, much more weight could be devoted to bombs, and in that single one-way sortie, as many bombs could be delivered as in 25 round-trip sorties. And this is the payoff, each airman's survival probability would increase from a quarter to a half, because he's like a half, with probability a half, he's not chosen to be flight. It's chosen by lot. Now, the behavior was that the airmen unanimously refused the offer. When individually asked why, each replied that he is a better pilot than the other, and he will not be shot down, okay? He will avoid the shooting down. He's a better pilot than the others. Each of the 25 said that he's better than the others, okay? Okay, they were individually asked, not when they were all together. The rule is, in the Army, look ahead just one day. Tomorrow will take care of itself. That's a rule in the Army. I was in the Army also, okay, many years ago. I was in the Army. And the reason, if I could, if in 2 weeks is a festival, and I would like to go home and be with my wife and children for the festival. And and this week they are offering me a leave of absence this Saturday, but next week when there's a festival, I don't. They're not offering me a leave of absence, but somebody else gets the leave of absence in 2 weeks. So do I exchange my leave this week for the leave during the festival? No, you look ahead just one day. Next time, in 2 weeks, there could be a war. There could be, or everybody could get released. Yeah, there's many things that can happen. You look at just one day in the Army. Especially in a war, changes are so rapid and unexpected that it makes no sense for soldiers to make long-term plans. Okay, the airmen were following this rule subconsciously. They said that they are a better pilot than average, and I think they believed it consciously, but subconsciously they were following the rule. Okay? And they're following the rule to look ahead just one day, okay? The story has a beautiful, surprising denouement. After 3 sorties, the island of Iwo Jima, 600 miles from Tokyo, fell to the Americans, and the Saipan mission was canceled. So the airmen had been right. The unconsciously adopted rule worked. Okay? Maybe the decision looked irrational, but the cancellation, but actually it was the rational thing to do. This was related by Kenneth Arrow, who told me, this was related to me by Kenneth Arrow, who told me, who attributed the story to Merrill Flood. Okay, I think we've just about reached the time of the end of the lecture, and I thank you very much, and I thank Marilda for organizing this beautiful conference, and I'm very proud to open it. That's it. Thank you very much. Obrigada.
Okay. Thank you very much. Thank you very much, Bobby. Thank you
Okay.
very much. Okay. And now,
I think that's should be the end of the talk. It's 10 minutes after 10, after 11, right?
yeah, we will talk to each other in the round table. Yeah. The round
Hello?
table. The round table. You will talk on the round table. What is happening?
Hello?
Yeah.
What's going on?
When the round table, chaired by Roger Myerson, will be tomorrow at 10:05. And you are one of the components of the round table. Okay?
Hello? Hello, hello.
Okay, okay. Thank you very much. It is closed? Vai, agora você. Não. Chamar o... Tem que chamar outro agora. Espero que ele esteja aí.
Esperando.
Oh.
Claro. Já.
Now I'd like to call Professor Eric Maskin from Harvard University to give the plenary lecture, Strategic Voting and Majority Rule. Welcome to this conference. You can
Hello
start.
there, everyone.
Yeah, you have 45 minutes.
Okay, thank you. Well, it's a pleasure to be with you, if only virtually. I've been to a few of Marilda's conferences in person, and I can say that they are most enjoyable. I couldn't make it this time, but I'm glad to be with you by video link. So let me show you my slides. Can you see the slides? I hope you can see the slides.
Yeah, we can.
So I'd like to talk to you about strategic voting and majority rule. This is part of a long-term project I have on voting reform, voting reform in the United States, voting reform in Europe, and the emphasis today will be on strategic voting. So what is strategic voting? It's saying that you as a voter prefer candidate X to candidate Y, when actually you really prefer Y to X. And why might you do this? You might do it in order to get a better electoral outcome. Here is a simple example. Suppose there are 3 candidates, red, purple, and blue, and there are 3 groups of voters. There are the red supporters over on the left, and there are the blue supporters over on the right, purple supporters in the middle. And I've indicated each group's preferences. So red voters like red best, then purple, then blue. Suppose that we use the voting method that is most common in the United States, also in Canada and the UK, India. It's called plurality rule. So each voter votes for one candidate, and the candidate with the most votes wins. Well, in this scenario, red will win because red will get 45% of the vote, at least assuming that voters vote truthfully. But notice that if the purple supporters vote strategically, that is, they vote for blue rather than for purple, then blue wins. Blue now will have 55% of the votes, and that's enough for blue to win, and purple voters actually prefer blue to red, and so this strategic vote is worthwhile for them, showing that a plurality rule, which is sometimes called first past the post, is vulnerable to strategic voting. Now, I believe that vulnerability to strategic voting is highly undesirable. And there are 2 main reasons why it's unattractive. First of all, it distorts the outcome that was supposed to occur in the election. If we're using plurality rule, then presumably we have in mind that we want the candidate with the most first place support to win. But if in this example, the purple voters are voting strategically, then red, who has the most first place support, won't win, and instead blue will win. So strategic voting distorts outcomes. But I think even more importantly, it makes life much more difficult for voters. If you're a conscientious voter, it's hard work just to figure out your own preferences. If you're going to be voting in an election and there are a number of candidates, you have to study those candidates, you have to read up on their backgrounds, you have to understand their positions, you might have to listen to them debate. It's actually a fair amount of work if you're going about it in a serious way. If on top of that, you have to know other people's preferences over candidates, then your decision problem becomes several orders of magnitude more complicated. For example, in this 3 candidates election that we were talking about, if the purple supporters are going to vote for blue, if they're confident that that's a good strategy, well, they have to forecast that if they don't do that, red is going to win. They also have to forecast that enough of them are going to vote for blue to make blue more likely to win. And they have to forecast that that the blue supporters won't vote for purple, which would sort of counteract what the purple voters are supposed to do. So all of that is very demanding. it requires a great deal of extra knowledge on the part of voters, and it would be much simpler for them if all they had to do was to vote according to their true preferences. Unfortunately, there's a famous negative result, the Gibbard-Satterthwaite theorem, which says that there's no voting method except for a dictatorship that is always resistant to strategic voting. Now, I would argue that this result is overly pessimistic because Gibbard-Satterthwaite insists that voters' preferences are entirely unstructured, entirely unrestricted, and in reality, preferences usually are structured, and preferences usually are restricted. What do I have in mind? Well, many years ago, Duncan Black, the political scientist and economist, argued that we should expect preferences in partisan elections to be single-peaked. What did he mean by that? He meant that in partisan elections, candidates tend to line up on an ideological spectrum going from the far left to the far right, and voters also line up on this spectrum, and a voter is going to tend to prefer candidates that are closer to her on the spectrum than those that are farther away. And this is going to lead to a picture like this, where we put the candidates on the horizontal axis and we graph the voters' utility on the vertical axis, and the utility graph will have a peak someplace. In this case, has a peak at purple. Single peak preferences, Black argued, can be expected. Now, is that a good assumption? Well, actually, part of this paper, which I hope to tell you a little bit about at the end, is empirical, and we actually looked at voters' rankings in actual elections, and it turns out that it's actually a pretty good assumption. Of course, it doesn't fit exactly, but it fits well enough so that the theory that I'm going to be showing you actually works. Now, Black proposed using majority rule as the voting method, or this is sometimes called Condorcet voting. In majority rule, voters do more than just vote for a candidate. They rank the candidates, and then the winning candidate is the one who, according to the rankings, beats each other candidate in a head-to-head contest by a majority. So here's an example. Once again, there are three candidates, red, purple, and blue, and I've shown you how the electorate breaks down into four different groups. In this example, the Condorcet winner is purple, even though purple will only get 25% of the first place votes. Purple beats red because these voters prefer purple to red, so do these, and that adds up to 54%. And purple also beats blue. These voters prefer purple to blue, these do too, and that adds up to 71%. So Condorcet the Condorcet winner is clearly purple. Now, Condorcet himself, back in the 18th century, understood that there are circumstances where a Condorcet winner may not exist, and he gave, as his famous example, something like this, where there are 3 candidates, X, Y, and Z, and approximately 1/3 of the population has preferences X, Y, Z, and similarly for YZX and ZXY. In this case, there's no Condorcet winner because X beats Y, Z beats X, but Y beats Z. And this is called the Condorcet cycle. But Black showed that Condorcet cycles cannot occur if preferences are single-peaked. If preferences are single-peaked, a Condorcet winner always exists. And you may have seen this argument before, but it's so simple, I'm going to show it to you again. So each voter will have a favorite candidate corresponding to that voter's peak in the utility graph. Let's look at the candidates which constitutes the median peak. So X is the median candidate if 50% or more of voters have their peak to the right of X, and 50% or more have their peak to the left of X. And now let's compare X with some other candidate, Y. As I've drawn it, Y is to the left of X. Well, notice that any voter with a peak to the right of X is going to prefer X to Y, because according to single peak preferences, you always prefer candidates who are closer to you than those who are farther away ideologically. So X will get a majority of votes in the comparison with Y. But we can turn this around, and X will also beat a candidate on the right. So X will be the majority winner, or the Condorcet winner. So a Condorcet winner not only always exists with single peak preferences, but it's going to end up being the median candidate. Now, we can also explore strategic voting in this setup. We might ask the question, does any voter or coalition of voters gain from voting strategically? Well, that would entail submitting false preferences over the candidates. So suppose there's a coalition V, which by voting falsely creates a false Condorcet winner by manipulating their preferences. So let's suppose that X is the Condorcet winner if everybody votes truthfully, but if the members of the coalition V vote falsely, they create a false Condorcet winner Y. Now, why might they do this? They would do it because they prefer, the members of the coalition prefer Y to X. You wouldn't join the coalition unless you preferred Y to X. But the point is that if they prefer Y to X, they would be ranking Y above X when they were voting truthfully. In other words, if they create a false Condorcet winner by voting falsely, they were already ranking Y above X when they were voting truthfully. And so that means that they can't create a false Condorcet winner that they prefer to the true Condorcet winner. They were already voting for the false Condorcet winner to begin with. So that tells us that the coalition is never going to want to create a false Condorcet winner, but that doesn't settle the question of strategic voting. Oh, by the way, the argument I just gave you is an old one. It goes back to Dummett and Farquharson 65 years ago, but it doesn't settle the question about strategic voting and majority rule, because perhaps voters might gain from creating a Condorcet cycle. And let's look at that. So this is the same example I was talking about a few minutes ago. Suppose that, oh, and you can check that preferences are single peaked here. If red is on the left and blue is on the right, and purple is in the middle, then actually I said it the other way around. Red is on the right, blue is on the left, purple is in the center. Then preferences are single peaked. Purple, as we already noted, is the Condorcet winner. But suppose that the red voters decide to vote strategically. Instead of submitting their true ranking, red, purple, blue, they submit the false ranking, red, blue, purple, instead. Well, then we get this profile here. And in this profile, there is no Condorcet winner. Red beats blue, blue beats purple, but purple beats red. So we go round and round as in a Condorcet cycle. Clearly what we have to do, Condorcet himself acknowledged this, is to have a tie break rule. If there's no Condorcet winner, you have to break the tie using some other method. And one common tie break rule is the one that Black himself proposed. This is the same Duncan Black who introduced single peak preferences. Black said, well, if there's a Condorcet winner, you elect the Condorcet winner, but if there's no Condorcet winner, you elect the board account winner. What is the board account winner? Well, in a 3-candidate election, voters rank candidates, and a candidate gets 2 points every time she's ranked first, 1 point every time she's ranked second, 0 points for a third ranking, and we just elect the candidates with the most points. Now, in this example, that is red. Red is the board winner for this profile, which has been manipulated by the red voters. They're voting falsely. But this is a worthwhile manipulation for the red voters because they prefer red to purple. If they voted truthfully, they would get purple. If they voted falsely, and we're using Black's method, they get red. So this shows that that Condorcet voting, majority rule voting, is manipulable if we use Black's method to break ties. Now, you might ask, well, what if we use some other tie-breaking rule? There's, in fact, a very substantial literature on tie-breaking rules, Condorcet tie-breaking rules, going back to Condorcet himself. These are called Condorcet completion methods. There's, just to name a few, there are literally dozens of them. There's Copeland's method, there's the Kemeny-Young method, there's the Minimax method, Nansen's method, Dodgson's method, and so on. If you go through all of the voting methods in the literature, it turns out that all of them are manipulable, which sounds unpromising, but that still doesn't settle the question, because perhaps there's a way to elect a Condorcet winner using a tiebreak rule, which is strategy resistant. And the answer to that question is yes. I'm going to show you a way to elect Condorcet winners in a strategy resistant way. And this method turns on the fact that if preferences are single peaked, as in this example here, we will tend to see more diversity among the supporters of candidates in the middle than for candidates who are at the extremes. What do I mean by that? Well, in this example, there is only one single-peaked preference in which candidate red is ranked first, which is red, purple, blue. If you put red first, you can't put blue second, because blue is all the way over on the opposite ideological extreme. So red voters, if they're single-peaked, have to have preferences like this. Blue voters have to have preferences like this, but there's more flexibility for purple voters. Some of them might put red above blue, some of them might put blue above red. Both of these rankings are consistent with single peakness. Now, I've showed you this for the case of 3 candidates, but the same principle holds with any number of candidates. We will tend to see more flexibility, more diversity in rankings among supporters of candidates who are more toward the middle of the ideological distribution. This is an endogenous feature of preferences when preferences are single-peaked. So what I propose to do is to exploit this natural diversity in creating a voting method that is resistant to strategic voting. And so what we're going to do is, for each candidate, we're going to calculate that candidate's diversity score, which is simply the number of different ways in which that candidate is ranked first. So once again, in this example, purple has a diversity score of 2 because some voters have the ranking purple, red, blue, and other voters have the ranking purple, blue, red, but red and blue each have diversity scores of 1. There's just one ranking of red, purple, blue, and there's just one ranking in which blue is ranked first, blue, purple, red. So you can think of the diversity score as one possible measure of how broad a candidate's support is. And as I said, we're going to make use of a candidate's diversity score in our election rules. So here are the election rules. We first, as in ordinary Condorcet voting or ordinary board of voting, we have each voter rank the candidates. And then if there's some candidate who is the Condorcet winner, well, that's the end of the story. And that candidate is elected. But if there's no such if there's no such candidate because there's a Condorcet cycle, then we drop the candidates with the lowest diversity score. And then we look again to see whether there's a Condorcet winner. And we keep dropping candidates with the lowest diversity score until eventually there is a Condorcet winner. There has to be a Condorcet winner eventually because there's only a finite number of candidates. By the way, if there's a tie for the lowest diversity score, we can drop the one with the fewest first place votes. So those are the election rules. Let's explore how they work in our example. In our example up here, where voters are voting truthfully, then purple is the Condorcet winner. That's the end of the story. But let's suppose that the red supporters try to manipulate things and submit the false ranking, or at least some of them submit the false ranking red, blue, purple. Let's suppose that some red voters vote truthfully, red, purple, blue, but others vote according to this false ranking red, blue, purple. Then we get this profile here. And you can check that there's no Condorcet winner. Red beats blue, purple beats red, blue beats purple. There's no Condorcet winner. And so now we have to use our diversity score Condorcet completion rule. We will drop the candidates with the lowest diversity score. Well, that's blue here because because of the manipulation, red has a diversity score of 2, purple has a diversity score of 2, blue has a diversity score of 1, so blue gets dropped. And now it becomes a contest between purple and red. But purple wins because these voters and these voters and these voters all prefer purple to red, and they constitute a majority. They're 54% of the electorate. So red can manipulate and create a Condorcet cycle, but if we now apply our election rules, the manipulation, we see that the manipulation doesn't pay. Yes, red can get blue dropped, but red still loses to purple. There's no manipulation that red can do in which red can get purple dropped. And so by virtue of the fact that purple really is the true Condorcet winner, purple will always beat red. And that in one slide is why these election rules are going to successfully deter manipulation when voters' preferences are single-peaked. Let me make this a little bit more formal. So we're assuming that that voters' true rankings are single-peaked. We're also supposing that each possible single-peak ranking is represented in the electorate. So in particular, that means that purple is going to have a diversity score of 2 because both the ranking purple, red, blue and purple, blue, red will be represented. We might call that the fullness assumption. And I'm also going to place a limitation on the kind of manipulation that voters undertake. In the manipulation I showed you before, red voters manipulated by some of them submitting the ranking red, blue, purple. They might also, at the same time, have submitted the ranking blue, red, purple, in which case they would be elevating blue's diversity score. That manipulation actually might be successful because by doing that, all three candidates have diversity scores of 2, and now we eliminate purple, which is what red wanted to do. I would argue that that kind of manipulation, where some voters are manipulating to the left of the Condorcet winner, some voters are manipulating to the right of the Condorcet winner, is in practice much too complicated for a coalition to undertake. And so I think it's not a bad assumption to rule this out as being utterly impractical and also dangerous. If the red voters are submitting the ranking blue, red, purple, then they run the risk of electing blue, which is the worst possible outcome as far as they're concerned. Anyway, if we make these three assumptions, then we get the main result of the paper, which is that the voting rule that I showed you is actually resistant to strategic voting. Now, you might ask, well, we've been concentrating on Condorcet voting. Is there some other kind of voting which can be made resistant to strategic voting in the same way that we made Condorcet resistant when preferences are single peaked? The answer to that turned out to be no. Condorcet methods are uniquely strategically resistant, at least if we confine attention to voting rules that are anonymous and neutral. An anonymous voting rule is one where all voters count equally. In other words, only their votes count, their identities don't matter. And that is a very natural requirement for a political voting rule. And then the other requirement is neutrality, that we treat all candidates equally. We don't want to, say, give special treatment to the incumbent. But if we treat all candidates equally and all voters equally, then only Condorcet methods can be made strategically resistant. And the way to see this is, again, through an example. Let's suppose that the true preferences are given by this profile up at the top. Suppose that, and we saw that for these true preferences, purple is the Condorcet winner, but suppose we had a voting rule in which red rather than purple was the winner. So this is a non-Condorcet method. Could it possibly be resistant to strategic voting? Well, suppose that these voters here, the purple, blue, red voters, voted strategically red, purple, red, blue. Well, for this profile, then it would have to be the case that red wins, just as red wins for this profile up at the top. Otherwise, the the purple, blue, red voters would gain by manipulation. Notice that the purple, blue, red voters rank red at the bottom. So if they can get anything better than red by voting in this way, they will. So that tells us that red must win for this profile. And similarly, if the blue voters also join this coalition, the outcome for this profile must also be red. Otherwise, these voters would gain by manipulating. So let's look at this profile here. Now, we're confining attention to voting rules which are neutral in the sense that all candidates are treated equally. That means that if we permute the candidates, we have to permute the winner in the same way. So let's permute the candidates. Let's replace red by purple, and let's replace purple by red. So in this profile here, everywhere you see red, you replace it by purple, and everywhere you see purple, you replace it by red. And then we get this profile here, and we have to permute the winner in the same way. So we said that red wins here, so that means that purple must win here. But if purple wins here, these red voters, some of them can vote for purple. Some of them can vote purple, red, blue, and reproduce this profile here where red wins. And so that manipulation will pay off. In other words, if a voting rule is not Condorcet, there will always be a majority coalition which can manipulate and do better for itself. That this shows the uniqueness of Condorcet voting methods in the sense of being resistant to strategic voting. Now, let me conclude by talking a little bit about the empirical side. I said that although single peak preferences, of course, don't literally apply in reality, they're a pretty good approximation. And to see that, we actually have data from the United States, because there are now two states, the state of Maine and the state of Alaska, where we have actual ranking data. Maine in 2018 went over to ranked choice voting, in which voters rank candidates. Alaska went over to ranked choice voting in 2022. So we have the actual ranking data from these elections. Is it single peaked? Not quite, but pretty close. And here is a typical example. This is an example from Alaska in 2022. There was a race for Alaska's representative in the U.S. House of Representatives. Alaska doesn't have much of a population, so they only have one House seat. And there were three candidates for the House seat. Sarah Palin, who became famous years ago because she was John McCain's running mate in the 2008 election. She was a pretty far right Republican, Trump supporter. There was another Republican named Nick Begich, a more traditional Republican, who was running, and there was a Democrat running, Mary Peltola. And here are the actual rankings in that election. So to explain what this means is 18% of voters ranked Palin first, then Begich, then Peltola. 11% did what is called bullet voting. They just voted for one candidate, in this case Palin. They didn't choose to rank Begich and Peltola at all. And we see some bullet voting here, and there's some bullet voting here. So bullet voting is a violation of single peakness because voters are not ranking all the candidates. However, it's bullet voting is consistent with what we might call weak single peakness, where the Palin voters don't rank Begich and Peltola, but at least they don't rank Peltola above Begich, which would be a strict violation of single peakness. Now, there were some strict violations of single peakness in this example. Notice that these voters here put Palin first. Palin is to the far right, Peltola second, Peltola is to the far left, and then Begich. So this is a violation of single peakness. And this is a violation of single peakness. Voters who put Peltola first, Palin second, and Begich third. But notice that these strict violations of single peakness are pretty rare. Only 2% of voters had this ranking. Only 2.5% of voters had this ranking. And so it turns out that if we change our voting rules a little bit so that a voter gets a diversity point, a candidate gets a diversity point only if at least 4% of the electorate has a particular ranking, then the method I showed you before continues to work. So it's the same rules as before, except that you don't get a diversity point for a particular ranking unless at least 4% of the electorate has that ranking. And so that would rule out this ranking here, which is non-single peaked, and this ranking here, which is non-single peaked. With that change, the election rules work just fine. And as I said, this is a typical pattern for Alaska and Maine elections. In every single election which has been held to date, if we use this 4% rule, then the election method that I showed you will produce a Condorcet winner and will also be resistant to strategic voting. So that is that's what I wanted to tell you. I think that for countries which are badly polarized, like the United States, Condorcet voting is extremely attractive as a voting method because it gives us compromises. It elects candidates in the middle, which is attractive. And as I just showed you today, we can use a version of Condorcet voting, which is actually strategy resistant, which is also, I think, a very attractive property. So let me stop there and thank you for your attention. I don't know, is there meant to be
Okay.
a Q&A session now?
There is no time for questions.
No, no
Now-
time for questions.
now
Sorry
we
about
have-
that.
We have a lunch. Okay, thank you very much, Eric.
Well, thank you. Thank you. Good. It was good to be with you. So I will leave then.
Como é que desliga aqui?
Posso dar uma visão do almoço? Rapidinho.
Hello. Just going about lunch. If you are a student, lunch will be on the fourth floor. There will be volunteers accompanying you. If you are a professor, lunch will be behind the in the building behind. There will be also volunteers accompanying you to get you there. Okay.
Well,
one-
all the students
Oh, please, let's get ready to start this afternoon's mini course. Only two announcements, please. The students who are attending the courses and wish to have a certificate, they have to sign the list, like to say that they attended. Okay, every lecture you go there and sign. There is a form outside. Okay, and second, those who wish to return to the hotel, there will be a bus at 1:30, and that will be the last bus. Return to the hotel in the afternoon. Then the bus will pick up anyone who is in the hotel back here, and then after the ceremony, the opening ceremony, we'll have soup, some food, and then after the food, the buses will be taking everyone back to the hotel again. But that will be later this evening, okay? The schedule is 8 p.m. So we are happy to have Professor Michael Ostrovsky, who is starting the mini course on matching, carpooling, and congestion pricing.
Okay, thank you. All right, so thanks everyone for coming. And this is, in the program mini course 2 on market design. And I'm going to talk about transportation markets. And I'm going to talk about matching, which you'll see why I'm talking about matching in the context of transportation markets, carpooling, congestion pricing, all those other things. That's the content of those 4 lectures. Before I get into more detail on that, I want to start with this photo. That's sort of the problem that I'm trying to solve, and a lot of people are trying to solve, right? So this photo, some of you have already seen this photo because I've used it for several years to start my talks on this topic. And of course, this photo could have been taken anywhere, but as fate would have it, this photo that I've been using for a few years is actually from Sao Paulo. I just realized that yesterday I was going through this slide. I'm like, where is this from? Like, I vaguely remember it was something Portuguese speaking. Like, oh yeah, it's from Sao Paulo actually. So, quite a coincidence. And we want to solve it, right? Because this photo could have been taken anywhere. Traffic congestion is a huge problem worldwide, and we want to see it finished and sort of in the foreseeable future. So here's the plan of this specific course, right? Obviously, we're not going to solve everything in 4 lectures, but at least I hope that by the end of those 4 lectures, you'll see that there is hope, that there is a potential way forward. So in the lecture today, I'm just going to talk about two-sided matching with transfer. So this is going to be a purely theoretical lecture. In fact, lecture today is not going to be related to, I'm not going to talk about transportation in any way, shape, or form. It's going to be, if anything, it's going to look like a continuation of Professor DUBEY's morning lecture on matching. It's just, I will introduce transfers. Now, lecture 2 tomorrow is where transportation will actually show up. I will teach you this beautiful model by Vickrey from 1969. It's the same Vickrey most of you know, right? The Vickrey of the Vickrey auction and of the VCG mechanism. What most of you don't know is that in addition to that amazing work, Vickrey is also one of the founding fathers of transportation economics. I did not know that until I started working on this topic. I never learned in grad school or anywhere else. And I'll teach you this beautiful, very simple, but very powerful model of traffic formation. And then in that model, I will show you actually Vickrey's results on how congestion pricing works or doesn't work, and exactly what that means. I'll show how self-driving cars, again, in the context of that framework that's 50 years old, it's very easy to see that they won't help us, in fact, that they won't save us. And then I will introduce kind of this new idea of carpooling, which I think is the way forward, is the way how things can be dramatically improved. And that's what lecture 2 is all going to be in the context of this very stylized very basic Vickrey model. And there kind of, it's sort of like the complementary part to today's lecture, where there's not going to be much matching there other than just mechanical carpooling, but there's going to be a lot about transportation. Today, it's all about matching, almost nothing about transportation. Lecture 3 is where I'm going to bring everything, all of this together. And I'll present this kind of overarching framework that's going to be heavily based on matching, right? That's why we need today's lecture. It's going to talk about self-driving cars and carpooling and congestion pricing and how they can all in principle interact in a way that's genuinely going to help us, solve this. All right. And then the last lecture, the first 3 are going to be, theories with theorems and, results. The last one is actually going to be empirical. I'm going to tell you about the latest experiment, well, not really experiment, attempt to introduce congestion pricing in New York City. They launched congestion pricing in a year and a half ago, January of 2025. I'll tell you about some issues, some results, how it can be improved, and why they still need a lot of help from market designers. So that's the plan for the course, for the 4 lectures. I know some of you may have seen some of the some of these topics, so feel free to pick and choose. But that's the outline. All right. So let's jump into today's lecture, which, as I said, you can even think of this as lecture 1.5 in Professor DUBEY's mini course, except he talked about matching without transfers, and I will talk about matchings where payments are possible. But before I do that, we're going to do one warm-up slide on matching without transfers on the Gale-Shapley model. And the reason why we're going to do it is I'm going to show you an alternative proof to Gale-Shapley, and it's due, the proof is by Marilda Sotomayor, very appropriately. It seems hard to believe that it's possible, but it's a simpler proof than Gale-Shapley. Okay, so I'll show you this proof. And here, part of the reason is just to thank Marilda for organizing this amazing conference and presenting her result. But I will then show you how to use the same trick in a much more complicated setting to get something that's usually proved with like lattice theory and all this other stuff in one paragraph. Okay, and it's going to use the same idea. All right, so enough sort of poetry. Let's get to math. So there are standard setting of Gale-Shapley that you just saw this morning. There are M men, there are N women. Each side has preferences over those on the other side. Your goal is to generate a matching, which is a way to pair up men and women, one on each side. And a blocking pair is a pair man-woman, such that the man prefers that woman to his assigned option, possibly empty, and the woman prefers this man to her assigned option, possibly empty, because the idea is they would just marry each other and not agree to this proposed matching. Okay, and of course the Gale-Shapley theorem says that a stable matching is guaranteed to exist and gives us this deferred acceptance procedure for finding one. All right, here is a simpler proof than through the deferred acceptance algorithm, Sotomayor 96. Definition: we're going to call a matching simple if for any blocking pair MW, the woman in that pair is single, right? So let's just think about this for a second. So clearly every stable matching is simple because there are no blocking pairs. An empty matching is also simple because every woman is single. So whatever blocking there is, the woman that there is going to be single. Okay, so that's the definition. Now, of course, the set of matchings is finite. Therefore, there must exist at least one matching, one simple matching, that is Pareto optimal for men. When I say Pareto optimal, there may be a few of them, right? And I'm not saying all the men are going to agree on which one is the best for them. All I'm saying is that there is at least one matching, one simple matching, such that there is no other simple matching that is strictly better for at least one man and no worse for all the others. Okay, just completely mechanical, just from finiteness. Okay, there's nothing deep here. Okay, but here is the cool observation. Here is this sort of one-line proof once you introduce this definition. Take that Pareto optimal for men simple matching. It has to be stable. Okay, why is that? It just seems kind of like it almost feels like we cheated, right? We didn't do any hard work. But it turns out this works. So why does it work? Suppose this matching mu star, which is a Pareto optimal for men simple matching, suppose it's not stable. Well, then they must be blocked by some pair. By definition of stability, by the definition of simplicity, that pair has to involve a single woman, right? So let's say this woman W. Now we have to do something slightly delicate. Now we say, okay, we know there is at least one blocking pair involving this woman W, but there may be more. So of all the blocking pair involving this woman W, let's pick the one with the man she likes the most. Okay, so let's say this is M prime. Now let's generate a new matching, mu prime, where this woman is matched to M prime. And if M prime was matched to someone else in the earlier matching, we just discard that match. Okay? So now notice that this new matching is Pareto improved for the man, because this man M prime is better off and no one else is worse off. That's why we're looking at this single women. And it's also still simple because we did not generate any new blocking pairs, which contradicts the assumption that we started with a Pareto optimal simple matching. Okay, that's it. So that's, a proof that's shockingly even shorter than the Gale chapter. No. If M is not but M was not married to W, right? MW was a potential blocking pair. All right. Okay. All right. So now put that in your sort of back pocket. We'll come back to this idea at the end of the lecture. And now let's talk about matching with transfers. Now I'll give you a bit of a chronological progression of how it worked. So the starting point for matching with transfers is the primary reference is this paper by Shapley and Shubik from 1971. It's in chapter 8 of ROTH and SOTOMAYOR. We're going to start with one-to-one matching, where there is one group P with M agents on one side, I1 through IM. There's group Q with N items, J1 through JN. And it's also known as the assignment game or the optimal assignment game. And for each pair of agents, we know how much value they would generate. So imagine we're matching workers to jobs. For each worker, we know what's the total value that's produced by this worker job pair, right? Without yet worrying about how much they pay the worker. It's just how much they produce. Okay, so this total surplus produced by a given match, IJ, is given by alpha IJ. All right. And if an agent is left on their own, the production value is 0. So this gives us a matrix, M times N, summarizing all of these values of potential matches. All right, now we need a few definitions. Definition, an assignment is a matrix X of size M times N, right? M times N on the side, whose elements are all zeros and 1. And 0 means that there is no match. 1 means that that row and that column indices are matched. So the sum of elements on each row and each column is at most 1. Okay. If your row sum is 0, that means that you're not matched to anyone. Now, a feasible outcome. So now we start putting payoffs on this thing. Is going to be a triple that contains this assignment, X, and also contains vectors of payoffs. U are the payoffs of the first group of agents, right? It lives in RM. You can place it, so it lives in RM. And then V denotes the payoffs of this right side of agents, this, Q, n-dimensional one. And so this triple vector u, vector v, and assignment x is feasible if the total amount generated by all these matches, right? So the sum alpha ij xij, right? That's the total output in this economy, is sufficient to give, all of these payoffs u and v to all of the agents in the economy. Right? We're not yet discussing, will they want to do it, will they not want to do it. It's just feasible, right? If this is the assignment, we have enough money to give those payoffs to agents on these sides. Make sense? All right. So in other words, an assignment tells us who is matched to whom. Feasible outcome also tells us in addition how we allocate that surplus. Now, next definition is very natural. We say that the assignment is optimal if it maximizes the total output of the economy, right? So it's the way to make as much surplus as possible, total surplus. Now, the key economic sort of thing that's going to tie a lot of things together here is this notion of stability. Now, it's going to look very different from how stability is defined in Gale and Shapley, but it's actually in spirit the same thing. So let me first give you the formal definition and then explain why in spirit it's the same thing. So the formal definition is the following. A feasible outcome u, v, and x is stable if for every p agent I and q agent j, every pair of agents, if we add up their payoffs in that outcome, then they are at least as high as the total value they can generate together. Right? And the idea here is if this was not true, right, if you had the less sign over there, then agents I and j could say, wait a second, let's run away, let's match with each other on our own, we will generate alpha ij together, and then because in this model, transfers are continuous, there's going to be a way for us to share the surplus so that both of us are better off. All right? Okay, so that's the definition of stability. Now that we have the definitions, let's start proving some lemmas and theorems. And again, this goes back to Shapley and Schubeck. Lemma, if UVX is stable, then it's actually quite a bit simpler than you may initially think. Specifically, in any stable assignment, all the unassigned i's and j's have to get 0, and all the matched pairs have to get between them exactly the total value that they produce. Okay, so there is no cross-subsidization, right? So in stability, so the only question essentially becomes, if I'm matched to someone, we generate 17 units of surplus, how do we split that, right? There is no sort of cross-subsidization across pairs or unmatched agents. So why is that? How do you prove that? Well, the way you prove that is the following. Go back to this inequality, okay? And now imagine that what you have, I don't have the whiteboard here, so we'll do it sort of in virtual space. So imagine that I first list all the matched pairs, okay, all the P1, Q1, P2, Q2, etc. And then below them, I list all the unmatched agents, okay? And I add up all of these sort of, all of these payoffs. Now, I know that each row for the matched pair is going to be greater than or equal than their alpha ij. And for the unmatched one, it's going to be 0. So when I do this big addition, I get that the sum of payoffs of all the agents in the economy has to be, for a stable assignment, has to be at least as high as the value produced in this economy, right? Because for each matched pair, they have to get at least as much as they produced. So the total payoff of those who are matched has to be at least as high as the total value that's produced in the economy, plus all the remaining agents get at least 0. So we know that the sum of all of those U's and V's has to be greater than or equal to sum of all the alpha I, alpha ij, xij's. Now, at the same time, by feasibility, we know that this big sum has to be less than or equal than the sum of alpha ij, xij. It's just the condition in line 5, or in the third line of that definition. So which means that all of this inequalities becomes equalities for the stable matching. You have the same thing on the left and on the right. So for a stable assignment, all of this greater than or equals just become equals. Okay. All right. So that's sort of that's kind of a key proof trick in this setting, where instead of looking at just one pair individually, you say, okay, let's look at all the matched pairs. Let me add up inequalities across them, and then that gives me a ton of information. Okay, we're going to do the same trick again right now. The next theorem. If UVX is stable, then it is also optimal. Okay, that one should be more surprising, right? The first one, yeah.
The second theorem, next page,
Yeah.
implies the first one too, because the first thing we said that the coalition of everybody can't block. And the second says no coalition. So the first theorem is technically correct.
Well, not quite.
The whole coalition can't block.
So, okay, so let me be a little bit careful. So the first lemma essentially says that no coalition of one agent can drop it, and the coalition of like a pair can drop it. This theorem says that the grand coalition can drop it, and then there is a separate argument that any sub-coalition, which will also be true by the same argument, but that one, yeah, okay, all right. Okay, so this one is more surprising because it says, look, the stability only talks about kind of each individual pair, right? But somehow it ties together the entire universe and gives us the optimal assignment. That's interesting. And by the way, preview that will show up in lecture 3 when I talk about matching for self-driving car co-passengers, where we'll say, oh, it's enough to make sure that they are doing the right things for themselves, and then by similar arguments, it will propagate back to the entire economy. But anyway, let's go back here. So how does the proof work? The proof works in the following way. Suppose we're given the stable outcome UVX. Now take any other assignment Y. Yeah, suppose Y was optimal. Okay, so take that assignment Y. Then what we do is we say, okay, let's do the same exact trick as we did before, okay? But we will do it over assignment Y, okay? So we start with this alternative assignment Y, and then we say, let's first list all the pairs in this assignment, okay? And then below, we're going to list all of the unmatched agents, okay? And for each unmatched agent, we just say, oh, like their payoff is greater than or equal than 0. That's not interesting. And then for each matched pair, we're going to say, oh, U of the agent in that pair plus V of the other agent in that pair has to be greater than or equal than alpha corresponding to that pair in assignment Y. So now we add all of these things up, okay? All of these inequalities up. What do we get? We get, carefully, we get the inequality on the right, right? This one, right? Because we were adding up across all of the matches in assignment Y. But we know that we started from a stable assignment, okay? And for the stable assignment, we already proved that lemma. So we know that the sum of all these U's and V's has to be equal to the sum of alpha ij xij over assignment X. And so just so that's the left equality. And so you just immediately get that the left-hand side is greater than or equal than the right-hand side. Okay? So that's sort of kind of where the bodies are buried, even in going from stability to optimality. And then, as we just discussed, you can replicate the same argument. It doesn't have to be for the whole grand coalition. You can show it for any sub-coalition. So that's this last theorem on the slide, and I'm not going to prove it. You can do it as an exercise. It's very similar to what I just did here. Okay? All right, let's keep going. All right, so here is the hardest part of this lecture. So if you need to have this extra gear, turn it on now for the next few slides. And so the key theorem here, once you prove that every stable outcome is optimal, is to prove that a stable outcome actually exists. Okay? And that is not a given. You may say, oh, yeah, of course it exists. Here is an example. It's very similar to the roommates problem, just so that you don't think it's automatic and trivial. Suppose we don't have this two-sided structure. Suppose we just have 3 agents, and any pair can generate a pair of 1. That's it, right? In that setting, there does not exist a stable outcome. Why is that? Well, suppose their names are A, B, and C. A is matched to B, for example, and they split it in some way where at least one of them gets less than 1. It has to be the case because the total amount is 1, so at least one of them has to get less than 1. Then that person who gets less than 1 and the remaining person who gets 0 say, oh, why don't we rematch and we can both be better off? Okay? So it's a very simple counterexample. So once you have it, it's like, oh, so why does it not happen the same way here? And that's where we're going to have to do this work. Okay? All right. So the proof technique, and one of the things you will get after, the morning lecture and the lecture today, you're going to have a bunch of different techniques for proving results in this set of problems. So this proof is going to be, you've already seen 2, right? You've seen the deferred acceptance algorithm and this kind of shortcut due to, Marilda SOTOMAYOR of looking at the simple matching. So here's a third one. It's going to be through linear programming. Okay, it's one of the canonical approaches. And what we're going to do is the following. We're going to say, well, suppose we just forget about this whole matching business and everything else. Let's just write down this problem of finding the optimal assignment. Okay? And let's write it down as a linear program, right? What is it going to look like? Well, here is this linear program, right? Maximize the total output, which is the sum of those alpha ij's over whoever is, how people are matched. What are the conditions we have? The conditions are that the sum of xij's in each column in each row is less than or equal than 1, right? We had that in feasibility. The sum of xij's in each row is less than or equal to 1, and in each column less than or equal than 1. And all the entries are positive or non-negative, right? You can't have like minus 0.3 of a match. Now, notice that, so if we added integrality conditions, right, that each xij has to be an integer, 1 or 0, then this is literally the same problem as we had before. So the only difference now is that I removed that. I now allow these things to be fractional, right? So it could be 0.5s running around or 0.3s or whatever. Okay? However, so this is a linear program. Everything here is bounded. So it is going to have an optimal solution. There is a theorem, which I'm not going to prove for you, that says that in this type of problem, there always exists, even if you don't impose integrality, there is at least one solution that is in fact integral. Okay? Each xij is either 0 or 1. Normally, if you read Shapley-Shubik, or if you read standard expositions, the proof relies on the total unimodularity of the set of constraints. Total unimodularity means that you look at any square submatrix of the set of constraints, and the determinant is going to be -1, 1, or 0, which sounds complicated. So in this setting, you can actually prove this by hand because it's sufficiently special. You can just start with a fractional matching. And by staring at it, you can see that you can perturb it in some direction so that constraints are still satisfied. but things are closer to being integer. If you're genuinely interested, catch me afterwards, I'll show you. So
The paper of Shapley and Kubik, they do it by hand or?
no, they use unimodularity, yeah. But again, that's a good exercise if you want to prove it by hand. And by the way, this is the part that breaks if you try to do the roommates kind problem. If you have this problem with 3 players that I just described to you, right, each of whom would generate value 1 was paired with the other person, and you put this into this LP, then the optimal fractional LP is going to be 0.5 of each match, right? And this 0.5 of each match will give you a total value of 1.5, whereas the integer solution would only give you best possible match of 1. So this two-sidedness, actually, this is where it really comes into the picture. Okay? All right. So now here is where the heavy math is hidden. So let's go over this slowly. And if it's the first time you see this, it's probably very hard to understand on the fly, but at the very least, you can get the gist of it. And then if you want to know, you can go and kind of go through this by hand to verify that what I'm saying is like, well, what Shapley and Kubik are saying is actually true. So here we're going to rely on this famous theorem, the famous property of strong LP duality. So let me first, there are several versions of this, so let me first, in the first kind of paragraph, define exactly the form I'm going to use, and then I'm going to apply it to this theorem. Okay? So, and this is this abstract theorem. And by the way, one thing I should mention is, let's don't think of the letters in this theorem as corresponding to anything here yet, right? These are just like totally fresh notation. So suppose there is a vector C in Rk, where k is some number. Suppose there is a vector B in RL, L is also some number, and there is matrix A in RL times K. All right? So these are just some objects from linear algebra. Okay? So we're talking about k-dimensional space and L-dimensional space and a matrix k times L, L times K. Now, they're going to be the sort of constraints and the objectives in the linear program. So suppose our linear program, what we're optimizing, the primal, is given by the expression in the first parenthesis. So we're trying to maximize C dot product of C and X, right? X is going to be one of those variables that we're maximizing over. So C transpose X, subject to the constraints on AX less than or equal than B. Okay? So we're maximizing the CX subject to those constraints. And the only additional constraint we're imposing is that those X's are all greater than or equal than 0. Okay? And by the way, just so that to help you, right, we have A times X. So X is going to live in Rk, right? So in order for you to be able to maximize it, to multiply it by this matrix. And we're going to assume that it has a solution, right? Because you can write a linear program that doesn't have a solution. It may not have just a feasible solution, or it may be infinite, but this one is a well-behaved linear program with a solution. Then we can write a dual. Essentially, what we're going to do is we're going to swap variables and constraints. We're going to write its dual as follows. We're going to say, you know what? Instead of maximizing Cx, let's minimize B transpose Y. Okay? Right, so B used to be in the constraints. Now it's in the objective. B transpose Y, subject to A transpose Y. Right, we have to transpose Y because Y lives in the L-dimensional space, greater than or equal to C. So now C used to be in the objective function, but now it's in the constraint. Okay, subject to positive, to all the Y's being 0. So that's called a dual. Okay, and the theorem says, and by the way, if it's the first time you see it, this is a very good thing to look up on. And I think now there are lots of sources on where to learn this, how it works. But basically, if the primal has a solution x star, then the dual is going to also have a solution y star. So it's not going to be poorly behaved. It's going to be well behaved. And moreover, and this is a remarkable result from linear programming, Cx star is going to be equal to B transpose Y star, right? So the values of these optimization problems are the same, right? So variables and constraints in a linear program are sort of interchangeable in this funny way, okay? All right, so that's sort of the part. If it's the first time you see it, just trust me on this one and Chaplin, but go learn. This is like probably the hardest part of the whole thing. Now, once you have that, then we sort of get everything for free, almost. Like it seems like magic. So why do we get it for free? Well, recall what we started with, right? Let's go back to our matching setting. We're trying to maximize our primal LP, maximize sum of alpha ij's, xij, subject to a bunch of conditions. Okay? Well, let's stare at this and map them to what's in that paragraph, right? So let's start with constraints, actually. There it's a little bit simpler. So if you look at all the xij's being positive, well, that's just the same thing as x is being positive in the original formulation. So that's, forget about that. They're all non-negative. Now, we have all those constraints of the form sigma sum of ij's less than or equal than 1 for all I, and sum over I over those things is less than or equal than 1 for all j's, right? So how many of those constraints do we have? Well, we remember that we had m, if you go back to our matching problem in the very beginning, right? We had m agents of type I and n agents of type j. So when we go back here, we have constraint I for all I. Okay, this is bad, but you understand what I say. So we have m constraints of the first type, and then we have n constraints of the second type. Okay, just counting, right? Now, how many variables do we have? We actually, so space x in over there, x is a vector. Here, x is given to us as a matrix, right? It's an assignment matrix. So essentially what you're doing is you're taking this matrix and turning it into one long vector. Okay, you're just treating them all as part of one giant vector of m times n variables. Okay, and you do the same thing for the matrix A of those pairwise values, right? You stack them together in the same way, and then that becomes our primal, right? So vector B is just a vector of m plus n once. Vector C has those alpha ij's from matrix I, and that's that. Okay, so that's our primal. Now we're going to jump to the dual. Okay, now this is where I'm going to lose almost all of you, but at least you know the roadmap, so then you can go on your own and slowly verify that it works. When we flip this, remember that S in this formulation over there, all the B's from the constraints jump into the optimization function. Okay, so and all the B's were equal to 1. Right? So we're going to have just a sum of m plus n variables. Okay? Well, we're going to call the first m of those variables u, and the last n of them v. Right? So the dual is going to be minimize this, right? It's literally just b transpose y. Subject to, again, the non-negative part is the non-negative part is easier. And so what's the last thing? What are the constraints now? So now remember that vector A, so matrix A, from our old setup now becomes this long m times n vector of alphas, right? Alpha 1, 1, alpha 2, 2, then alpha 2, 1, etc. Right? So there's really long vector of alphas. And they used to, and then there were all the x's next to it. And now that thing from the objective, it moves over to the constraints, right? So when you have A transpose Y greater than or equal than C, those become the constraints. So alpha ij goes on the right. And if you look at what's actually in this matrix A transpose, it's going to have ones on precisely the I and the J where that constraint apply, which is the UI and VJ. Okay, and so basically what we get is that the dual almost immediately, it just gives us, we start with this optimization problem, and the dual of this problem, the solution of the dual, just gives us the payoffs of these players. Okay, let's just verify that everything works. So now we're going to say, okay, let's take any solution of the primal LP. Let's take an integer solution. And any solution U star V star of the dual LP. Okay? Then by strong duality, we know that the value of the primal is equal to the value of the dual. Well, the value of the primal is just highest possible sum of alpha ij's, xij's. And the solution of the dual is the sum of all of those ui's and vi's. And so we ended up with a feasible outcome. Okay? So again, and from the constraint and the dual, from those constraints, right, we know it's going to be a stable one, right? So the constraint just give it to us. All right, so this is, I know it's a bit much to ingest if when you're seeing it for the first time, but at least, if you, hopefully the slides will be shared. If you stare at the slides, if you work through it, if you look up linear programming, you will see how this proofs work. And I have good news. I'll show you another proof in a moment that's going to be infinitely simpler than this one, completely elementary. But LP is a very useful tool. You kind of have to know this, right? If you're interested in this area, if you decide that you want to learn more, you kind of need one of those things, because it just shows you how rich this machinery is. And there's a whole discipline of OR that developed a ton of useful tools in this framework. So you want to be able to talk to them. All right. Let me close this set of topics on the stable matchings with one-to-one transfer, the Shepler-Shubik one. Then I'm going to have more stuff, but it's not going to be as hard. And the last thing I want to show you is going to be a lattice structure on the set of stable outcomes. Okay, so Professor DUBEY this morning showed you that there is a lattice structure on the set of matching without transfers. Now I'm saying, oh, it's the same thing with transfers. But the proof here is going to look quite different. So it works as follows. Suppose you have two stable outcomes, u v x1 and u prime v prime x2, and x is potentially yet another optimal assignment. Right? We know x1 has to be optimal. We know x2 has to be optimal. X could be one of them or something else. It doesn't matter. Now, generically, if you just generate those alpha ij's at random, of course, there's going to be only one optimal assignment. But in some specific settings, you may end up with more. All right. So we have two of those stable outcomes. Now let's define ui lower bar for each I as just the min of ui and ui prime, right? So there are two payoffs I get on two different outcomes. I'll just get u lower bar just gives every agent on group P the worst one. Okay? And then all the other variables, u upper bar, v lower bar, v upper bar, are defined analogously. Okay? Theorem, actually, I guess I should have said this as a theorem, u lower bar, v upper bar x, and u upper bar, v lower bar x are feasible stable outcomes. Right? So it looks very similar to what we saw before, but in a very different setting with this whole LP. I'll tell you how they're connected in a few slides, but for now it should be a bit of a mystery, which it was, I understand, in practice for about 10 years, maybe even 20. Okay, so how does the proof work? Well, first it's immediate that all of this UI lower bar, and VJ upper bar, and all this other stuff, they're all non-negative, because all the underlying things were non-negative. So all the mins, maxes, everything is also non-negative. Now the second one, it is also immediate that UVX and U prime V prime X are feasible stable outcome. Okay, why is it immediate? Well, it's because basically the way we define stability, the specific assignment and the payoffs are completely interchangeable, right? Because if there are multiple optimal assignments, they all have to give to generate the same value, and so we can assign it to the players. And stability did not actually talk about that; it just talked about individual payoffs. Okay, so all of that is immediate. We don't need to do work. Now we need to do a little bit, just a tiny bit of work. Observe that, take some I and J who are matched in X, right? Who are actually productively matched. So then we know that both, and from those lemmas I showed you, that both in the original, in the first matching and in the second matching, right? Outcome. I keep calling them matching. I call them outcome. In the first outcome and in the second outcome, UI plus Vj is equal to alpha ij, and also UI prime plus Vj prime are equal to the same alpha ij, right? So in plain English, we know that if I'm matched to someone in the stable matching, then together what we get is the our alpha ij, right? So it has to be true both in UVX1 and U prime V prime. Okay. So, and also from that we get if the lower of the two, so suppose the UI lower bar is UI, right? It has to be one of the two, right? It has to be either UI or UI prime. So if it's UI, then Vj upper bar has to be Vj. And then if UI lower bar is UI prime, then Vj upper bar is Vj prime. Okay? So either way, basically, again, in plain English, this U lower bar and V upper bar come from the same original outcome, right? Because that's why when we combine them, because at first it makes it look weird. When we combine them, we take the worst payoff for one side and the best payoff for the other side. But that's precisely why we do that, right? Because when we look at the sum, it stays the same. Okay, so that's that. And so the last thing we need to prove is that this outcome is stable. And for that, take any I and j. So then UI lower bar has to be either UI or UI prime without loss of generality. Suppose it's the first case. So UI lower bar is UI. Then we just have a very simple expression at the bottom, right? You say, okay, let's look at UI lower bar plus Vj upper bar. And notice this is for any I and j, right? This is not for those who are matched. We're checking stability across all possible i's and j's, right? Then we know that this has to be equal to UI plus Vj upper bar. Well, but that has to be greater than or equal than UI plus just Vj, because Vj upper bar has to be greater than or equal than Vj, which is equal to alpha ij. Okay, so we just proved stability. Okay? All right, so again, if it's the first time you're seeing it, go through this slowly and internalize it. But good news, I'll show you a much simpler proof in a moment, but using very different machinery. But before we do that, and I have about 20 minutes left, right? Yeah. No? Oh. No, we started at 1:10. We started at 110. No, if 10 tell me, but I looked at the schedule beforehand. I'm glad I'm double checking. Okay. Anyway, let's continue, and then I'll speak twice as fast if I have less time left. So, what are the 20? Okay, good. I'm glad I checked. All right. So before proceeding, because that was all kind of very hard to ingest on the first fly. But let me walk you through a few examples that at least will hopefully make it more digestible. Okay. Example number 1. You have only one agent on the first side, right? In P, and there are 4 agents in Q, and so the values of the potential matches are given by the following matrix: 6, 8, 3, and 5. Okay, and then you look at this and you say, okay, so I know right away, without doing any thinking or any calculations, that the match has to be there. You know, there's only one match. There's only one agent on the first side. Has to be with the second agent on Q, right? Because it has to be optimal, and the optimal is 8. Okay, so that's good. So now, what about payoffs? All right, so we know that the sum of payoffs has to be 8. So the agent on side P is going to get something, and the agent on the other side Q is going to get 8 minus that. So what could that be? Well, actually, there is one outcome that turns out to be stable. Suppose the agent on the first side gets 0. The agent on the first side gets 8, and the agent on the other side gets 0. Okay, that's a stable outcome, right? Because there is no one else for the agent on side 2 to try to match with. Okay, so the agent on side P can be very, very greedy under the stability notion. Now, does it work in the other direction? Could it be what I initially misspoke? Could it be that the agent on side P gets 0 and the entire 8 goes to the agent on side 2? And the answer is no, because that would not be stable, because then this agent on side P would be able to rematch with, for example, the first agent on side Q, and they would together generate 6. Okay? And therefore, the set of stable matchings is, the stable outcomes is, the agent on side P gets matched to agent 2 on side Q, and he can get anything from he can get, one sec. Yeah, he can get anything between 2 and 8, right? The most that agent on the other side can get is 6. Sorry. Sorry, I confused myself. Okay, so the lowest price that the agent on side 1 can get is 6, right? So the agent on the first side gets price 6 or above, and agent on the Q side can get the surplus of at most 2. Make sense? All right, perfect. Good. All right, so now let me give you 2 other examples that sort of illustrate both how this model works and also how good it is to be on the short side of the market. That's a general economic lesson. No different from standard Econ 1. So suppose you have 10 agents on side P and 10 agents on side Q. And the value of each possible match is 1. Okay? So what happens in this setting? Well, the first observation is that as long as they're all matched, it doesn't matter how they're matched, right? They have a production value of 10 no matter how they're matched. Now, and they're going to generate the total value of 10. And, each match is going to get 1. Now, what about the prices? And your first intuition may be, oh, like, prices can be anything. But that's not quite right. Because prices here have to be the same for each pair, right? So there's going to be one price in this market, right? There's going to be the price that all P side agent get that price, and all the Q side agents get 10 minus that, right? Because if two pairs trade at different prices, then the relative losers in both of those two pairs could profitably rematch. Okay? So it's like we have this like very, I don't know, long core, I would say, right? So it's kind of thin. There's just one price and that goes together for everyone. Now, what happens if we just add just one agent on one side? Suppose we add one agent on side Q. And now the whole thing collapses. Why? Well, now we know there's going to be at least one unmatched agent on side Q who gets 0. So they all have to be getting 0. So basically what's going to happen is all the matches are possible. And they're all going to give the same value. And the payoff is the agent on the short side of the market get the entire payoff, the entire pie. Make sense? All right. Yes. Say it again. Yes. Oh no! It's because we're solving the assignment problem, so they will all be integers. Now in the LP solution, there's going to be a whole bunch of others, but we're not going to look at them. We're gonna take all the LP solutions. There's going to be a bunch of fractional ones, but we're going to discard them. We're only going to look at integer ones. All right. So as I promised, if those of you who are seeing this LP stuff for the first time, it's tough going. So I'm going to give you an alternative proof that showed up like a decade later, and that not only gave them, direct proof of this result without all this LP machinery, which again, it's very useful. That's why I'm teaching it to you. But also explained why these parallels, stability with two-sided markets, but not with one-sided, core lattice properties, lattice properties of the core, like it's not a coincidence. It's actually a very intrinsic feature. And that's from a paper by Crawford and Knorr, 1981, that shows that the similarities are not accidental. It's one of my favorite papers in this literature. So here's how it works. We still have P and Q. P are firms, Q are workers. And now in the primitive, right? This is in the setting. We're going to assume that if they just match and no money changes hands, then worker I is going to get utility, firm I is going to get utility Uij from this match, and worker J is going to get value Vji from that match. Okay? So just some numbers. And I didn't tell you anything else yet. But notice how this model can incorporate both of the settings we discussed before, right? So if there are no transfers, right? Suppose, take this model, so there are no transfers allowed. Then we just say, oh yeah, like these U's and V's just determine the orders of preference for men and women in this market. Okay, suppose they're all different. On the other hand, if we think of the Shapley-Shubik model, then we just say, oh, like this Uij, the individual Uijs don't matter. The only thing that matters is the sum, right? Uij plus Vji, that's the alpha from before. In principle, they could even be negative. It's easier if they're non-negative, but they could even be negative, right? So if they're negative, then you need to start thinking. So they could be negative. Here's why. Actually, it's important to allow them to be negative. There are lots of people who work only because they get paid, right? Like, it doesn't apply to everyone in this room, but there are definitely some people who would just stay at home if they didn't get paid, and that would mean that their Vji is negative. But the value of the firm gets over. Yeah, so I wouldn't want to assume that. All right, but here is the key idea of Crawford and Knorr. They say, look, we're going to look at the settings where we can have transfers, just like before, but they're not going to be a continuous set of transfers. It's just going to be some finite set of possible salaries. Okay? There is just a set of possible salaries, and a match will now describe I, J, who gets matched, just like in Gale-Shapley, plus we're going to append the salary that the firm pays to the worker. Okay? So that's a match. And then, the definition of stability is going to be very similar to Gale-Shapley before, where they say, oh, if there is a firm and a worker who can find a salary at which they're both better off than under the old arrangement, that's going to be a block. Okay? Now, I'm going to show you the main result for the finite set of salaries. And I'll also assume that there are no indifferences. So for under all salaries, there are all the strict preferences. But if you then take this unit of discretization of this of these salaries to zero, right? You do them in dollars, then in cents, and in microcents. Then you just convert to Shapley-Shubik, right? And you get an alternative proof of the stuff I just showed you before. All right. So how can we? This looks complicated. This looks more complicated than Gale-Shapley. It looks definitely looks more complicated than Shapley-Shubik. It turns out it's not. And it turns out that, remarkably, essentially the same Gale-Shapley mechanism continues to work with just one modification. Here they call it a salary adjustment process, and it works as follows. So the round one, firms say, okay, here are all the workers I can hire and all the potential salaries I can offer. Okay, well, I'm going to find the most profitable combination for me, selfishly. Just like in the Gale-Shapley, each man says, oh, like, what's the best woman to make an offer to? Here's like, what's the best combination of worker and salary? And the firm is going to send that offer to the worker. And each firm does that. Okay? So now all the workers have offers. Well, not all the, some workers have offers. Those who have only one or none do nothing. They just hold on to their offers. Those who have multiple offers say, oh, that's great. Let me reject all the ones that are not the best one and keep just the best one. Just like in Gale-Shapley. So that now they evaluate not just the identity of the firm, but also the monetary offer attached to it. And then the rejected firms, once they get rejected, they say, oh, now I can no longer make an offer to that worker at that salary, right? So that's where the difference with Gale-Shapley comes. It's the only place where it's different. It says, oh, I can go back to the same worker at a slightly higher salary, or I can go to a different worker, right? Whichever is the best one from the remaining set of options. And then everything is the same, rinse and repeat. Then everything works in exactly the same way as in Gale-Shapley, and all the proofs work exactly the same, right? It has to stop because you have a monotonic process on each side. There cannot be a block because if there were a block, it would have been encountered along the way in the salary adjustment process and was rejected, and so the worker is not even better off than before. Okay, so this is a really, a short and concise proof. And of course, as I said, if you take the unit of discretization to zero, you converge to the Shapley-Shubik world. Okay, the last thing I want to show you, this is a further generalization, and this is where, in the remaining 7 minutes, I'll go back and use that, Professor Sotomayor's trick about simple matchings in this much more fancy setting. So the setting is from Hatfield and Milgram, 2005. It encompasses Kelso-Crawford, it encompasses some work by L. There are going to be two differences here. The first one is, instead of thinking about salaries, we can think about contracts more generally. Right? So in the real world, contract can be very multidimensional. Which position you're doing, how many hours, geographically, all kinds of stuff, anything you can imagine, not just money. Now we're going to assume there's a finite set of those possibilities, finite set of contracts. The other thing we're going to change is that we will now allow each firm to be matched to multiple workers. Okay, there's going to be a condition we need to impose, but beyond that, that's this. So other than that, everything is the same as before. There are firms, contracts. Just for notational convenience, the contract also specifies who is the worker and the firm involved in it. Okay, so the contract says, this is the firm, this is the worker, these are the terms. And stability is just as before. The definition of stability is just as before. If a worker would prefer to match with some firm under certain contractual terms, and the firm would also want to do that, and under the option they could drop someone else, they're allowed to do that. That would be a block. All right. So, okay. So I need one more definition, and then I'll be able to prove it, and then I'll be right on time. We need the definition of substitutability. We're going to say, for that definition, we need the notion of a rejected set. So here is a definition. Suppose you're a firm, and I come to you with a set of contracts. And I said, just choose your most preferred set. And of course, like each worker will be chosen only once, because you only can hire a worker in one term. But there may be multiple workers with multiple positions, multiple contractual terms. Okay? That's going to be your choice set. Now, a rejected set is everything else, right? It's just literally the complement of the choice set, right? That's bullet point number 2. Okay, so here's the definition in a very compact form, and then I'm going to translate it into English. We say that firms' preferences are substitutable if for any firm and any sets of contracts X double prime, that's a subset of X, that's a subset of the entire set of contracts. If X double prime is a subset of X prime, then the rejection sets contain the same relationship. Now, in plain English, this is impossible to process. So in plain English, what it means is, suppose I come to you and say, here are 17 workers, and here are the contracts under which you can hire those workers. What's your optimal set? And you choose 6 of them. And now I come to you and say, oh, I forgot, here are 2 more workers. Good news, here are 2 more options. That new piece of information can only make you more selective, right? You may end up dropping some of those 6 workers in favor of these new ones, but you can't say that, oh, now that I have these 2 workers, I also want to hire this 11th one who I didn't want to hire before, right? So for example, like there may be some operations where in order to produce a widget, you need an expert of type A and an expert in type B. Like those would be complements, and that would violate this assumption. Okay, and so we need this assumption. And matching is pairwise stable, as I said, if it's not blocked by any firm worker pair. All right, so here is the theorem, and it's the last theorem I will show you. And the theorem is there exists a pairwise stable matching. And here is the cool proof. Here is why I gave you this warm-up exercise in the very beginning, telling you about SOTOMAYOR 1996, because the proof in Hatfield and Milgram is very long. You need to know lattice theory. There is like many, many steps. Instead, you can do it in one paragraph. So here's how it works. We're going to say that a matching in this setting, again, this fancy matching with contracts and many-to-one matching, blah, 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 everything you want. We're going to say that it's simple if the only blocks that happen in this market are by unemployed workers. Okay? That's the definition of a simple matching. Take a simple matching that is Pareto optimal for the firm side, right? And just like before, we know it has to exist because everything here is finite. Empty matching is simple. So there is going to be at least one matching that is cannot be Pareto improved by the firm side when you're staying in the space of simple matchings. Okay? Claim, just like in that beautiful paper, this matching has to be stable, and the proof is almost exactly the same, right? Suppose this matching mu is not stable, and suppose it must have a block involving some unemployed worker W. Now there may be multiple blocks involving this W, so pick the one that he likes the most. Okay, so let's form that match. Now on the firm side, they may now reoptimize and drop some of the earlier workers, but after they do that, the firm is better off. It's an improvement. All the other firms are equally well off as before, and the matching is still simple. And that's the last theorem, and that's the last result I wanted to show you. The only thing I will leave you with, just so that you don't think everything is so obvious, homework exercise, figure out where in this proof I used the substitutability assumption. Because we know that if they're not substitutes, it's not going to work. So I used it somewhere. I know where I used it, but it's homework exercise for you to figure it out. All right, so here is my concluding slide on matching with transfers. So in a sense, between Professor DUBEY and myself today, we taught you a bunch of technical machinery for this setting. So there is deferred acceptance algorithm and the salary adjustment process. And by the way, there are more algorithms in this family. There's like a cumulative offer mechanism, which works in a similar fashion. Then a very different approach of linear programming, which is much harder, but it's, a very powerful one. Then we have this non-constructive approach via simple matchings. And then the one I didn't cover, but I just want to flag if you're interested, there is this lattice theoretic approach under which the stable matchings are defined as fixed points of an isotone operator in a properly defined space. So Hatfield-Milgram, use that. If you're curious, I have a paper on that that goes even beyond two-sided matching with this fixed point machinery, but that's it. Thank you.
Okay, so our next talk is by Marilda Sotomayor. And, at many meetings, you hear someone introduced by saying this person needs no introduction. But that's especially true at this conference, where many of us have come to help celebrate Marilda's career. Let me just say one thing about Marilda, which is that she and I have known each other for a long time. And in 1990, we wrote a book that I think helped make a matching of the kind you've just heard about from Mike Ostrovsky. We wrote a book that helped make it part of mainstream economics, which it wasn't always so.
Eu preciso desse negócio aqui. Ah, ele está aí funcionando. Para que isso? Não. Tem esse ha-ha-ha aqui. Agora me diga onde é que eu vou para... Ah, é aqui?
Clicar nessa.
Ih, mas ele é muito rápido esse treco aqui. Well, I will talk about this paper. It was already published, but I think it was not very well understood. It is about the continuous two-sided matching market. Here are the references I used to write it. The study of the continuous two-sided matching markets has been of great importance to economists and game theorists since Chaplin Schubach, due to its applications to the organization of real markets, and because these models provide interesting examples of the use of the game theoretical tools. The main feature of these markets is that they are endowed with a cooperative game structure and a competitive market game structure. The relationship between these two structures is of economic interest in the extent that it contributes to a better understanding of the fundamental similarities and differences between the cooperative and the competitive treatments of the same market. Traditionally, a continuous matching market is modeled as a static market, a one-stage game where the players are present all together and interact coalitionally. It happens that many markets change along the time. There are entrances and exits of agents which modify its cooperative game and competitive market game structures. The aim of this work is to contribute to a better understanding of how such markets operate as population grows up. For this purpose, we introduce a general framework that fits well for the class of multi-stage continuous two-sided matching markets. Each stage configures a subgame where new participants are added, while the agents that are present in the previous stage are maintained. Therefore, the whole set of players is only formed at the final stage. The set of the new agents is formed with one agent of each type of the agent belonging to the original market. It is as if the original market M was replicated in each period of time. Therefore, we obtain the sequence S of M, generated by the replications of M. The terms of the sequence are called the extended markets. M1 is the market M. It is called simple market. It is the sequential game with one player of each type. MH is the HS extended market. It is obtained by replicating H times the simple market M. So it has H copies of each agent. M infinity is the asymptotically extended market. It is the infinity union of all terms of the sequence, so it has infinitely many copies of each agent. Each copy of an agent maintains the same characteristics of this agent. The main advantage of regarding an extended market as a sequential game is that instead of an equilibrium analysis only supported on its structure of a static game, we can obtain a more precise and rigorous equilibrium analysis by also taking into account its structure of a multi-stage game. In each subgame, the new entrants can interact with the current players. By assuming that the agents behave optimally, the agreements that take place in a given stage may be undone in a subsequent stage. Then, in a given subgame, the optimal behavior of an agent may change in the subsequent subgames. The optimal behavior means that a coalitional agreement is signed if each agent of the coalition is sure that more favorable terms cannot be obtained in any future negotiation without breaking the rules of the game. Here, for example, in this situation, we have an allocation in the market M. The agents, by assuming that they are behaving optimally, we have cooperative equilibrium. At the second stage, these copies of Q1, Q2, Q3 enter the market. Then they can interact with the agents of M. And now it is optimal for Q3 to break his partnership with these two agents and to work together with these two agents. And it is also optimal for the first copy of Q2 to work together with the second copy of himself. Then we are assuming that the agents are behaving optimally. This is a cooperative equilibrium. But we did not use the multi-stage structure of the market M2. This allocation captures the traditional idea of equilibrium for the extended market M2 regarded as a static game. We can imagine that it is yielded in an environment where all agents are present all together and under the presumption of optimal behavior, they freely interact with each other respecting the rules of the game. However, this concept of equilibrium is unsatisfactory for any extended market regarded as a multi-stage sequential game, since it ignores the sequential structure of the decisions taken in each subgame. The alternative concept is the concept we call sequential stability, which emerges distinct and stronger than the respective traditional stability concept. Sequential stability captures the intuitive idea of equilibrium for an extended market regarded as a multi-stage sequential game. By assuming that the agents behave optimally, the coalitional interactions that take place in any of its subgames are preserved in the subsequent games. This idea is analogous to that used to define a subgame perfect equilibrium of a non-cooperative dynamic game. Therefore, the restriction of a sequential stable allocation to any subgame is well defined. Formally, an allocation is sequentially stable for a finite term MH of the sequence S of M if it is stable and its restriction to any previous term if n is stable. It is sequentially stable for the asymptotically extended market infinite if its restriction to any extended market is stable. The concept that captures the idea of competitive equilibrium for an extended market regarded as a sequential game is the perfect competitive equilibrium concept. The perfect competitive equilibrium allocations for an extended market are the competitive equilibrium allocations whose restriction to each of its subgames is a competitive equilibrium allocation. Then the question is, what can we say about the relationship between cooperation and competition under the static and sequential approaches? This question is answered here for the sequence of extended markets generated by the multiple partners assignment game introduced in this paper. There are two finite and disjoint sets of players, which we may think of a set of buyers and a set of sellers. A player of a set may form more than one partnership with different players of the other set. Every agent has a quota representing the maximum number of partners he or she can have. Each seller QJ has a finite set of S of QJ identical indivisible goods to sell and cannot sell more than one item to the same buyer. Each buyer PI is allowed to acquire R of PI objects from distinct sellers. No buyer is allowed to buy more than one object from the same seller. For each pair PI QJ, there is a non-negative number, AIJ, representing the gain from trade between PI and QJ, the amount of income they can get if they work together. The transactions are accomplished pairwisely and independently, and utility is identified with money. Independency means that the trade between two agents who are partners is not affected by any other trade in which these agents may be involved, When the quota of every agent is 1, we have the assignment game of Shapley and Schubert. When a buyer is allowed to acquire more than one object from the same seller, we obtain a special case of the general quota matching model introduced in this working paper. In this model, the quota of a player is any real number. Maybe it is the maximum number of units of labor time it can distribute among the partnerships it forms. An allocation UWX specifies a matching X, which is a set of partnerships that respects the quotas of the players, and a payoff allocation UW, an array of individual payoffs for each player, resulting from the division among the partners of the gain from trade within each partnership formed. Then, if, for example, PJ and QK become partners at the matching X, then the sum of this individual payoff of PJ and this individual payoff of QK is equal to AJK. And all the individual payoffs are non-negative numbers. Facing two arrays of individual payoffs, an agent prefers the one which gives to him the highest total payoff because utility is identified with money. The key notion in any matching model is the notion of stability, which captures the intuitive idea of a cooperative equilibrium. In this model, stability is equivalent to pairwise stability. This means that the allocation UWX is pairwise stable if it is feasible, and for all pairs PI, QJ, PJ, QK not matched to each other, the sum of any individual payoff of PJ with any individual payoff of QK is not less than AJK. In this situation here, this allocation is not pairwise stable because there is a blocking pair here. No, 2 plus 0 is less than 3. The gain from trade if P1 and Q2 work together. No. If they break their present partnership, then make and work together, they can split 3 among them instead of 2. Well, the other important notion is that of competitive equilibrium introduced in this paper. The allocation UWX is a competitive equilibrium allocation if it is feasible and each buyer is assigned to a bundle of objects of his demand set at prices W. No, the demand set of the agent at prices W is an allowable set of items that at the given prices might maximize his total payoff. Here, this allocation is not a competitive equilibrium because the P1 demands Q2, and he is assigned to Q1. We have here some results already proved. We state them here because they are used in the remaining part of the stock. Stable allocations always exist, and are in the core. But not all core allocations are stable. This model was the first matching model that appeared in the literature where the core it is not equal to the set of stable allocations. It is bigger, maybe bigger. Competitive equilibrium allocations always exist and are stable, but not all stable allocations are competitive. An allocation, this is characterization of the competitive equilibrium allocations. An allocation is a competitive equilibrium if and only if it is stable and non-discriminatory for the buyers. No buyer discriminates, no seller discriminates the buyers. Each seller sells all his items for the same price. When the allocation doesn't discriminate the sellers and the buyers, we say that it is non-discriminatory. And non-discriminatory stable allocations not always exist. This was proved in the present paper. It is immediate that every perfect competitive equilibrium allocation is sequentially stable and competitive. And every sequentially stable allocation is stable by definition. Nevertheless, not all competitive equilibrium allocations are perfect, and not all stable allocations are sequentially stable. And not all sequentially stable allocations are perfect competitive equilibrium allocations. There are examples illustrating these sequences of relations in the text. In general terms, the main contribution of this paper is the identification of a subsequence of extended market L of M, which has the following properties. In all terms of L of M, the cooperative and the competitive equilibrium concepts under the static approach are equivalent to the concept of non-discriminatory stable allocations. If the set of sequentially stable allocations of some term of L of M is non-empty, then it is non-empty in all terms of L of M. And the cooperative and competitive equilibrium concepts under the sequential approach are equivalent in all terms of L of M. Okay. This means that in all terms of L of M, the agents behave cooperatively and competitively in the static and in the sequential equilibria as in the large markets. The novelty is that the sequence, the subsequence L of M is the sequence where the first term of it is MH capital H plus 1, and this capital H is the maximum quota of the agents. Then, if every agent has a quota of 2, the first term of this sequence will be M3, which is finite. And it is not necessarily a large market, but the agents are behaving as in the large markets. Then formally we have the first equivalence theorem. The sequence S of M is structurally stable with respect to the equivalence between the stability, the competitive equilibrium, and the non-discriminatory stability concepts, and any finite extended market in L of M is a stable point of S of M. Now, in mathematics, we say that a sequence is structurally stable with respect to some property or to some proposition if there is a finite term of the sequence where this property or this proposition is true and it persists in all the subsequent terms. And these finite terms in all subsequent terms are called the stable point of the sequence. The second equivalence theorem asserts that Suppose the set of sequentially stable locations is non-empty, it may be empty, for some extended marking L of M. Then, any finite term in the sequence L of M is a stable point of S of M with respect to the property. The set of sequentially stable location is non-empty and coincides with the set of perfect competitive equilibrium allocations. Theorem 2 means that any cooperative equilibrium allocation yielded in any extended market of the subsequence L of M, when the agents adopt a cooperative optimal behavior in every subgame, also occurs in a different scenery, with reference to the prices where the agents behave as price takers in every subgame and vice versa. This is not necessarily true for the other extended markets. To fix ideas, consider the structure of any extended market in this sequence. Here it is the set of stable allocations, which contains the set of competitive equilibrium allocations. Now, this set relation may be strict. Here, the set of non-discriminatory stable allocations. Competitive equilibrium allocations contains the set of stable and non-discriminatory allocations, but this set relation may be strict. This set of sequentially stable allocations is a subset of the set of stable allocations by definition. And the intersection of the set of sequentially stable allocations and the competitive allocations is this set here, the set of perfect competitive equilibrium allocations. Then the perfect competitive equilibrium allocation is the intersection of this set and this set. Now, if MH belongs to the subsequence L of M, what is the difference in the structure? These three sets coincide. This is theorem 1. Also, these two sets coincide. This is theorem 2. And this theorem 1 can be proved by using theorem 1 and this set in these relations very easily. The set of perfect competitive equilibrium allocations is the intersection of this set with this set. But the set of competitive equilibrium allocations, since the market is in L of M, theorem 1 asserts that this set is equal to the set of stable allocations. Then the intersection of the set of stable allocations with its subset, its set of sequentially stable allocations, is the set of the sequentially stable allocations. Okay, then we have proven theorem 2. The results of DUBEY and SCARF for exchange economies and the result of AUMANN for pure exchange economies with a continuum of agents imply that as the number of agents increases, the core shrinks to the set of competitive equilibria. Okay, this is not always true for the markets treated here. What we have is that not the core, but the set of equilibrium, cooperative equilibrium, shrinks to the set of competitive equilibrium, but coincides at some finite term of this sequence. Let us see this example. Every agent has a quota of 2. Here we have an allocation sigma, which is stable for the market M. There is no blocking pair we can verify. But this allocation is discriminatory. No? Then, if sigma star is the extension of sigma to M3, sigma star is discriminatory, because sigma is discriminatory. So by theorem 1, sigma star is not stable, no? Because M3 is in L of M. Every stable location for the term of L of M is non-discriminatory. And so if it is not stable, it is not competitive, because every competitive equilibrium location is stable. Then it is a matter of verification that sigma star doesn't have any blocking coalition. Then it is in the core of this market. Okay, you can see also directly here at the second replication of this allocation sigma, we get a blocking pair. 1 plus 0 is 1, which is less than 2. Well, then we have a stable allocation, which we extend it to any extended market, and the extension is not stable in any extended market. Okay? Well, but this stable location is not competitive. No? You can see that it is not competitive because competitive equilibrium locations are characterized by being stable and non-discriminatory for the sellers, and the sellers discriminate the buyers. The seller sells his object, two identical objects by different prices. Well, the extension of a competitive equilibrium location of M to an extended market is not necessarily competitive for this market. We can have this in this situation. We have here a market where we have P1, Q1, and Q2, the agents. These agents are replicated. And this allocation is stable. There is no blocking pair. And it is non-discriminatory. The Q1 and Q2 have only one object. And then it is a competitive equilibrium. But when we extend it to the second extension, to the second state, the second subgame, we get a blocking pair. No? 2 plus 0 is less than 3. Then there is a blocking pair here. Moreover, we learned with these examples that if you have a stable location, we extend, we not always we get a stable allocation in the extension. If you have a competitive equilibrium location, the same thing. And moreover, not all stable allocations of an extended market are extensions of a feasible allocation of M. Even in the case in which the extended market is in L of M. Now, see the following situation. We have only one buyer, 2 sellers. Here is the dummy agent, the dummy seller. And consider the allocation sigma infinite, which matches every copy of P1 with 2 copies of Q1. Okay? It extends to infinity, to the market, asymptotically extended market. Then it leaves all copies of Q2 unmatched. This is this allocation. We can see that this allocation doesn't have any blocking pair. It is non-discriminatory. Then it is non-discriminatory and stable in M infinity, which is an element of the subsequence L of M. This allocation is stable non-discriminatory for M infinity, but it is not the extension of any feasible allocation of M. Okay? Why? Its restriction to M is not well defined. There is no way for P1 to get the total payoff of 6. The maximum he can get is 5 if he works together with Q1 and Q2. Okay? Then this allocation, even the payoff allocation, no, this is not well defined. It is not feasible. However, this payoff, the payoff of sigma of this allocation, sigma infinite, is the extension of this payoff, which gives 3, 3 to P1, 0 to Q0, 0 to Q1, and 0 to Q2. Okay? You can see that it is the extension of this, but this is not a feasible payoff. Then the questions are, what are the stable locations of M, which is succeeding extending to stable allocations? And what are the competitive equilibrium allocations of M, which succeeding extending to competitive equilibrium allocations? And what are the stable allocations of an extended market that result from the replications of the stable allocations of M? Then we have Theorem 3, which characterizes the successful feasible allocations of M. It asserts that let MH be an extended market of S of M. Let sigma x be a feasible allocation of M. Okay? Sigma x is a feasible allocation of M. And the market is any extended market. Then the extension of sigma x to MH is stable and non-discriminatory if and only if sigma is stable, but stability doesn't guarantee that the extension will be stable, as we saw in our examples. The crucial condition is that non-discriminatoriety. Then, if and only if sigma x is a stable and non-discriminatory allocation, we need this condition. Okay, it is a stable non-discriminatory allocation, which we know that not always exists. Well, it is easy to see this also, no? Only this part that the non-trivial part is to show that if it is stable, we need this condition in order to get stability for its extension. Consequently, if sigma x is competitive, but it discriminates the sellers, as in example 2, then its extension is not competitive because it is not non-discriminatory. Then we may have a competitive equilibrium allocations where its extension is not competitive, no? Unlike the results of DUBEY and Scarf. Then its extension is not competitive for any extended market. On the other hand, we may have competitive equilibrium allocations for an extended market that are not extensions of any competitive equilibrium allocation of M, as in example 2. In this example, the allocation, sigma infinity, is stable, non-discriminatory for this market. So it is competitive. However, it is not the extension of any feasible allocation of M. Instead, its payoff allocation is the extension of a non-discriminatory but unfeasible payoff of M. The payoff sigma infinity is the extension of this payoff, which is not feasible for M. Well, lemma 1 shows that this phenomenon is not an accident. This lemma asserts the following. Let MH be any extended market, any. Let sigma star be a non-discriminatory stable payoff, not allocation, payoff of MH. Then sigma star has the equal treatment property, which means that every copy of an agent has the same array of individual payoffs. Okay? Then, if the allocation is stable and non-discriminatory, as it happens in the sequence L of M, the allocation has the ETP, and since it has the ETP and is non-discriminatory, it will be the extension of some allocation. Some payoff allocation. Then, if a payoff for an extended market is non-discriminatory and it has the equal treatment property, then it is the extension of a non-discriminatory payoff, which is not necessarily feasible for M. Therefore, every stable payoff for an extended market of L of M, which are the sequence where every stable allocation is non-discriminatory. Then every stable allocation for an extended market of L of M results from the replications of some payoff, not necessarily feasible for M. If the payoff of M is unfeasible, then its extension may be stable, but it is not sequentially stable. That is, the sequentially stable payoffs of an extended market of the subsequence L of M result from the extensions of the non-discriminatory stable payoffs of the market M, and are the only stable payoffs with this property. Then we have the characterization of the sequentially stable payoffs of the terms of L of M. Let sigma star be a feasible payoff for the extended market M star in L of M. Then sigma star is a sequentially stable payoff if and only if sigma star is the extension of some stable and non-discriminatory payoff of M. We are telling that if sigma star is sequentially stable in L of M, then it will be the extension of some sigma, okay, which is a stable non-discriminatory payoff of M. It is easy to understand too, because if it is sequentially, this allocation is sequentially stable, then its restriction to any subgame is well defined. And it must be stable by definition. Then sigma is stable for the market M. On the other hand, this allocation, if it is sequentially stable, it is stable. Since the market is in L of M, theorem 1 says that this allocation is non-discriminatory. Then it is stable and non-discriminatory. Then sigma is non-discriminatory too. It's stable and non-discriminatory. On the other hand, sigma star is stable and non-discriminatory. We can use lemma 1, which asserts that it has the equal treatment property. Has the equal treatment property and it is non-discriminatory, then its restriction to every subgame is the same payoff. It must be sigma, 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 sigma. Okay? Then we have an extension of the payoff, not an extension of the allocation. We cannot say that this allocation is the extension of sigma x. The payoff allocation is the extension of sigma, but of course we may have distinct matchings in distinct subgames. No, the condition for sequential stability is only that its restriction to every subgame is stable, and it is feasible and stable. And we may have a sigma compatible with this matching. Here, sigma is compatible with this matching, okay? And we don't need to have the same matching. Then we cannot say that the allocation is the extension of this allocation. Well, the set of sequentially stable payoffs of an extended marketing L of M is empty if and only if the set of non-discriminatory stable payoffs of M is empty. Then for the market M, in which the set of non-discriminatory stable payoffs is empty, no competitive equilibrium payoff of M extends to a competitive equilibrium payoff for an extended marketing L of M, contrary to the results of DUBEY and Scarf. Well, let's see how many. I finished my time? No, I think there is 5 minutes. Okay. The model where the buyers are allowed to purchase more than one object from the same seller was studied I studied this model in the working paper, this working paper. There I proved that the stability concept for this model is not equivalent to pairwise stability concept. And pairwise stable allocations are stable, but we may have stable allocations which are not pairwise stable. And always exist, then we always have the existence of stable allocations. The competitive equilibrium allocations coincides with the set of pairwise stable non-discriminatory allocations and always exist. Then competitive equilibrium allocations are non-discriminatory stable allocations. It is stable because it is pairwise stable. The competitive equilibrium allocations the set coincides with the set of pairwise stable and non-discriminatory allocations, and always exist. Then the set of sequentially stable allocations for this model and the set of perfect competitive equilibrium allocations are always non-empty, unlike the multiple partners assignment game. Well, I proved the 4 theorems. The 4 theorems proved for the equivalence theorems and convergence for the multiple partners model is true here, but with a different definition of the term of this capital H. No, this term here, MH plus 1, is the term of the sequence where H is not the largest quota of reagents. It is the double of the largest quota of the N, but it is a small number in any case. And stable locations are competitive, and sequential stable locations are perfect. Then we have theorem 1 and theorem 2 here. No? Every competitive equilibrium location of M extends to a competitive equilibrium location of any extended market, as in the model of Debreu and Scaffi, and the multiple partners model. However, the set of competitive equilibrium locations may be a proper subset of the core, as in the model we studied before, in every extended market. We hope that in the future, the study of the extended markets as sequential games, obtained by the method of replication, be recognized as an indispensable piece for the advancement of the theory of matching markets. Although this is not the correct method to model perfect competition, the replication of an economy has been a useful tool in game theory applications for the investigation of the connections between cooperation and competition in large markets, as it allows the population to go to the limit in a countable way. This way, we can address the relationship between solutions of finite extended markets and solutions of the limit problem. Well, I finish here, and I will not answer questions. I prefer to talk to each one. If you have a question to me, you want to talk to me about that, I am available outside. Okay? Como é que tira? Quero tirar o pendrive. Vê se eu desliguei lá direito. Não perco.
almost done one down, but they're in line to kind of finish.
Okay.
But I think we could start.
And let people chip in.
I don't know. What would you prefer?
I mean, the question is, I mean, we are now 25 minutes late.
Yeah,
So the
yeah.
next, I mean,
on YouTube. By remaining in this venue, participants acknowledge and agree to the capture and use of their image and voice in the broadcast and recording of this event. So we are happy to start the mini course by Professor Bernhard von Stengel. Professor, please.
so thanks for joining me here in this late afternoon. It's a long day. So here is an overview of what I want to talk about in these almost 5 hours that I have over the 4 sessions. And it essentially, I mean, studying 2-player games. The ultimate goal is an algorithmic problem. What are the equilibria of this game? But a lot is about the structure of these equilibria and insights about the structure. And it is actually part of in a book that you will see the cover of shortly. And it is what I think every game theorist should know, which is the general motto of this book. And it will be in many cases familiar to you, but it has algorithmic implications. So we talk about best responses and Nash equilibrium. I want to start with zero-sum games and present you a beautiful proof by Loomis about the minimax theorem in about 5 to 10 minutes, which actually has been independently reproduced at least 3 times. But the main story is the geometry of Nash equilibria. In particular, this Lemke-Hausen algorithm, which proves that in a generic game, the number of equilibria is odd. I will show that the whole thing is essentially a study of polytopes, like cubes, for example, pyramids, and an algorithmic part which is called complementary pivoting, also about the possibility of finding all equilibria, and the concept of an equilibrium index in the context also of a complexity class called polynomial parity argument with direction, very related. And if we have time later on in the course, talk about an advanced use of these best response polytopes. In fact, my scientific talk, I think it's tomorrow, will be about new results on maximal numbers of Nash equilibria in bimatrix games, and possibly in the course exponentially long Lemke-Hausen paths via certain polytopes. So we start, I will start easily. So we start with zero-sum games. Here is a zero-sum game with two players, two strategies, top and bottom, left and right. We have here the payoffs to the row player in red, 1, 0, -2, and 2. And you see the best response, which I put in a box for the row player against the left column is obviously top, and against the right column it's 2. Whereas the minimum, which is what the column player does in blue with the circle indicated, is right against top and bottom, I mean left against bottom, so we don't have a pure equilibrium here. And so the blue thing, I mean the blue player considers these numbers as costs. Now, because of the circular structure, we need to find a mixed equilibrium, and here is a trick that you may or may not know how to find it. We play the columns with probabilities 2/3 and 2/5 and 3/5. And why is that? Because the difference in the first column is 3 between the numbers. In the second column, it's 2. And you just write the numbers on the opposite columns, 2 and 3, and normalize. Let's do the same thing for the rows. The difference in the first row is 1, and the difference in the bottom row is 4. We write the 4 at the top, the 1 at the bottom, and then we put normalize, and then we get that the value of this game is 2 over 5, as you can readily verify. So this is the difference trick, which tells you in a second how to solve a 2x2 game, or in fact, whenever you look at 2x2 submatrices. So that's one of the things you should take home once you solve games. Now, we have to assume that when we look at these numbers, that we can take expected values and that they represent preferences about these values. And that's why I think the penalty kick in soccer or football in England is a prime example for this, because it's clearly a strategy where you don't have a pure equilibrium. And I think a cat is a very good animal to jump into a corner to catch a ball. I had this drawn especially for my book cover, and I think it's a perfect example, because what you're looking at is the expected probability of scoring when you're the striker, which you try to maximize, and the goalie tries to minimize it, and an expected probability is still a probability. So it's the perfect example for not having to worry about whether utilities are actually fulfilled here as expected utilities. So let's look at a specific example. Say the striker has two possibilities, kicking left or right. The goalie can jump left, right, or wait. And these are fictitious, say, probabilities. Obviously, if you jump into the wrong corner, like jumping left column, and the goalie kicking right, that's give you here 1.0, I mean, a certain chance of scoring as long as you hit the goal, which not always happens, as you know. Similarly here, and when you wait, the probability of catching the ball is actually lower. The scoring probability is higher, but it's sometimes possibly, I mean, let's assume that these are the probabilities between 40, 50, and 100%. Now, how do we solve this? The way I propose is what I would call the goalpost method, particularly suitable in the case of soccer. So we have two goalposts where we look at the probability of right is the right goalpost, the probability of left is the left goalpost, and then we look at the expected probability of scoring depending on the strategies of the opponent. So for instance, when it's left, when the goalie jumps left and I kick left, it's 50%, it goes linearly up to 1.0 along this line here. For W, for waiting, it goes down from 0.7 to 0.6. And for right, down from 1.0 to 0.4. And you have to assume that the goalie will do what they do as the best response, which is the lower value of these, because the goalie tries to minimize this probability. So we get the lower envelope of these payoffs. And the maximum of that is this roof-like structure, which is the max-min strategy, which maximizes the minimum of all best responses. And you see that happens here when x hat is 1/3. Again, you can check it by the difference trick because it happens when L and W intersect. Difference here is 0.2. Here it's 0.4. 4 and 2, the first probability of going left is twice as large as for going right. And then L and W are the mixed probabilities. You can also compute them actually weighting with probability 5 out of 6 and jumping left with 1 out of 6. So that's the way to solve a mechanically, or geometrically, a zero-sum game, and we will do something relatively similar for non-zero-sum games. I do introduce a little bit of notation, which I try to emphasize. For instance, so everything that we look at is a matrix, including if it's a vector or a scalar. A vector is for me a column vector. If I transpose it, it becomes a row vector. And you have to have the matching, obviously. So in particular, a row vector times, for example, here, a row vector times a matrix of the same dimension as the row vector creates a row vector. Or a scalar product is a row times a column vector. And what I always emphasize is if you multiply a matrix with a scalar, multiply the scalar to the right, because only then it's a correct matrix multiplication. Unless it's a row vector, then you multiply it from the left. Okay, we'll see here a little example where this is useful, because then you don't have to think about these things, and you can use the associativity of matrix multiplication to figure things out. Here's an example. If you take a matrix A, and you have a probability vector x for playing rows and y for playing columns. And now you add a constant to the matrix A. What is a constant matrix? Well, it's a column vector of all ones. I didn't say that, but that's what I mean. The one means for me both the number one, but also the all one vector. Probability vector means row of all ones times x equals 1 is the equation for probabilities. So the all one matrix is a column vector of ones multiplied by the scalar alpha times the row. So this is a big matrix full of alphas. If I add this to the matrix A and take expectations, I can use linearity. I can then use associativity, and you see that then x times 1 is 1, because that's a probability. So that's simply the expected value plus alpha without any thinking. So that's an example of using the calculus in the right way, because you put the alpha at the right place. So that's advertisement for a little bit mathematics. So an easy condition is the best response condition. So in general, we look at now two-player games, which are defined by two matrices, called a bimatrix game, with m rows, always n columns. And the row player plays a row I, a column j, and then you have this cell, which the matrix entry aij of A as payoff to player 1, and bij as payoff to player 2. And we have these mixed strategies, always x and y, with these probabilities when we get these expected payoffs, where I multiply the vector x time with the vector ay, which is obtained by taking the matrix A multiplied by y, creating a column vector of expected values that is then multiplied by x. Similarly, x transpose B is the matrix B multiplied by the, for you, x from the side, squashed into a row of expected payoffs for the columns, multiplied by y. So that's how you should read it, although it's not unique when you look at a matrix product. Why do we do this? Well, here's the spelling out of this. The question is, how can you decide whether a mixed strategy is the best reply to another mixed strategy? And this is a very nice finite condition. It's familiar to you, presumably, but the idea is that when you look at this expected payoff, say for the row player, where you have this column AY of expected payoffs, when you face Y, AY is a column of expected payoffs. In each row, you have index subscript I. You take the expectation. Well, this is the best response if and only if. So let's look at an example. For example, if the vector of expected payoff is 4, 4, and 3, 1/3, 1/3, 1/3 is not the best response, because when you multiply it up, you get 3 times 2 plus 2/3. You obviously should only put weight on the best ones, on the top ones. So this is what the best response condition says. A mixed strategy is a best response against another mixed strategy if and only if only rows that have maximum payoff in this vector AY are played with positive probability. Okay? So very easy condition. It's a finite condition. You only have to check whether everything you play with positive probability has maximum and hence also equal expected payoff. That's the equilibrium condition, which in Nash's paper about mixed strategies as equilibrium points is a single line. And here is the theorem. And it's easy to prove. What do? You look at this expected payoff. You now take the maximum here, you subtract it twice, and that's the same expression. And now you multiply it here, xi times u is u itself. And here you have the difference, which is also called the slack, u minus whatever you get in row I. And you see that this slack has to be 0 for the whole thing to stay equal to y, to u, meaning if xi is positive, because we have here two non-negative vectors, xi and the slack vector. And if you multiply these two non-negative vectors, you get something zero only when they are complementary in the sense that at most one of the components can be non-zero. Yeah, because otherwise you get a positive term that you get never rid of and you pay less. That's the best response condition. We will use it all the time. You know it, but keep it in mind. So, and I can also write it because it means the scalar product is 0. That's, complementarity. Two non-negative vectors are complementary if and only if they are orthogonal, meaning the scalar product is 0. I write it with this sign orthogonal 2, meaning x greater than or equal to 0. And this inequality here, what is this? This is the vector of expected payoffs when you multiply a times y. This is the all one vector multiplied by u, so it's a vector of all u's. This is the difference has to be 0 whenever x is positive in the respective row and vice versa. You can have both equal to 0, but not both positive. So now all this is very geometric, what is happening. So we look at convex combinations because probabilities are essentially weights for convex combinations. Here's again a way of how to write convex combinations. When I look at the vector x, say in the plane, but it's actually a picture in any dimension, in any finite dimension. Vector x and the vector y. What is the line that goes through the points x and y? Well, I take x and I add a multiple of the difference y minus x to x. Okay? So if alpha is 0, I get x. If alpha is 1, I get y. If I get anything positive bigger than 1, I go to the right. If I get anything negative, anything to the left. So the line segment between x and y is simply when alpha is between 0 and 1. And when you multiply that out, this term here, this is simply saying x times 1 minus alpha plus y times alpha. And again, this is the standard way, and I insist to make these little time-saving things when you use these things. Multiply the alpha to the second element, not to the first one. Why? Because then the segment alpha between 0 and 1 maps nicely to the line segment between x and y. Okay? Alpha 0 is x, alpha 1 is y. Yeah, not if you multiply the alpha to the x, then it's already the wrong way around. Okay? I'm preachy here, but part of teaching, okay? So, now what is convexity? It means that any convex combination belongs to the set. A set is convex if and only if it contains with any 2 points its connecting line segment. The mango is convex, the banana is not convex. Okay, idealized mangoes and bananas here. And we look at the mixed strategy sets, x and y in capitals, which are exactly these things. They are called simplices, so they are the convex combinations of the unit vectors. A unit vector 1, 0 and 0, 1. Convex combination is this line segment. So the one-dimensional simplex is a line segment, which is when you play two strategies with one probability. The second, for the second strategy, pure strategy. Here it's a triangle. For 4 strategies, it's a tetrahedron, and then it becomes harder and harder to visualize when you go in higher dimensions. They're called simplices. Now, let's continue with zero-sum games. Now, here is a trick, and it actually generalizes nicely in more general settings, but I keep it in the standard setting now. Suppose we are in a zero-sum game with payoff matrix A for player 1. We multiply this matrix with y. We get a row entry I for every row of the row player. This is the expected payoff to player 1 in row I. A best response maximizes this. So it is this expression here. So this is the maximum of all the convex combinations of the numbers AY subscript I. It is also the maximum of the pure entries, as we just learned. Now, the maximum of a number of points is the same as the least upper bound on these numbers. So it's this minimum of U, such that U is greater than or equal to AY1, AY2, and so on up to AYM. So it's the minimum U such that A times Y is less than or equal to 1 times U. Very easy. What it simply means, but the nice thing, it's a single minimization problem. It's not a max min or anything. It's a minimization problem of trying to pay as little donated by you in every row. So the problem of minimizing U subject to choosing Y in Y as a mixed strategy, such that this is minimized, is what we call a min-max strategy. Okay? So this is the min-max strategy, which we call Y hat. And the analogous thing for the other player is the max-min strategy. So this is this way. I mean, the min-max strategy is what we just said. The max-min strategy X hat is the one that uses a value such that you get in each row, in each column, you maximize what the other person has to pay in each row, which you call V, by choosing a suitable convex combination of the rows of A. Okay, so that's a max-min strategy. Okay, the easy part of the minimax theorem is that max-min is less than or equal to min-max. This has to be like that because it's what player can guarantees for themselves. In expectation, it's very easy to prove. The max-min strategy, when you plug it in, is clearly less than or equal to when you substitute the particular min-max strategy Y hat, and then that's less than or equal to the maximum, so max-min is less than or equal to min-max. The converse inequality is a theorem. That's what Shapley told me. It's not the same. It's a theorem. So that's the minimax theorem of von Neumann that says that the two values are equal. Von Neumann was a polymath. As you know, I went the other day to a conference in physics where he had major contributions to the mathematics of physics by unifying Heisenberg's matrix calculus with Schrödinger's wave equation in a book called The Mathematics of Quantum Mechanics, The Mathematical Foundations of Quantum Mechanics. Before that, he was a set theorist. He had the minimax theorem in game theory. He invented the stored program computer, which is still the concept of software. I mean, the phone that you have in your pocket is still a von Neumann computer. And I love this. It's a very nice book called The Man from the Future by Madhvacharya, by Edward Teller, who said, von Neumann would carry on a conversation with my 3-year-old son, and the two of them would talk as equals. And I sometimes wondered if he used the same principle when he talked to the rest of us. So von Neumann was obviously above everybody. Okay, now what I want to show you, and which I think is a highlight, is a proof by Loomis from 1946, which was actually overlooked. And I'll tell you later on why. And it's acknowledged in a later edition of the von Neumann-Morgenstern book. It is a proof that which shows you that the minimax theorem holds. And it's one to remember. So try to listen. So we have two compact sets, which are the mixed strategy simplex Y for player, the minimizer, and the same compact set X, not the same set, unless the two dimensions are equal, for the row player. So there is clearly a min-max strategy Y that minimizes U subject to Y in Y, and such that you pay at most U in each row. Similarly, there is a max-min strategy that maximizes the amount that you're guaranteed to get, called V, when you play X times A. So that's the combination of the rows, and you get at least V in each column. Now, we can plug this in. Let's remember my favorite way of writing vectors and matrices. So V is V times 1, which is 1 times Y. Now we use the inequality that 1 times Y is less than or equal to X times A. So when we multiply this with a non-negative vector Y, so we have this inequality. And then we use that AY is less than or equal to 1 times U. And then we rewrite essentially X times Y1 is again 1, so that's less than or equal to U. So V is less than or equal to U, which is just what we had proved before. Max min is less than or equal to Y, to U. So max min is less than or equal to min max. Sorry. So now see that if we have equality in each things, in other words, if we can guarantee to pay exactly u in each row and to get at least v, exactly v in each column, then these inequalities are all equations. So if we have these equations for both the rows and columns, we already have them in Max theorem. So the only case, and that's the standard case actually, where this doesn't hold is when there is at least one of these inequalities either in rows or columns that is strict. Let's assume one of the rows is a strict inequality. So in other words, the column player plays y such that he pays at most u in each row, but in one row he pays less, and let's call this row, say, row k. Okay, so in other words, ay times k is less than u for some row k. What we do now, this whole thing is an induction proof. The theorem is trivial when we have only one row and one column. So let now assume that it holds for all, the minimax theorem holds for all smaller games. So we look at a smaller game where we delete row k, okay, a bar. And by the inductive hypothesis, this game has a value, namely u bar, which means you pay, there's a different strategy, a max strategy y bar that guarantees to pay at most u bar in each row. And similarly, that's also the thing that the row player can guarantee in each column. Now, it's very easy to see. It's a computation, but it's also obvious that u bar has to be less than or equal to u, because we have only strengthened the minimizer, because the row player has not used he has one row less. Now, what's the intuition behind the entire proof? The entire proof says, the intuition is, this is a row which you get less actually if you would play it, so you wouldn't play it. So let's drop it, nothing should change, but that's what we have to prove, okay? So we know that u bar is less than or equal to v, u bar is less than or equal to u, so the challenge is to prove that u bar is equal to u, yeah? And what I just said, the maximizer avoids this suboptimal row k of A anyhow. Now there is, however, a problem. The problem is that you have now used a strategy y bar that could be rather bad for this row k, right? Because we have omitted it from the game. So now let's just recap. We have this expression with y and u. Now we have this without row k, where we have less than or equal to u bar in a new minimization problem for the minimizer. And now the question is, what would happen if there was actually a lower value in the smaller game? And I prove that this is not the case. Not I. Loomis did this. And not only Loomis. At least two more people afterwards. One of them was Guillermo Owen, 20 years later, published, and so on. Nobody realized that had been proved before. Anyhow, so what do? We use now the new strategy y bar, which could be really bad for this row k. But we played only a little bit with epsilon. So we take a convex combination of the original min-max strategy, y, put rather heavy weight, 1 minus epsilon it, but with positive epsilon, and a little bit of the strategy y bar for the smaller game. Now, by linearity, it's the convex combination of u and u bar that you get. And because we assumed that u bar was less than u, it's actually less than u. So in other words, we have now reduced for all the rows except k, the value, that's the whole point, but only, with epsilon. And now comes the trick. Because in row k, we had a strict inequality, we know that if we make epsilon small enough, we still stay strictly below u. Okay? What does this mean? That we have now found a strategy, which is the convex combination of y and y bar, that gives you less in every row, not just row k, in every row. In other words, my y was not the min-max strategy in the first place. That's a contradiction. So actually u is equal to u bar. Now, the rest is trivial. We have u bar is less than or equal to v, which is less than or equal to u, which was the original weak inequality, which is equal to u bar. Hence, v is equal to u. The induction is complete. Now, isn't that a beautiful proof? That is really the way it should be. And I liked it so much that I tried to extend it to a proof of the strong duality theorem for linear programming. I failed. Actually, I thought I had, but I had a big bug, and then a whole paper came out of it, which I published in MOR on the relationship between linear programming duality and Minimax theorem, which there was actually a bug in that too. They are not as equivalent as people think. Anyhow, so this was something that created a lot of stuff. Now, why was this thing ignored? Because Loomis entitled his paper on a theorem of von Neumann, not a new proof of the Minimax theorem or something. A theorem of von Neumann. You shouldn't write papers with such titles. They are not unique enough, okay? In fact, he proved a more general theorem, which was actually in another paper on some economic stuff, but it's not, if you look at the matrix B with all ones in there, you get the Minimax theorem as a special case, and you can in fact use it, and it's in the book by Sorin and Renaud and Laraki. You can actually deduce the more general theorem out of it as well. So that's why it was overlooked. Okay, so that's the Loomis proof. I hope you like it. Let's also say one more thing, because it's about Nash equilibrium. When you write this in this equation, max min is equal to min max, well, you plug in the strategies x hat and y hat, because then the max min is equal to, when you put in the max min strategy, is actually to the minimum, the best response against x hat, which is equal to this, which is equal to that, simply by plugging in the max min and min max strategies. So in other words, we have these inequalities here. So the minimum of over y and y is equal to that. It's the same saying as for all y and for all x, we have this inequality and that inequality. In other words, when we play this pair of x hat and y hat against each other, no player can do better than playing that strategy. The minimizer would do worse by paying possibly more. The maximizer would pay less, get less by changing to x. So this is the concept of equilibrium, and just saying that x hat and y hat are mutual best responses. It is an exercise that you can also do it the other way around, that if you have a Nash equilibrium in this zero-sum game A and minus A, then they are actually max min and min max strategies. I warn you, actually it's an interesting story. If you don't do it right, you can get easily confused because the inequalities are not in the way you expect. So I was stuck once when I gave this lecture because I walked in and thought it's easy, and I got stuck for 5 minutes, and then I gave up because I didn't know how much time I would need to recover. And interesting enough, the people remembered that thing way better than my smooth proof in subsequent years, because they realized this is not as trivial as it looks. Sometimes it's better to have some sharp edges in your theorems indicated by what is easy and what is not easy. So now let's just know, you all know it, consequences for zero-sum games. Equilibrium and max min min max are the same. The existence is equivalence to this theorem. The strategies are optimal. They don't depend on what the opponent does. There's a unique payoff, which is called the value. And we also have interchangeability, because anything that is in equilibrium is also a max-min strategy or min-max strategy. And they're also closed under convex combination. So these are lots of properties that you don't have in general games. So that's what is the thing that you should know about zero-sum games. Now, all of this will you have known, but now let me move on to non-zero-sum games in my next set of slides, which is here somewhere. Okay. So this is now two-player games, which are not necessarily zero-sum. Okay, so what's the plan here? We talked already about the best response condition, and we look at what we saw with the football game as lower envelopes. In general, they are upper envelopes because we look at best responses of maximizers, not minimizers. We'll introduce labels, and we will find that equilibria can be represented by completely labeled strategy pairs, and then we go into Lemke-Hausen and polytopes. So, reading material here. By the way, the exposition is based largely on a very nice exposition of the Lemke-Hausen algorithm that came 10 years after the invention by Lloyd Shapley in '74. So, again, here we have now a two-player game which is not zero-sum. A Nash equilibrium is a pair of strategies XY, which are mutual best responses. For instance, bottom left, because, the best response against left is bottom and vice versa. We also can have mixed equilibria. So here's an example. When you play the columns with probabilities 1/3 and 2/3, you get in the first row 4. 6 times 2/3 is 4. 2/3 plus 2 times 2/3 plus 10/3 is 12/3 is also 4, and 3/3 is 3. So the expected payoff when you play 1/3, 2/3 is 4, 4, 3. And interestingly enough, as you know, the way to equalize these two strategies determines the probabilities of the column player, but not of the row player. The best response now of the column player, of the row player, sorry, could be any convex combination of 4 and 4 of the first two rows. But in order to make player 2 indifferent, because player 2 is mixing, we know in order to get an equilibrium, we actually look at the difference trick of the columns of the rows. So it's 2 and 1. So in other words, you have to play the first two rows with 1/3 and 2, no, what was it, 2 and 1, exactly 2/3, 1/3, in order to equalize the columns. So we have a mixed equilibrium, and we have the best response condition that only pure best responses can have probability that is positive. So again, this is a mixed equilibrium. What was it? 2/3, 1/3, 0, and 1/3, 2/3. There's a third one, which we'll find in a second. This was the best response condition. To recall, only pure best responses are allowed to be played with positive probability. Now we can write it with a little logic as follows. It means xy is a mixed equilibrium if for all pure strategies I of player 1, either, or not necessarily either, I mean at least an or, xi is 0, or we get maximum payoff. What we cannot have is a positive probability and non-maximal payoff. Similarly, y is either 0 or optimal. Okay, these conditions will be called labels. Labels that we assign. Every pure strategy will be given a label, and it means that a strategy pair XY must have every label appearing either as an unplayed strategy or as a best response. So let's do that geometrically. Here's our game. And the first trick that we introduce is due to Shapley to make the labels unique. So we number the strategies 1, 2, 3 for player 1, because here 3, 4, and 5 for player 2. Here we have the mixed strategy set. 1, 0 is the left column, 0, 1 is the right column. I now look at the mixed strategies of player 2, because they're easy. There's only 2 goalposts, if you wish. And now I plot the expected payoffs to the rows. So 1, 0 goes from 0 up to 6. It's a convex combination, so it's exactly this line. The second row is from 2 to 5. The third row is from 3 to 3. And if you look at all 3 of them, you get this picture here, where you want to look at best responses of player 1, which is called the upper envelope, which is just, inequalities that say the expected payoff has to be greater than or equal to the expected payoff for each row. And now we do something special. Namely, we not only label here these lines 2, 3, 1 with the best responses, but we also label the columns of this polyhedron with labels 4 and 5. And what do? We label them with the unplayed pure strategies. So on the left line, we see that 0, which is the right column, has probability 0. Here 4 is played with probability 0. We don't label them with the strategies, we played with them with the unplayed strategies. We actually can also afford to reduce one dimension because we project the whole thing down onto the strategy set Y of player 2, where we have labels 1, 2, 3 in these segments, which indicate where 1, 2, or 3 is the best response. Here 2 and 3 are best responses. And here at these corners, 4 is not played, 5 is not played. You might see where this is going. So let's do the same thing for player 1. It's a little bit more complicated because player 1 has 3 strategies. So we look at the mixed strategy simplex of player 1, which is a triangle. Let me just check. Yeah, I'm good in time. So now we have to think of this as a 3-dimensional picture. We have only 2 dimensions to draw, but imagine there's a triangle in the plane, and now we erect goalposts. Okay, goalposts here coming. They will now be applied to the strategies of the responder, which is player 2. So let's look at the first column, which has, against the pure strategy 1, it's 2 here, 1 here, 4 here. And now we look at all convex combinations, which is just this kind of tent that we draw, which is this triangle spanned by these things. This is exactly the plane of expected payoffs against any mixed strategy of player 1. This is what you would get when you play column 4. Let's do the same thing for the right column, which has values 1, 3, and 3. It's getting this thing. And now you have to think in 3 dimensions. We look at the two of them, and we only look at the upper envelope of them, which is this thing. Okay? So this is the upper envelope of expected payoffs of player 2 against the mixed strategies of player 1. And we label them. Namely, 4, whenever 4 is the best response, 5, whenever it's 5, a best response. And now we also label them with the unplayed best own strategies of the row player in this case, which is along the back line here. You see that's where 0, the first component is 0. That's exactly the face, actually the line opposing the point 1, 0, 0. It's exactly opposite. Along this line, strategy 1 is not played. Along the back line is player 2 is not played, and strategy 2 is not played. And in the front, which I've taken off, because otherwise you won't see anything, at the front of this thing, thing 3 is not played. Now, you have had a bit of coffee already, but the way I show it also is with a prism, a Toblerone thingy. I don't think they sell them anymore. I don't know. Anyhow, here you have your prism, which is my goalposts in 3 dimensions. We chop off the Toblerone depending on the mixed strategies. And so there is this prism, and you look at it from below, you get the upper envelope of these things. Okay? So what we also do, we can simplify it by ignoring the columns, which is just the dimension of the payoffs, and projecting it down to the triangle itself, which is now subdivided into best response regions 4 and 5. They have a common line, which is namely where 4 and 5 are best responses. And then the unplayed own strategies 1, 2, and 3. 1 is here not played, 2 is here not played along this line, and 3 not at the front. Okay. Derived from the payoff matrix for player 2. Okay. And now we look at both strategy sets. Any 2 points, X on the left in the triangle, Y on the right on the line segment, defines a strategy pair. And I claim this strategy pair is an equilibrium if and only if the labels that you find that are associated with these 2 points appear, all 5 labels appear. For example, this thing is a pure strategy. This is where you play the bottom row, number 3, which means 1 and 2 have probability 0. 4 is the best response, combined with the left column, which is where the right column is not played. That's why I've labeled 5. And 3 is the best response. And you see that I have all labels. 1, 2, 3, 4, 5. Why? Because this is exactly the best response condition that every label appears, meaning every pure strategy of either player is either played with probability 0 or is the best response. You cannot have it missing, because that would mean that you play something with positive probability, which is not the best response. It's actually an if and only if condition. Now, the nice thing is that we have not many. We need 5 labels to identify equilibria. And there are not that many points, in fact, in these graphs that have enough points. We have only 3 labels on the right, maximally 2 labels on the right. So we only have to check them to find the equilibria. And this is actually already an algorithm. Namely, here's another equilibrium, 1, 4, 5. This has the labels, and 3 and 2. So we have labels 1, 2, 3, 4, 5, like this. This is actually the probabilities where I don't play the first row. This is a new equilibrium. We didn't see it before. But we mix the strategies 2 and 3, which are then best responses. And there's another equilibrium which we saw earlier where we mix here. So we have 3 equilibria here. Okay, so we can identify the mixed equilibria of the game completely by these best response diagrams, which I like to call Lemke-Hausen diagrams. We'll see shortly why. They were essentially introduced by Shapley. And this is not yet an existence proof, however. We don't know whether an equilibrium exists, but we're one step short before the existence proof. And this is what is called the Lemke-Hausen algorithm. It was not presented as such. This is a simplified version. Shapley simplified it. I will present later on something which I think is even simpler. We'll get there. Okay, so what is the Lemke-Hausen algorithm? It can be very nicely explained with these diagrams. We introduce an artificial equilibrium by introducing an extra point. And this point is actually, because you remember this is the unit vectors in 3 space, it's actually the origin. Okay, this is not an equilibrium because it means everything is played with probability 0. But it fulfills the fact that every label appears because everything has probability 0. Having probability 0 means every label appears. So it fulfills this condition that everything appears as a label. But it's not an equilibrium because, I mean, you have to play something, as we know in games. Okay, so this is our starting point. And now we relax the condition that's the main trick. We relax the condition that we need all labels. Namely, we declare one of the labels as missing. It will be missing throughout the algorithm. It's called the missing label. It's a free choice in that algorithm, which is one of the, in this case, 5 strategies that we can choose. And whatever we choose defines a different path, as you will see, that we will now compute. So if we don't have label 2 anymore, we only need labels 1 and 3 and labels 4 and 5. So in particular, here we have a whole edge, which is defined. If you think of it, you can think of it in 3 space or in the graph. This is the edge that connects 0, 0, 0 to 0, 1, 0, because 2 has now positive probability. Along this edge, we can now move. It's the degree of freedom because we have omitted the condition that the label 2 has to be present. So we follow this. We follow a line. You can actually implement it, and I will a little bit later tell you how, as a so-called pivoting step that you might know from the simplex algorithm of linear programming. But it's actually so far just an explanation. So we follow an edge until we find a new endpoint of this edge, and this actually hits this point here. So along this edge, we have all labels except label 2 together with this point here. Yeah. So we have labels 1, 3, 4, and 5. And now we hit a new point, which now has a new label, namely 5. This label is not the label that we are missing, namely label 2. It's another label, but now we have 5 labels again, 3 on the left, 2 on the right. So because 1 is missing, 1 must be duplicate. What label is that? It's label 5, because that's the new label we have picked up. And now comes the trick. Well, we have it duplicate. Now we can drop it in the other diagram because it's duplicate. So we can go away from this point here. And now we have a new pair, which is the point, the pure strategy second row, 0, 1, 0, together with its best response, because that's the best response, 5, that we found here. So we wind up at the right column, which is the best response here. That's another way of starting the algorithm. But this is a better way, a geometric way. Now, what have we found here? Again, we have 5 labels, 1, 5, 3, 1, 4. Label 2 is still missing, but we hit a new label, namely 1. So we can go away from label 1 in this diagram. So we move over to the left here. Now we have a new pair of points, this one here, which is actually the point 2/3, 1/3, 0. Now 4 is a new picked up label. We can't go away from label 4. It doesn't have to be played with probability 0 anymore. We go here, and now we find a new label, and that is actually the missing label, and that's therefore now an equilibrium. And that's the entire algorithm. We just start, we choose a missing label, we walk along an edge, we find a new label which is now duplicate if it's not the missing one. We go away from that label in the other one, and we alternate and we move until we find an equilibrium. Now the question is, of course, why does this work? So we found the label 2. Well, we find it because there are only finitely many vertices in this. It's in fact the polyhedron that we looked at earlier. It's actually an easier way of looking at it. And if the game is generic or non-degenerate, there will be a unique starting edge giving the missing label. Actually, that's always the case, even in non-generic games. And a unique continuation, because we don't hit more than one new label. And that means we cannot come back to the starting point, because that would be another way of starting, or can we come back to this thing, because it would mean there are 2 ways of proceeding, but there's always a unique way of proceeding. So it has to wind up at another equilibrium. A good way of thinking about this is a castle, which I used to have a knight and a princess. It was considered politically incorrect, so I changed it to dog and bone. So we have a castle which has the feature that, now this is recorded on video, I shouldn't have said it. We have a castle where every room has 1 or 2 doors, and the entire castle has 1 door outside. In every room that has 1 door, there is a bone. And now the dog wants to find a bone. Well, it's easy. you just enter the castle, and either you have found a room with only one door and that it contains a bone, or it has a second door. You just go to the next door and keep going. So sorry, you just walk. It's a trivial algorithm, and you find the bone. Okay. The only question is how long it takes. That was actually one of the things that I proved sometime later. It can take exponentially time, but anyhow, this is a way of existence. In fact, there might be passageways that are just cycles that don't end at any endpoint. But if you have other rooms with bones in them, they pair up in this way, and so you get another pair of bones like here. So in total, you get an odd number of rooms with only one room. That's the oddness theorem. And we can try it now actually for our game as well. So we can not only start it at the equilibrium, but we can start it at any Nash equilibrium. For example, this pure equilibrium here that we will actually find if we drop the label that corresponds to this pure strategy, because we find it right away and its best response, it's an equilibrium. So if you start at this pure equilibrium, which is always found by the Lemke-Hausen algorithm, and we drop, so we have to keep the same missing label, which was 2. We drop label 2, we walk along here, we hit label 5, which is not missing label 2. So we go away from 5, we go here, and now we find a label 2 again, and so we have found another pair. This is actually a path in the product of the two graphs. So we have two paths, and the endpoints of these paths are the equilibria plus the artificial equilibrium, which doesn't count. The artificial equilibrium is always there, so we have an even number -1, which is an odd number, which, by the way, is non-zero. So, I mean, that's an existence proof, but it's a more general theorem. So we have an odd number of equilibria, Nash equilibria, in a non-degenerate game. Now the question is, what does non-degeneracy mean? And normally you find genericity and so on. It's always a little bit hushed what it exactly means. Here's a very nice definition for two-player games. Namely, if you have a bimatrix game AB, so you don't want to say the equilibria are non-degenerate, because you don't want to put the cart before the horse. You want to know something about the game before you start, say, your algorithm. So a game is non-degenerate if for any mixed strategy, the number of pure best responses against the mixed strategy is always at most the support of the strategy. So you never play more best responses than you mix. So for example, you shouldn't have a pure strategy that has pure best responses, or you shouldn't have a mixed strategy that plays two strategies with 3 best responses. And it turns out that this is exactly the following condition. Namely, no point in X has more than M labels if you have M strategies for player 1, and no point in Y has more than N labels. Why is that? For example, if you had a point in X with more than M labels, some of these labels are the unplayed on strategies. So let's say S of them, which is the non-support ones. So we have M minus S ones in the support, but they are bigger than this. The other labels have to come from the opponent. So are these more than support size many best responses? So it's degenerate. It's exactly the same condition. Non-degeneracy means not more than M labels, not more than N labels. And you see in our pictures that always means in particular that you cannot have a label on both sides, because you get only M labels on the left and N labels on the right. We need M plus N ones. In other words, in a non-degenerate game, every best response has to be with positive probability in equilibrium, quasi-strict if you wish. Here's an example of a degenerate game. For instance, here 4 and 4 are 2 best responses against the bottom row. It's clearly degenerate. A pure best response support size 1 is 2 best responses. You see this line here going through this one, and now you have 4 labels here. And that's not cool, because 4 labels need only 1 label on the other side to get an equilibrium. But that can also be used for computational purposes, and a little bit later, we will actually find a way of even finding equilibria in degenerate games. Namely, we can identify them with this label condition. So in this degenerate game, where I only changed 1 payoff in the bottom row to player 1, we now have this degenerate situation, so to player 2, sorry, that if you play the bottom row, you have 2 best responses, namely 4 and 5. So you have 4 labels, the unplayed on strategies 1 and 2, and the pure best responses 4 and 5. So in order to get an equilibrium, we only need label 3. So the entire region where 3 appears which is the interval between 0 and 1/3 for the rightmost strategy, together with this pure strategy here, is an equilibrium. So we have a whole set of equilibria indicated by this pair of the square and the line segment that are indicated here, plus an isolated equilibrium here. So obviously we don't have oddness, we have in fact an infinite number of equilibria. Okay, so even for degenerate games, this label story is useful. The question is, can we still have an existence proof? Can we still use Lemke-Hausen? And it turns out yes. And there is actually a way of symbolically perturbing the game such that you always have unique missing labels, duplicate labels and so on. And actually the existence proof goes through. It's a little bit more extra work. You have to go into the algebra. But in fact, it can be seen as an existence proof without Brouwer and fixed point theorems for two-player games and Nash equilibria, even in degenerate games. So the Lemke-Hausen diagrams are what I call these strategy simplices subdivided into labeled best response regions. Another thing is what I like about them when you know this technology is you can generate 3x3 games with equilibria, all sorts of conditions about equilibria that are much richer than 2x2 games. 2x2 games are kind of boring. But with 3x3 games, you need these triangles with their subdivisions, and it's a qualitative diagram. Yeah, you draw these diagrams, and then you look at what are the completely labeled points, which is much better to deal with than with any numbers. You have a lot of power by using this combinatorial/geometric construction of games, and then you only in ex post construct the matrices after it. So here's an example of two games. They happen to have these best response diagrams. Let me just show you how I did this for the other player. Well, this was the original matrix B for the second player. The best response regions are 4, 5, 6. Now, how do I get that? Well, you can add a constant to any payoffs of the column player without changing the equilibria, because it means everything is just lifted by the probability for the first row times that constant, so it doesn't change best responses. So if I added 2 here, I get one column here, which is 2, 2, 2, which is kind of in this diagram with the goalpost, with the 3 goalposts, just a plane here, a lake is labeled 2. And then I have a little one that goes up here, 3, 0, 0, and 0, 3, 0. These are these little wings that go up. And so if you're a little bit used to 3 dimensions, you get immediately this little, whatever you call it, stealth bomber that creates here the upper envelope and the best response region. So if with some practice, you can even generate games nicely, and including exam questions and so on, to let students solve them. So, and for this particular game, very similar, we could now follow the Lemke-Hausen algorithm for maybe label 1. That's from Shapley, essentially. So we drop label 1, we go here. So we start at the artificial equilibrium, we pick up label 5, we go away from label 5, we hit label 3, duplicate label 3, go away from here, we go up here, we go up here, we hit label 4, we go away from 4, we hit label 1, and that's now a pair which is an equilibrium because it's the missing label here. We have labels 2, 4, 5, and 1, 3, 6. And in a similar way, you could connect the other 2 equilibria here. Okay, so this is the pairing of equilibria. When you have missing label 1, you get other pairings when you have other missing labels. Another question is, so this is Shapley's diagram, more or less what I just showed you. There is also an example from Shapley done by Bob Wilson. One of the reasons Bob Wilson was always interested in equilibrium computation, so he has been a great mentor of mine. Here's an example where every missing label leads to the same equilibrium, namely the pure equilibrium I'm here. So in other words, the Lemke-Hausen algorithm might miss equilibrium. Yeah. So for example, I can show it to you here. If I start at the central one, which has all 3 labels, it's a completely mixed equilibrium, 1, 2, 3, 4, 5, 6. And I drop label 1, say, I go up here. I hit label 5. So I go away from label 5, I go here. Now I hit label 3. I go away from label 3, which goes down here. hits label 6, I go away from label 6, it hits this one, I go away from, no, it hits label 5, I'm sorry, I go from label 5 and I find the other equilibrium. So this was actually the longest path from the central one. If I drop label 2, we go here first, we find label 6, we go away from label 6, we find up here, we find label 3, we go away from label 3, we also find this equilibrium. And finally, when we go away from label 3, we find this one here and immediately find, by hitting label 6, from 6 to the other equilibrium. So in other words, labels 1, 2, 3 dropped, connect these two equilibrium. This is a symmetric game, a completely symmetric situation. The same will happen if you drop labels 4, 5, or 6. So in other words, these two things are paired for any missing label. They find each other, but they're not found from the artificial equilibrium. So this is an example where the Lemke-Hausen algorithm does not find all equilibria. It's exactly Bob Wilson's example in the Shapley paper. Okay, so I have 10 minutes. I'm doing it a little bit shorter because we started very late. Let me just say a few things that arise in this context. So the one question is how to implement Lemke-Hausen. We actually will not subdivide, we don't project to a triangle, for example. That's very good if you have a 3x3 game, but in higher dimensions, it's actually useful to keep the extra payoff variable, which is this polyhedral construction with the inequalities. The algebraic way of doing it is called complementary pivoting. I will say a little bit about handling degenerate games in this algebraic fashion. And obviously tomorrow, and I might not even succeed today with these 2 bullet points. If you want to find all Nash equilibria, we are in much different territory. For example, already deciding whether an equilibrium is unique. So one of the complexity questions when you look at computation, you can ask, is this an NP-complete problem? This is the wrong notion. NP-completeness is about decision problems that ask you true or false. Asking the question, does this game have an equilibrium? You can answer immediately without even looking at the game. We know it has an equilibrium, so you have to do a different complexity class. But once you ask questions about an equilibrium, like is it the only one, or does it get a certain payoff and so on, then it starts to become hard because it might be true or false. So uniqueness is co-NP complete. That means it's easy to prove that there's a second equilibrium, but it's hard to prove that it's unique. So the non-uniqueness is NP complete. That's another way of putting it. And then also what is the running time? And actually, in practice, it seems to be a very good algorithm, even though I myself constructed examples where it ran exponentially long. I think the exponential complexity is, in my opinion, a red herring. You might have heard that Nash equilibria are PPAD hard. PPAD is, by the way, the concept. So it's called, to repeat, polynomial parity argument with direction. The parity argument is exactly the fact that we have paths, the endpoint of which are even in number, because the number of paths, each path has 2 endpoints. The parity argument is that this evenness guarantees us existence, and we have this one starting point, which is at the artificial equilibrium. The polynomial part in the PPAD is that the fact that you can compute one step in polynomial time. The direction I come to sometime later, a very interesting part, it's related to this index. But so you might have heard that because Nash equilibria are PPAD complete, which is a different story, I won't talk about it, it means they're infeasible. In my opinion, this is nonsense. I mean, not nonsense, but it's not in practice true. The simplex algorithm for linear programming is also exponential for certain worst case instances, but it's very well running in practice. My impression is that these complementary pivoting algorithms, I will talk more about them in some variations, and then in the subsequent lessons, that these are actually very well working algorithms. Okay, now let's see what I can do in 6 minutes. So I also put that in my book because that is one of the things that you don't find in other books. So, okay, so let's look at again the best response polyhedron, as I call it. Well, you can write it down. X is the mixed strategy set. It's B transpose X less than or equal to 1 times V, or here, and what we did here in this case, A times Y bar less than 1. U is the vertical component. So essentially the inequalities that say U is greater than or equal to all these rows, A1 times, I mean, the first row times y, the second row, and so on, that this has to hold for all rows, is this polyhedron defined by inequalities, namely these ones, and also the inequalities that says that the y's are non-negative. And one equation that they sum up to 1. And then we get these best response polyhedron with the facet labels that we saw earlier. There's now one trick for the Lemke-Hausen algorithm, which simplifies the construction by normalizing the payoffs to 1, which you can do by dividing by these payoffs, provided you know that the payoffs are positive. That's easy to achieve. You just add a constant to all payoffs to make sure that the best response payoff is positive. Okay, so what we have got here is now a vector x, which is just non-negative. It's not necessarily summing up its components to 1. And the payoff is now normalized to 1. But you have exactly the same inequalities by this division by the payoff to the opponent v or u, because the inequalities are preserved, or the equations are also preserved. And all you need to do once you find a complementary pair, what is that? That's one where each inequality holds. So let's see how we wrote them down. The first m inequalities are, say, x non-negative and ay less than or equal to 1. They have labels 1 up to m. The second set of inequalities has labels m plus 1 up to m plus n. And the complementarity says exactly at least one of these labels has to be there. And once we have such a complementary pair, we just rescale x and y to probability vectors. The scaling factor will then be exactly the payoff. Okay. And by the way, that also has a geometric interpretation, which I try to illustrate with this picture here. So this is again my game that I looked at before, now drawn above the mixed strategy set 1001. This is the upper envelope here. And what does division by u mean? Well, you map y divided by yj divided by 1 to yj bar divided by u. Well, geometrically, that's the following. We look at this point here, say, this one here. It has payoff u here. Well, if we scale it down, that means yj divided by 1. That's the same ratio because we have this triangle here, okay? So in other words, what I'm doing is I look at this polyhedron q bar from the origin all the way up, and I project it to the plane which says payoffs are now equal to 1. And then it maps down to Q. And you see the one point that when you go all the way up, which you don't see, which is infinity, that creates, this is actually missing, it's the artificial equilibrium 0, 0. So except for this infinity point, this is what is called a projective transformation. That is exactly this correspondence between Q bar and Q, which simplifies the algorithm. So we have now this pair of polytopes, which are bounded, no infinite objects anymore. Start at 0, 0 as the starting point, and now I can run on the polytope. I will conclude now. A better way of seeing this is actually to take the product of the two, P times Q, with a certain matrix C, 0A, B transpose 0, where I look at the polytope Z in Rk. K is now equal to the sum of the two dimensions, Z non-negative, CZ less than or equal to 1, where the first rows have the labels the m plus n labels. Let's call them k labels. The rows are also labeled with the best responses, 1 up to k. And now I have a single polytope. And I illustrated now for a smaller polytope what is going on. It's exactly our algorithm. But if I project this polytope, say, to a plane, it's like this. Say here we have labels 1, 2, 3. We start here at the origin. And these are the labels. So you have to think of it as a projection of a three-dimensional object here. If I have missing label 1, I look at exactly the points that have all labels 2 and 3. So this is this green line, and it leads to this other equilibrium 1, 2, 3. And the other labels look at, this is when we have missing label 2 and missing label 3, for example. So that is a view that you walk on a single polytope. It's in fact the product of polytope, which is mathematically a simpler object than alternating between the two polytopes. Okay, I do have officially more time, but we started very late, and I think my next speaker should have a chance of also doing a little bit more. I hope you're interested in this, and I know this is a bit of a competition because now My mini course will from then on be in competition with mini course number 6. If you liked what you saw, stay with me for the next 3 sessions, and see you tomorrow. So thank you for today. Okay.
Vamos aqui. Essa é a primeira classe.
Sí. Sí. Sí, 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 sí.
E aqui há uma maneira, eu coloquei isso aqui. Onde está isso? Aqui.
Control L, ¿eh? No, control L. Control L. Típicamente. Sí. Gracias. Lo esperamos un minuto.
Parece. Shall we get back to start? We're running a little bit late. Shall we start, please? Please take your seats. So, we are happy to welcome Professor David Perez Castrillo for the final mini course of today. So, Professor David.
Thank you. So thank you for being here. So I have prepared a course which is a little bit in the intersection between industrial organization and game theory. So probably more applied than the other courses that you are going to see, and it is more applied also with more applications, and so what we will do, not necessarily today, but in the next days is examples economic situations where we can apply this type of tools. And the two words in my course are contracts and matching. Now, so these words already appear together in here, right? So why these words go well together? So these are probably two of the most successful stories in game theory, right? So usually when we do very theoretical work, most of it is not applied, or sometimes it's serves as a tool, but like nobody uses it, or you cannot tell your mom about what you are working. But if you work on matching, you can actually tell your mom what you are working on. So I use matching often to finish the courses on my advanced microeconomics, because after you see general equilibrium and stuff, you tell stories about kidney exchanges and school choices. At least you finish in high, right? So students like it. So in matching, so why matching is nice? So there are several reasons why matching is nice, and probably in this room the number of people who don't like matching is as zero measure. So matching is nice because like everything works, which is again surprising. I mean, there are not that many theories where everything works. So you take the initial, the original matching papers of, without transfers, and then, you show stability, and actually you show stability through an algorithm. Come on, this doesn't happen that often. And it's actually a nice algorithm. So again, you can tell your mom about it. And then you also have a nice lattice structure. And then you can extend it, right, to situations where there are transfers. So not only you care about who is on the other side, but also you can make transfer, you can pay him or her, or the other way around, you can receive money to be with him or her, or to work for some firm, and still everything works. You find stability. Actually, not only you find stability, it coincides with the core, it coincides with the competitive equilibria. And again, it also has this very lattice structure. The only difference now is that the lattice structure now is not on the matching, it's not on the pairs that are formed, but it is on the money, on the prices, right? So you can easily identify the matchings, which are the optimal matchings, but then there's a set of vector of transfers. And then this vector also has a lattice structure, nice lattice structure. Again, on a different object, but the same structure. And you can find mechanisms, for example, to reach, to implement these allocations, etc. Right? Now you can go further, right? I mean, I'm talking general results are extremely nice for one-to-one, but even when you go to many-to-one, still, things are reasonably well under conditions of, we have already heard about substitutability, right? Now you can actually extend to matching with contracts. And there's recent literature that tell us that all these things that we know about matching with money, you can actually do with contract, with more complex things. Everything I say so far, by the way, and all my course will be in this environment, will be under quote unquote, under complete information in this sense. So at the moment in which we take decisions and we do whatever, everybody knows everything about the situation at this point in time. So now this is matching. Again, everything is nice in matching. Of course, it's so nice that we have a few Nobel Prizes, in particular in this room, in this theory. Now, the other big success story in microeconomics, probably more related to industrial organization, is contract theory, principal agent theory, economics of information, whatever you want to call it. So what is this theory about? And I will spend some time, I think, today will be devoted to this, because my understanding is that most students in this room, and I will be addressing to the students, most students in this room don't know about economics of information. Many of them come from mathematics doctorates or mathematics schools, and others have been lucky enough to have seen it in master courses. But I will assume that nobody knows anything about contract theory. So this will be my starting point. So sorry for those of you who are experts in economics of information. There's also a few in the room. You can leave, by the way. I will be very simple about what I will do. And I will. So what's contract theory? So contract theory is about how the terms of the contract should be to try to address information problems. Information problems in which sense? You know, we talk about the relationship between firms and workers. You know, if you take a firm and a worker, but we can also talk about a teacher and a student. It's the same. So the firm is interested in the worker working. The workers typically are less interested in working than the firm would like to. So, and also the firm is interested in the output of these relationships, so the production. The worker is not so much interested in the outcome of the firm, it's interested in the salary at the end of the day. So there is what is called, I will study today, a moral hazard problem, because, you know, the firm wants the worker to work, the worker doesn't want to work. So the contracts need to address this issue. So there cannot be a salary, because I pay a fixed salary, you probably will not do much. So this is one type of information problems. And this is the type of information problem I will be extremely simply studying today. So for those of you, which again I think is there are a few don't know anything about economics of information, don't you worry, you don't need to know anything about economics of information. There are other problems of economics of information which are actually more complex from my purpose, which are it's called adverse selection. Adverse selections are problems that exist before. So in the relationship between a firm and a worker, an adverse selection problem appears when the firm doesn't know the characteristics of the worker. It doesn't know whether the worker is a good worker, is a bad worker, you know. It doesn't know his skills. If you don't know the skills of the person you are hiring, it's hard to make a good contract for this person, right? I will not be dealing with adverse selection. I might make some comment, but I will not be dealing with adverse selection. I will be dealing with moral hazard. Now, these are the two words in my course: contracts and matching. Now, these beautiful theories actually are not substitute at all. They're actually complement. And again, recent literature show that they can complement very well. What I will be interested in this course is not so much about the existence of stable allocations or you know, the lattice structure of the final outcomes, etc. I will be much more interested in how can we use matching theory as a tool, not as a theory. So I will, of course, we all know that I've been a lot of excellent research on matching. This is not what it's about. This is a tool that we can use to actually study contract theory better in a more complex, more interesting, and more realistic environment. And why matching theory? Because it's a way to endow in a general equilibrium environment situations that we have most of the time studied as isolated relationship. You know, when you teach contract theory, you typically do as I will do today. So, you know, there is one principal, that will be the contractor, that will be one agent, that will be the person in charge of doing the job, etc. And then, so let's see what is the optimal contract between these two parties, the contractor and the contractee. But usually, relationships are not isolated. They are, you know, it's not that there is a worker in the world and a firm in the world. the worker can look for other firms, and the firm can look for other workers. So we're in a general equilibrium environment. And why matching is such a nice tool for it? Because it allows to study a general equilibrium in situations where you can have as much heterogeneity as you wish. You know, there is nothing in matching theory that tells you every man is identical or every woman is, you know, they can have extremely different characteristics that we might call vertical. You know, there may be firms that are better than others in every respect. There may be workers that are better than others in every respect, but there are so many horizontal characteristics. Maybe this firm is better for me, but it's worse for you than other firm because I like it, because it's in a different city, because, you know, this is the type of job I like and you don't, whatever. And the same concerning workers. Workers are very heterogeneous in many characteristics. Again, there are some that are better than others, okay? But there are also some that are, you know, better for this position and others that are better for the other position. So, and matching theory doesn't impose anything on whether there should be homogeneity or heterogeneity. You know, you can have anything, and it still allows you to talk about general equilibrium in an extremely flexible environment. So again, we know that we can work with it because recent literature has stated that we can. But what I will do in this course is to go through a few models that provide examples in the industrial organization that tell us that we can actually use these tools to study relationship between managers and firms in a general equilibrium environment, relationship between, I don't know, hospitals and doctors in a general equilibrium environment, or whatever. And we're going to see that, and the interest, again, is not about the existence of equilibria, or it's about how the fact that we are in a general equilibrium environment influences the shape of the contracts that are signed. And the interest is also to see how the existence of asymmetric information problems may change the nature of the matching that happens. So I will be talking about assortative matching. So it's always the case that, you know, the better workers work for the better firms, etc. Can incentive problems, can moral hazard problems influence the type of assortative matching that we observe in reality, etc. Is that interesting? Well, there is actually, you know, all these things. Again, my understanding is that at least 99% of the audience in these courses are theoretical. But you can take all this to empirical data. There are, you know, there's plethora of data now, luckily, I guess. And you can take this to the data. And then when some people have started taking contrast to the data and see characteristics, etc., they sometimes realize that some of the characteristics don't correspond, don't agree with what the theory of the single principal agent theory tells you. So when you compare comparative statics, etc., you get some results, and sometimes you go to the data, and you don't have this. And one explanation, one reasonable explanation is that, again, that the contracts are not isolated entities that appears in one relationship. They are general equilibrium animals, and then when you embed contrast in general equilibrium, all these type of, for example, comparative statics exercises that you do in a single contract disappear. They're not necessarily true, right? So this is the objective of this course. Okay, this is like the publicity of this course. Okay, this is about the details of the contracts, and then we'll see through models, through examples. I will make some briefly mentions about the how can you take this to the data, etc. But I'm not an econometrician. I have some co-authors, by the way, that are econometricians, so this is nice. You can look for co-authors who are econometricians. This is always nice. And it also tells, actually, working with empirical people is nice because it gives you ideas also about different models, what happens in reality, what can you study. Okay. So today I will talk about moral hazard, only about moral hazard. And the objective is to get a couple of ideas. I will see two extremely simple models I will not scare anybody, maybe the other way around. So hopefully you will not be too bored. Okay. So the objective of this lecture today is to build a language to get to know two simple models that we will see in the next lectures later. By the way, I will also do for my students, or for those who are going to stay with me in the next 3 days, I will also introduce a little bit matching. You know, it will be a little bit superfluous because everybody introduces matching, which is nice. But I will see some properties, some characteristics of the matchings that are particularities of the matching that I will be using later in the contracts, that are not, again, general theories about matching. Okay, so I will introduce economics of information for you. Sorry. Now, what's the contract? So let's start with the basics. So I will provide. Will be extremely, hopefully, didactically simple, because I would like us to understand the intuition of everything. Because if we understand the intuition today, then it will be way easier to understand the result that will hold the next day. Okay. So what's a contract? A contract specifies verifiable obligations and transfer contingent on verifiable events. So I'm a teacher, and you are my students. At the end of the day, you know what I wanted you to study. Can I verify whether you study? Well, I cannot. There are things that I can verify. I think that I cannot. I can verify that you attend my course. I cannot verify whether you were very, attentive today or not, and I certainly cannot verify whether you study at home later when you leave me. So a verifiable variable is you attended the course. This is verifiable. Whether you are, attentive and you will study later, this is not verifiable. I can put in a contract. I will give you a certificate of attendance, but nobody will give you a certificate of proficiency unless we do some exam or something later. Okay. So verifiable is whatever can be taken to a judge, to a court. So if I hire you to work for me, and we're in a room, the two of us, and I see that you are working like crazy, and I give you a contract that say, look, you work like crazy, I pay you 1,000. You don't work like crazy, I pay you 100. And it is you and me in a room, we'll get out, I will say, you didn't work. I say, no, but I work. You saw me working. Yeah, I saw you working, but, go complain. Other way around, maybe you didn't work, and then you say, no, but I claim I work. This is not verifiable, so we cannot put it in a contract. So in a contract, we can only include whatever is verifiable. There are many things that are observable that are not verifiable. We can put in a contract whether it rained today in Sao Paulo or not. Whether it's useful or not, we'll see. Okay. So in the type of relationship we're going to study today, again, in these two simple models I will propose, is they will concern two parties. One we'll call the principal. The principal is the party who will get the outcome. So in the case of a firm-worker relationship, we will use the firm. In the case of a government who is asking a firm to produce for some public goods, the principal will be the government. In the case of a person who needs to go to the court and hires a lawyer, the principal will be the person who goes to the court. Okay? So whoever receives the output of the relationship, this party, can be a person, can be an organization, can be whatever, this is called the principal. Now the agent is the person who works to produce this output. Okay? So again, it's the worker in the firm-worker relationship, it is the government, is the firm in the government-firm relationship, or is the lawyer in the other case, okay? And again, in the contract, we can only include verifiable, okay? we can only include verifiable information. This doesn't work. So the contract may allocate tasks, may share risk, may create incentive, whatever is necessary. Again, so very important, verifiability is a big requisite, okay? And again, verifiability is like public knowledge in the sense that a judge can evaluate whether this is something happened or didn't happen. Now, the timing typically is, the principal, the firm offer a contract. Now, a contract can be a single contract, can be something more complex. Let's call it a contract right now. Then the agent either rejects the offer, and then the relationship doesn't start, or accept. If he accepts, then eventually he has to do some effort. I will refer to effort, but often it's not an effort, it's a decision. You hire a manager. Managers are typically work alcoholics, so they don't need incentives to work, but they do need incentive to get the right decision for the owners and not for themselves, or so whatever decision, okay, or to take the right decision. Again, in our framework will be effort. Then, we can be lucky or unlucky. You can work a lot and be successful or not successful. Of course, the likelihood of success will depend on the effort, but it's not necessarily one-to-one, okay? And then we have the result, and then we have the payment. Now, moral hazard, which again is the type of problem I will be considering today, appears when the action is chosen after signing the contract. So this is the timing, the offer, acceptance or rejection, effort, random result. There is no negotiation. Okay, you can think about negotiation, etc., but it doesn't change much. Why is that? When is it that the agent will accept? When he gets enough, and we call this the outside option. And this is, in principal agent theory, for many years, it has been like a black box. What this outside option comes from, I don't know. We call it U bar. I call it U bar, and this will be it. In a general equilibrium framework, this is anything about it. This will be part of the equilibrium. How much a worker receives, two possibilities. He can decide to work or stay and watch TV on the sofa, right? Or he can look for another job. This will be his outside option. Now, again, I've been mentioned moral hazard, which again is the type of problem I will be working on. Why moral hazard and others? The other type of problem, again, I mentioned before, is adverse selection. Adverse selection is the asymmetric information problem that happened already at the time of the contract. So I don't know you when we sit to sign a contract. Now, if I don't know you, how's the solution? When you go to get an insurance for your car, the insurance company doesn't know you, doesn't know whether you are a crazy driver or you are an extremely careful driver. It doesn't know whether you drive 10 hours a day or you drive 1 hour a week. It doesn't know. But of course, the optimal insurance contract depends on who you are. And the right premium depends on who you are. Right? Now, why I will not discuss adverse selection? Because it's way more complicated when we talk about general equilibrium. Because when there is adverse selection, there is no complete information. Moral hazard, at the time of the contract, when we sign contracts, there is complete information. Everybody knows everything that needs to be known. I also know you will misbehave, right? But I know everybody knows. Everybody is on the same foot. This is complete information. Later, problems may happen, etc. So contracts can be extremely complicated, but how to define stability, how to define equilibrium, this is very simple. Again, everything else can be complicated, but the notions of equilibrium are very simple. When there is not complete information, but incomplete information, yesterday I have lunch with a student that is working on incomplete information with matching. This is way more complicated. It's not clear what stability is. I mean, it's not clear. There are several proposals, etc., but it's not trivial. How to define a blocking with someone you don't know. Okay? So it's more complicated. That's the only reason. Okay. So I will not be talking to just briefly, since I mentioned contract theory. It's a little bit weird that I don't say a word. So let me say just a word about adverse selection. How do you address adverse selection? How the optimal contract in adverse selection look like? It is the same as when you go to an insurance company. You go to an insurance company for your car, and the insurance company tells you, look, you can pick. So we have this full insurance contract. It's going to cost you 1,500 euros. You don't want a full insurance contract. You only want insurance with, with some down payment. Let's say 300 euros. You have to pay 300 euros if something happens, and then it goes down from 1,500 to 600 euros dramatically. So this is called a menu of contracts. So the way to address adverse selection problems is to offer menus of contracts such that the agent can choose out of this menu whatever is best for him. And the menu is designed such that each type is going to select the contract that is addressed to him. Does this solve adverse selection? Of course not. This is the best we can do. But this is clearly second best. Okay, it's bad, but the alternative is worse. So you offer menus of contract, and then so that the people self-select. Okay, but again, I will not study because it's more complicated. And there is also not much literature on this, by the way. So there is some literature on the core under arithmetic information and matching under arithmetic information, but it's more complicated. And then signaling, let me not mention, this is when you have an adverse selection problem, for example, but the informed party, the agent can do something about it, can signal, can try to let you know whether it's good or bad or what, right? Okay. First best. Okay, so this is the model I will use. So we'll have a finite set of results of, okay, so we'll call them capital Y, capital Y, finite. In most of the cases, that will be 2. And the probability of the results conditional on the effort. So if the effort is E, the probability of result, we are going to call it Pi of E. Now, for any effort that you will do, that the agent will do, something will happen. So the sum of the probabilities is going to be 1, and all the probabilities are going to be positive. This is a technical assumption, but actually it's important because, imagine there is only 2 efforts, right? And high and low. And for any reason, I want you to do the high effort. And then there is a result that only happens if you do the bad effort, the low effort. If I see this result, I can kill you, right? So the payment is, whatever minus infinity you can think of. That means that even though the effort is not observable, there is enough proof that allows me to implement the high effort without any cost, like that was verifiable. So this is why it is important that we are talking about results that are feasible, that are possible for any possible effort. Okay. Now, the principal I already mentioned receives the result, so it's the one who cares about the Y. We are going to consider Y in monetary terms. Okay. So Y is the money value, money worth of the result, and it pays the salary to the agent, which we will call W. You see that here in the utility function of the principal that we are going to denote capital B, there is no E. If I hire you, I don't care whether you work hard or not. This is not my, what I care is whether you, at the end of the day, the result is great or not. But whether you work or not is your problem, it's not my problem, okay? So I don't care about the effort. I care about my result and how much should I pay you. Of course, the utility function is increasing and concave, weakly concave. So it's either risk neutral or risk averse. Again, in economics, we don't study risk lover agents. I will tell my students if some of you is risk lover, please let me know because I will make a lot of money out of you just playing you lotteries. Okay, so don't. Now the agent doesn't care about the outcome. The outcome is not for him. The outcome goes to the principal. Okay, so he cares about the result, which is Y. Sorry, which is W. So about how much money he receives. Cares about the so you don't see. Okay, maybe you can use. Yeah. So he cares about the salary, W, and he cares about the effort. So you work for a big firm, right? You don't care whether the firm goes good or bad. At least if you work for a year or something, a short-term thing, you care about how much money at the end of the day you receive and how much effort did you put. Again, agent it can be risk neutral or risk averse, and it doesn't like working. And then the expected utility again, which is something that the market will tell me when I will introduce the matching, is we'll call it UBAR. This is the outside opportunities. Okay? We call it in principal agent theory typically the reservation utility. Okay. Now, under symmetric information, the principal decides the effort. You know, I'm going to, that means that I can, under symmetric information, I can impose you the effort, okay? So I can tell you, look, you do this effort and you do it. There is no moral hazard or nothing. And which is this, the vector of salaries I will pay you as a function of the result eventually. And then the only thing is, so which contracts are feasible, acceptable for you guys as agents, and out of those, which one is the best for me? Okay, so this is the program the principal solves. Okay, so this is again, so remember, this is the probability that we get the result yi if the effort is E. This is the utility that the principal gets if the result is actually yi, and this is the salary he pays. And then you do the expectation. And this is the participation constraint. So this is the utility of the agent if the result is yi, and this is the probability that this actually happens. And so this expected utility should be larger or equal to the outside option. A very simple program. This is simple Pareto optimal program. Yes? You can do that. It makes your life a little bit more complicated, but yeah, you can do that. Yes. So the utility can depend. They don't need to be independent. Let's say. Okay. Yeah. Sometimes it creates a little bit of a problem depending on what you want to study, but yeah, you can do that. Yes. They can be cross effects. Okay. So this is a Pareto optimal program. No big deal. Now, which are the characteristics? I didn't put them actually in the. Which are the characteristics of the optimal contract? You imagine I tell you, okay, the effort is E star, right? How the optimal contract looks like. Okay, we need to pay the guys enough. So the level of salary should be high enough so that you get your bar. Of course, this constraint is going to be binding, right? So I don't want to pay more than enough. Enough is enough. And now the only thing that this Pareto program tells you is, the only thing that is here is risk. If both are risk averse, they should share risk. For example, if the principal is she's risk neutral and the agent is risk averse, she should take all the risk. And then what's the optimal contract? Fixed salary. Because again, the only thing that this program tells me is how to share risk. The way around, it may, you don't need to think all the time of the principal as the big guy and the agent as the small guy. It can be the government and the firm, right? If the principal is risk averse and the agent is risk neutral, then the agent should take all the risk. So this is a franchise contract. You sell the business to the agent, and he takes all the risk. This is the only thing its program tells you. Okay, nothing else. So somehow, although this is not 100% sure, in general, you can divide. There is an optimal effort in this program, and then the only thing is you have to split the surplus. And again, you split this surplus by providing enough salary to the agent, average salary to the agent, and by splitting the risk, if there is need to share risk. Okay. Okay, so what happened in moral hazard? So again, moral hazard, remember, is, I may want you to do high effort, but at the end of the day, you will do whatever is best for you because I cannot verify your effort. So I love this sentence, this paragraph that we found a few years ago. So there is a lot of debate on this subject about what kind of car handles best. Some say a front engine car, some say a rear engine car. I say a rented car. Nothing handles better than a rented car. You can go faster, turn corners sharper, put the transmission into reverse while going forward at a higher rate of speed in a rented car than in any other kind. This is not your car. Who cares, right? If it breaks, it breaks. Bad luck. You don't do that usually in your car, right? So this is moral hazard. But apart from jokes, there is a lot of moral hazard. Health economics is like the paradise of contract theory. Imagine you could be in an industry, in the car industry. Imagine the car industry, right? And in the car industry, the guy who pays the car at the end of the day is the government. So the payer of the car is the government. Who is going to get the car? You are going to get the car. Who decides what car are you going to get? The dealer. So again, this is the situation. You go for a car because you have the right for a car, right? And then you go to a dealer, but you say, hey, I want a car. And then the dealer say, hey, this car. He doesn't receive any money, or he doesn't drive the car. Government pays. Can you imagine this situation? How this is the health system. You are sick people. You go to the doctor. You have no idea. I mean, now with Google, you have less than an idea. This is even worse. You have bad ideas, but you don't know what's best for you. You go to the physician, and the physician tells you, hey, this is what we should do. This is the test we should do. At the end of the day, this is the therapy you should follow, etc. Who pays? Government or the health insurance pay. This is the car story I told you before. This is paradise for contract theory people. Every kind of information problems are there. By the way, I think one thing I didn't mention, but it's important in principal-agent relationship. Many relationships in life don't follow the paradigm I'm talking to you about. In many relationships in life, there is alignment of between the two parties. If I have to take a decision and I cannot take it because I'm not around or because I'm sick or whatever reason, and my brother has to take it, I trust, because I think it's true, that, he will take the decision in my best interest. So he would do as I would do. So I am the principal in this relationship, right? Because, I am the guy suffering the consequences, taking the outcome. The guy taking the effort or doing whatever is my brother. But if his utility function takes into account 100% my utility function, this is not a problem. This is not a principal agent problem. Many relationships in life are like that. You can trust your friend, that the friend will do whatever it is for you, etc. Then we don't have a problem. So if we think that physicians take your best interest in hand and takes into account the money of the government as a social partner would do, then we don't have a problem. We don't have to study this in the health system. Unfortunately, this is not true. I mean, there's a lot of empirical evidence that tells you that, physicians do care about your health, but they do care about many other things too. Okay. So this is again a big problem. For example, the cost in the U.S. of health system is I know the last time I read it, it was like 3 times like that in Spain. Is it better than in Spain? In TEFAUC, probably not. Why? Physicians get more money, a little bit is that, a little bit is there is insurance for physicians, etc. In Spain, if you have a problem with the physician because some error or something, you will get very little money. it's good that you get the money, but it has a lot of consequences on the cost of insurance, on the cost of the whole treatment thing. Okay? So there is a lot of moral hazard problem. Of course, how you solve it, you provide the right incentives, right? So you should give the carrot, whatever the carrot is, to the agent. Okay? So, and not, you have to differentiate what is the carrot or the incentive to the participation constraints, right? So in this program, you happens to go in this boat, probably you will suffer the incentive and you will do whatever you have to do. That doesn't mean you would accept going there. So participation constraint and incentive constraints, again, are two different animals. So what's the difference? What's the new problem? What the new problem, what the moral hazard adds to what we have? We have a very simple program, we maximize the principal expected utility subject to the participation constraint of the agent. Now we have a new constraint. Now, if the principal, thank you. If the principal wants the agent to exert high effort, he needs to be sure that high effort is actually what is best for the agent ex post once the contract is signed. So that means that if this is the contract, right? So this is WYI. Once the agent sees the contract, actually E, which is the effort the principal wants the agent to perform, is actually the best for him. And this is the new constraint. Right? So this is the new program. I will look for the best effort, taking into account that the best effort should also be the best effort for the agent. Now, for those of you who, I'm pretty sure almost all of you have solved programs like this is a tricky problem, a complicated program, because maximization, design maximization always make your life complicated. There are several ways to solve this, but so we go the easy way. So let's look at one model that will be somehow using. So imagine the principal is risk neutral. Effort can take two values, high and low. The utility of high, of course, is larger than low. So we order the results so that Y is the worst, or 1 is the worst, N is the best. And these are the probabilities of all the results given the efforts. And imagine that the principal prefers high effort to low effort. Why? Because under symmetric information, the principal is risk neutral, agent is risk covers, optimal contract is fixed salary. You pay fixed salary to your agent, the agent will do the low effort because it costs less and it's going to get the same. Okay, so if you want the low effort, nothing changes between symmetric and asymmetric information. So imagine you want to implement, the principal wants to implement the high effort. Now, this is the previous program rewritten, okay? So this is, instead of B, we have is risk neutral, so this is the expected utility of the principal. This is the same utility for the agent with two potential results, right? And this is the incentive compatibility constraint, which is written a little bit different, more compact. So this is the expected gain you switch from L to H. And this is the expected, this is the cost you switch from L to H. Okay. Remember that some of these differences are positive, and some of these differences are negative. The sum of the PIs is equal to 1. So it's not that all these differences are positive. But hopefully, this difference is positive for the high result, for the good results, right? And it's negative for the low results. Okay, so again, what happens if you pay a fixed salary? You pay the fixed salary, this condition will not hold, because if you pay the fixed salary, the guy will do the low effort. There's nothing to win, right? Because the salary is fixed, you can take this out, all this sum is 0, and the guy will do low effort. So you need to provide incentives. You want the high effort to be implemented. Now, you solve this program, and this is the condition you get. So lambda is the Lagrange multiplier for the participation constraint. Mu is the Lagrange multiplier for the incentive compatibility constraint. This is very, very simple, a nice equation, right? So this is everything depends on this ratio. Now, everybody here has studied statistics at some point, so this is likelihood ratio. What does it tell you? So this is the ratio between, this is the probability that you get the result yi if you do low effort, and the probability that you get the result yi, you do high effort, right? Now, what happens if there is a result? You know, what does it? That means that if this result has, you get a result yi that has a very high ratio, is way more likely you do the low effort. If this result is this ratio is very low, it's way more likely you do the high effort. You know, you have this problem with several results, and you don't know anything, and you observe a result whose ratio is very high, you could say this guy cheated, did the low effort. This is an ex post rationalization, but actually this is not ex post we are talking about. This is what you would think ex post, but actually we are doing the contract ex ante. So we are providing the incentives that work a little bit like ex post rationalization, right? So for any result such that the ratio is high, actually the salary is going to be low. You know, this is high, the difference is low, mu is positive, this is low, this is high. U prime high means W low. So high ratios relate to low salaries. And why? Because again, this is the way to make sure that the guy doesn't do, has less of an incentive to do low effort, okay? But that means also that the contract will be random. So the agent faces risks. You pay a risk-averse agent in expectation the same as before, but in a random manner, this is more expensive. Nobody wins because the guy will get you bar anyways, but the contract is less efficient, the principal loses. It's you lose money there. So I will finish very, very quick with two examples. So this is the first example is trivial, right? So okay, let me go to a little bit less trivial example. So imagine you want your manager to do, and I will finish here today. Imagine you have your manager, you want the manager to do an R&D project. Now, R&D projects are nice because, you know, they can give you big success. This is big money. Let's call it 100. But, you know, you do R&D, this is also more likely that you fail and it gives you 0. If you do business as usual, then you will get an average result, which is, let's call it 20. You know, in expectation, it's better to do R&D. Now you do the ratios, and what happens? Well, the lowest ratio is 1/10, which is high success. So you should pay the most in case of success. But the second is actually in case of failure. And the worst, because the highest ratio, is in case of business as usual. So you really want the manager to do R&D. You shouldn't punish because of their failure. Actually, you should reward with respect to the average. Because if you see business as usual, this is like a strong signal that the guy didn't really do R&D. You say failure, it's likely that it's because the guy did R&D. Okay. So again, it's not. Of course, ex post, the principal prefers average result than failure. But in terms of incentives, if I want the guy to do R&D, I cannot punish failure. Okay, I will finish here. I will continue tomorrow. Thank you.
Professor Gabriel Demonge. Are you here? Oh, all right. Quem? Ah, sim. É porque eu ainda vou compor.
Okay.
Good evening, everyone, and welcome to the 4th International Workshop on Game Theory and Economic Applications. It is with great pleasure that we are now opening the ceremony. I'd like to draw your attention and request everyone to pay respect to our national anthem.
Desafio
Throughout its 80 years of existence, FEA-USP has consolidated the excellence of teaching. During this period, the institution has given roughly 4,700 certificates in post-graduation programs, aside from having had an outstanding number of graduates ever since its foundation all the way back in 1946. This event has become one of the leading international conferences in the field, under the scientific leadership of Professor Emerit Marilda Sotomayor, one of the world's foremost authorities on matching theory. This workshop offers participants a unique opportunity to interact with some of the world's most distinguished researchers. Among them are 6 Nobel laureates: Robert AUMANN, Eric Maskin, Roger Myerson, Alvin Roth, Robert Wilson, and Paul Milgram. We are deeply honored by their presence and warmly thank them for joining us and sharing their knowledge, insights, and experience with the international game theory community. And now, to compose the table of the opening ceremony, we invite Professor Dr. Aloysio Augusto Cotrim Segurado, Rector of the University of São Paulo. Professor Dr. João Maurício Gama Boaventura, Dean of Faculdade de Economia, Administração, Contabilidade e Atuária. Professor Dr. Roberto Marcondes César Júnior, Dean of Instituto de Matemática, Estatística e Computação. Is he not here? All right. Professor Dr. Rafael de Vasconcelos Xavier Ferreira, Head of the Department of Economics of Faculdade de Economia, Administração, Contabilidade e Atuária. Dr. Bruno Oliva, President of the Foundation Institute for Economic Research. Professor Gabriel Demonge, immediate past President of the Game Theory Society. And Professor Dr. Marilda Sotomayor, organizer of the 4th International Workshop on Game Theory and Economic Applications. And to begin with, we'd like to invite Professor Dr. Marilda Sotomayor, organizer of the 4th International Workshop on Game Theory and Economic Applications.
Good afternoon, and welcome to all of you. It is my great pleasure to welcome all participants to the 4th International Workshop on Game Theory and Economic Applications. This meeting is part of a larger project to create a center for research in game theory using personal funds within the Department of Economics of the University of São Paulo. Going forward, it is our goal to hold this workshop every 2 years so that we can build a lasting institutional home for game theory, research, and training in Brazil. This will be my academic legate, a way to thank the Department of Economics of USP for providing me conditions for my scientific development. This is the 4th edition of the workshop we have organized at USP, University of São Paulo, following the very successful editions of 2002, 2010, and 2014. Modeled as a school of game theory, it aims to promote the field in Brazil and to attract students from around the world to this area of research. The workshop offers participants the opportunity to exchange knowledge and experience with some of the most productive researchers working in game theory today. Among 40 distinguished participants, we are honored with the participation of 6 Nobel laureates in economic science by their work on game theory. Robert AUMANN and Eric Maskin, who delivered their lectures online earlier today. Robert Wilson, who will also lecture online, and Roger Myerson, Alvin Roth, and Paul Milgrom, who join us here in person. The program includes 6 mini courses on advanced and current topics in game theory. Although they start from the basic level, they are designed to bring participants up to the most recent developments across several branches of the field. This will be complemented by 11 plenary lectures, 14 semi-plenary lectures, and 16 invited lectures, spanning a wide range of topics, along with contributed paper sessions, poster sessions, and a roundtable. We will also hold 4 social activities to encourage interaction among participants, to which you are all warmly invited. This workshop has been announced on the website of the Econometric Society and the Game Theory Society, through the website and the social media, Brazilian Econometric Society, Brazilian Mathematical Society, a National Association of Graduate Centers in Economics, and by the CNPq Research Group, Economics and Politics Research Group. It has also been covered by the press offices of the University of São Paulo and FEA, the School of Economics, Business Administration, Accounting, and Actuarial Science of USP, and by several other outreach participants. The workshop's program was significantly affected by the war in the Middle East. Abraham Neyman and Dov Samet from Israel had to cancel their in-person participation in the last moment. They will instead present online. Although nearly 700 people registered interest in the event, only 262 are participating in person. We are grateful to Professor Jérôme Renaud, editor-in-chief of the International Journal of Game Theory, who is organizing a special issue to publish the best papers presented at this workshop. I invited all of you to submit your work to the journal by December. When you do it, inform that you are submitting to the special collection, Game Theory and Economics Applications, IWGTEA 2026. We also have 121 students participating. During the event, they will have lunch together, offered by the workshop on the 4th floor of this building, so that they can have the opportunity to interact with one another and with senior participants. I would like to offer my sincere apologies to everyone present for the difficulties that arose during the local organization of this workshop. In October 2025, FAPESP, our main sponsor in the previous workshops, didn't grant the funding we had requested to cover travel and accommodation for invited participants and students. Priority was given, we were told, to applicants requesting support for the first time, which was not our case. At that point, the only solution I could see was to give up creating the Center of Game Theory and use part of the funds set aside for it instead. Fortunately, the problem seemed to resolve when the president of USP at that time, Professor Carlotte, offered to finance what we needed so that the workshop could proceed without compromising the creation of the center. A few months later, we learned that the main auditorium, this auditorium, and the other rooms originally planned for the workshop would not be available throughout July. We searched for alternative venues for the plenary lectures and mini courses, but couldn't find any that met our requirement of proximity to FEA and adequate size. We were unable to move our planning forward until late March, When we were finally reassured that the auditoriums and rooms would be released for our use. Shortly afterward, we learned that USP's financial support wouldn't cover the students' expenses, and that airfare for invited guests would need to be purchased by USP through a formal bidding process. That process could only open in May and would take at least 1 month, meaning tickets in economy class wouldn't begin to be purchased until June. Guests relying on this arrangement couldn't make their own reservations or choose their preferred airlines. Many wrote to me anxious and confused as fares rose by the day, and they hoped to upgrade to business class. Given the situation, I decided to forego USP's support for airfare and cover these costs directly. The resulting budget deficit became substantial, and we had to cut free social activities for non-student participants. Fortunately, unexpected sponsorship from Brazilian Development Banking, Brazilian Federation of Banks, and more recently from Stanford gave us new hope. And we are now able to extend the invitation to our social activities to all participants once again, and to maintain almost all the initial budget that I planned to use for the creation of the center. The complexity of managing sponsorships and payments, which under the legal requirements could only be processed by the Foundation Institute for Economic Research through formal contracts, led me to open a company, the Fourth International Workshop on Game Theory and Economic Applications, LTDA, to streamline the necessary transactions. Personal funds have also been deposited into this company to cover any remaining deficit and to advance the funds corresponding to the Brazilian Development Bank and the Brazilian Federation of Banks sponsorships, which will only become available after the workshop concludes. In these final months of preparation, we also worked out the support of one member of our local organizing committee, Professor Wilfredo Maldonado, who only returned this month, and our secretary, Alda, who was on mandatory vacation. Well, we made it. We are here, full of energy and enthusiasm, and deeply grateful because our efforts have been rewarded. You are here. This workshop has had the privilege of counting on the support of many individuals, above all endowed with goodwill and determination to help make it happen. I would like to thank the members of the program committee for their work in the selection of the papers for presentation in the regular and poster sections. I'm responsible for the scientific organization and share responsibility for the local organization with two colleagues and good friends, Maurício Bugarin, professor at the University of Brasilia, and Wilfredo Maldonado, professor in the Department of Economics at FEA-USP. My special thanks go to both of them for their invaluable assistance. I thank Regina for her generous volunteer work as secretary of the workshop. She took charge of organizing the coffee breaks and assisted with many steps of the local organization as the realization of the gala dinner, working tirelessly with me since January 2025. Her husband, Israel, also volunteered, helping install equipment for the social event that require electricity or water. I would like to thank the former president of the University of São Paulo, Professor Carlos Carlotti, for his commitment to our project, which resulted in the financial support that allowed us to cover transport and hotel expenses for our invited speakers and mini-course lectures. We also welcome the presence of the current president in office since January 2026, magnificent President Professor Aloysio Segurado. I thank the Brazilian Development Bank, the Brazilian Federation of Banks, Itaú Bank, Sempre Fair, CAPES, CNPq, and the Foundation Institute for Economic Research for believing in the importance of this workshop for the Brazilian scientific community and for their financial sponsorship, which together with USP funding made it possible to meet our workshop's budget. I also thank Dr. Arminio Fraga and Dr. Fernando Setúbal for their substantial personal financial support, and Professor Carlos Nobre and Fernando Setúbal for their help in securing funding from Brazilian Development Bank and Itaú Bank, respectively. I thank the Foundation Institute of Economic Research, FIP, represented here by its president, Professor Bruno Oliva, for its administrative support for this project. We thank the former chairman of the Department of Economics, Professor Rafael Corbe, for his valuable assistance in the Institute of Mathematics, Statistics, and Computer Sciences of USP, one of our partners, represented here by it would be, but I don't think why he didn't come, Professor Roberto Marcondes Cesar Jr. We thank Maria Dolores Montoya Diaz, former director of FEA, the School of Economics, Business Administration, Accounting, and Actuarial Science of USP, as well as Ana Angélica, Márcia, Renata, Ismael, and Fabiano for their logistical and administrative support, and we welcome the presence of FEA's new director, Professor João Maurício Gama Boaventura. Special thanks go to Professor Carlos Luque, past president of FIP, the Foundation Institute for Economic Research, for his valuable assistance during the early stages of organizing this event. Many thanks to the Secretary of the Department of Economics and of the workshop, Alda Castro, who has contributed with competence, goodwill, and enthusiasm to the work of the local organizing committee. And thank you very much, Alda. Many thanks also to the tireless volunteer work of undergraduate student Breno and graduate students Henrique and Lucas, and the Professor David, a professor at USP, the Department of Economics of USP. Breno was working with us since January 2025, and he is responsible for the workshop website. Henrique joined us this year as workshop assistant, and he's responsible for schedule changes. Lucas, who joined 3 months ago, is responsible for reading and answering the workshop's emails. Thank you as well to our team of student volunteers who are supporting the Secretariat during the event. Thanks to Professor Marcus Rossi for his collaboration with the Secretariat of the workshop. Many thanks to all of these people. This workshop is reviving an initiative first introduced in the second workshop in 2010, which was well received by both students and senior participants. Each student will have the opportunity during lunch to have a conversation with a senior participant of their choosing, selected in advance from a list they submit. You have to contact your mates, okay? I am confident that each of you will find over these 8 days of scientific program much to stimulate your research and to spark new collaborations. For many Brazilian students here, this is their first contact with advanced topics in game theory. You should not expect to understand every lecture, but you can expect to leave this workshop with a clear sense of the main topics in game theory, the mathematical background needed to pursue them, and which institutions to look to if you wish to specialize in a particular branch of the field. I wish all of you a wonderful time here. At the end of the session, we will move to the 5th floor of FEA for a soup cocktail. Welcome once again, and I wish all of you an excellent workshop.
Thank you, Doctor, for sharing your wisdom with us. And I would like to pay tribute to Professor Marilda. And for this, we invite Professor Gabriel Demonge.
The university.
And now we are turning over to Professor Gabriel Demonge, immediate past president of the Game Theory Society.
So I will be very short, I say a few words. Thank you. As a president of the Game Theory Society, actually my term is 2 years term is almost finished. It's my last week, and before I want to say how I met Marilda. Actually, it was in Paris, and I want to mention I was working with David Gale, and Marilda was working with David Gale as well. And finally, we worked together. And we wrote 2 papers. And so it was such a long time ago that the first was published exactly 40 years ago, in 86, on multi-item auctions, okay? So it's just my personal world. And after that, we diverge, or I diverge, maybe. And I met her again at this very first workshop in 2014. And I was very impressed. And I think this is a type of workshop that the society really wants to encourage it is rather unique. There are quite a few conferences, but this one is a workshop, so people work, and especially the young. And it's a combination of mini courses, talks by very prestigious people and researchers. And you have also this matching of seniors and juniors. I've never seen that elsewhere. So I think that the main objectives of Marilda have been fulfilled, because really to have all these people work together. And so this is a fourth workshop. And I hope that there will be other in Sao Paulo or in Brazil, I don't know. And this is just what I just want to say, that so the society supports this type of meetings, unfortunately not financially, but we support it. Oh.
Thank you, Professor. We now give the floor to Professor Dr. Rafael de Vasconcelos Xavier Ferreira, Head of the Department of Economics, Faculdade de Economia, Administração, Contabilidade e Atuário.
Professor Aloysio Segurado, President of the University of São Paulo, Professor João Maurício Gama Boaventura, Dean of the School of Economics, Business, Accounting and Actuarial Sciences, Professor Bruno Oliva, President of FIPE, Professor Gabriel Demange, President of the Game Theory Society, Professor Marilda Sotomayor, colleagues and guests. On behalf of the Department of Economics, it's an honor to take part in the opening of the 4th International Workshop on Game Theory and Economic Applications. This room holds a remarkable concentration of talent this evening, distinguished economists from across the world, several of them Nobel laureates. We are fortunate to have you here. I'd like to start by thanking Marilda for organizing this event. Marilda's credentials are known to everyone here. I will only add one fact worth sitting with. In October of last year, at the nomination of our department, this university conferred on Professor Sotomayor its highest distinction, the title of Professor Emerita. 9 months later, she has brought more than 300 researchers from around the world to this building. Let me say a word, though, from inside the department that hosts you this week. Our undergraduates arrived through one of the most selective admissions in the country. The students who reach these classrooms are among the most capable in this country. Many go on from here to graduate study at leading universities in the United States and Europe, and to research careers on several continents. Others continue their studies here, learning the craft in the same halls you will pass through in the days ahead. In the past few years, a wave of young research-focused economists has joined the department, well-trained and eager to build their careers here. To all of them, the student in a first economics course, the one waiting whether research is worth years of her life, the young colleague deciding what kind of scholar to become, Marilda's path is worth studying. There's undeniable brilliance, of course, but it's never the whole of it. What she paired it with is what we can learn from. The dedication, the courage to change direction, the willingness to take on the hardest problems, the commitment to the science itself. For a generation, she has convened the world's game theorists in São Paulo, and at each of these meetings, she has found the means to bring young researchers who could not otherwise have come. This week, up to 100 of them are here on support. My thanks to those who made this week possible. Professor Sotomayor, of course, as chair of the Scientific Organizing Committee, and the colleagues who organized alongside her: Wilfredo Maldonado, Rafael Corbi, David Turchik, Mauricio Bulgarin, Max Ross, together with the members of the program committee drawn from universities across the United States, Europe, and Latin America. These next words belong in Portuguese because they are for the people who built this week from the inside, and some thanks are better in the language they were earned in. Gostaria de começar agradecendo a Alda Castro, secretária do nosso departamento. Quem esteve perto sabe o quanto ela se dedicou a esse evento. Alda, muito obrigado de coração. Esse evento foi construído por muitas mãos e quero nomear as equipes que o sustentaram. A diretoria com a Eneida, assistência financeira, Márcia Bispo, José Nunes, Eduardo Felipe e Ivan. A diretoria de informática com Fabiano Ruel e sua equipe. Assistência de comunicação com Milena e Cacilda. André Ximenes na assistência acadêmica e toda a equipe de assistência administrativos e de manutenção da FEA, que realizou o trabalho invisível que tornou tudo isso possível. Agradeço também a Nilza e a Ruth e aos vários alunos que contribuíram na organização desse workshop. A cada um e cada um de vocês, muito obrigado. A workshop of this scale does not happen without real institutional support, and this one had it. I want to thank our Dean, Professor João Maurício Gama Boaventura, and his predecessor, Professora Maria Dolores Montoya Dias, FIPE and its president, Professor Bruno Oliva, for backing this workshop, and above all, the University of São Paulo and its president, Professor Luizio Segurado, whose support made this week possible. Finally, to our guests, I truly hope you enjoy your stay with us. We are genuinely glad to have you all here. Thank you.
Thank you, Doctor, for your words. We now hand it over to Professor Dr. Roberto Marcondes César Jr., Dean of Instituto de Matemática, Estatística e Computação. We'd like to call Professor Dr. João Maurício Gama Boaventura, Dean of Faculdade de Economia, Administração, Contabilidade e Atuário.
Your Magnificence, Professor Aloysio Augusto Cotrim Segurado, Rector of the University of São Paulo, Professor Rafael Vasconcelos Xavier Ferreira, Head of the Department of Economics at FEA-USP, Dr. Bruno Oliva, President of the Foundation Institute for Economic Research, FIPE, Professor Gabriele Demange, President of the Game Theory Society, Professor Marilda Sotomayor, Chair of the 4th International Workshop on Game Theory and Economic Applications, distinguished Nobel laureates, esteemed professors, researchers, students, and colleagues, ladies and gentlemen, it's a profound honor and a great personal pleasure to welcome you all to the University of São Paulo and to FEA-USP for the opening of the 4th International Workshop on Game Theory and Economic Applications. Allow me first and foremost to extend my warmest congratulations to Professor Marilda Sotomayor, Professor Wilfredo Maldonado, and the entire organizing committee. Bringing together such an extraordinary committee of scholars from around the world requires vision, perseverance, and a strong commitment to scientific excellence. On behalf of FEA-USP, I would like to express our profound gratitude to our rector, Professor Aloysio Segurado, as well his preceptor, Professor Gilberto Carlotti, and to the University Central Administration for their institutional support and for serving as the principal financial supporter of this workshop. I likewise acknowledge the invaluable contributions of all sponsoring institutions and partner organizations that have generously supported this initiative. On behalf of my predecessor, as Dean of FEA-USP, Professor Maria Dolores Diaz, I express my appreciation to the entire FAIR team, especially Alda Castro, who have devoted countless hours to making this event possible. It is an exceptional privilege to welcome 6 Nobel Prize laureates: Paul Milgren, Robert Wilson, Alvin Ruff, Roger Meyerson, Eric Maskin, and Robert AUMANN. Their pioneering work has profoundly transformed economics and numerous other disciplines. Your presence transforms this meeting into an extraordinary forum for scientific exchange. I also warmly welcome the more than 50 distinguished researchers and over 300 graduate and undergrad students who honor us with their participation. Your presence reflects the vitality of this scientific community. The program prepared for this workshop is truly remarkable. Over the coming days, tutorials, mini courses, plenary lectures, and panel discussions will promote the exchange of ideas among internationally recognized scholars while inspiring the next generation of researchers. I am confident that the conversations initiated here will lead to enduring collaboration, innovative research, and significant contributions to scientific knowledge. Game theory unquestionably stands among the most influential fields in modern economics, as evidenced by the remarkable number of Nobel Prizes awarded to scholars whose work has shaped this discipline. This work is undoubtedly provides a privileged setting for advancing these important discussions. Yet, I would like to reflect briefly on another aspect of game theory that is particularly meaningful to me: its extraordinary capacity to transcend disciplinary boundaries. Although my own academic career has been devoted to business administration, especially strategic management, game theory has been one of the intellectual pillars of my professional life. As a professor, researcher, and consultant, I have repeatedly witnessed its ability to illuminate complex strategic interactions, explain competitive behavior, and enrich decision-making. In business administration, the contribution of scholars such as Adam Brandenburger, Barry Nailbuff, Avnish Dixit, Susan Skeet, and Pankaj Gemavat have profoundly shaped strategic management and my own academic journey. I have even had the privilege of meeting some of them through the Strategic Management Society, the world's foremost academic association in my field. In classroom, game theory enables students to understand strategic interaction not merely as an abstract mathematical construct, but as a practical framework for analyzing cooperation, competition, incentives, negotiation, and leadership. In consulting, it has proven equally valuable in helping organizations navigate increasingly complex competitive environments. In short, the importance of game theory for business administration is undeniable. However, to speak only its importance to the management would be underestimate its broader contribution to many other areas. Some time ago, while serving as a doctoral examination committee at the University of Campinas, Unicamp, I was intrigued to find a dissertation in business strategy defended within an engineering school. When I asked about this unusual combination, I learned that the research was fundamentally based on game theory because of its central role in the design of sophisticated electronic control systems. That experience reminded me that truly powerful ideas rarely remain confined within disciplinary boundaries. Indeed, game theory influence certainly does not stop in engineering. Game theory has become useful analytical framework in political science, international relations, where it contributes to the study of electoral competition, peace negotiations, and international alliances. It also plays an important role in evolutionary biology, helping explain how patterns of cooperation, competition, and survival emerge and spread among species. The list continues through computer science, law, and many other disciplines. Those of us working outside economics sincerely hope this remarkable scientific community will continue expanding the frontiers of game theory, generating discoveries that benefits not only the academia, but also the society as a whole. May this workshop inspire new ideas, new collaboration, and lasting friendships. I wish you all a productive and intellectually stimulating conference. Long life to game theory. Thank you very much.
Thank you, Doctor, for your valuable contribution. And now we invite Professor Dr. Aloysio Augusto Cotrim Segurado, Rector of the University of São Paulo.
Good evening, everyone. First of all, I would like to greet my fellow panelists at this opening session. Professor João Maurício Gama Boaventura, Dean of the School of Economics, Business, Accounting, and Actuarial Science, FEA, at the University of São Paulo. Professor Marilda Sotomayor, Chair of the 4th International Workshop on Game Theory and Economic Applications. Professor Rafael Xavier Ferreira, Head of the Department of Economics at this school. Dr. Bruno Oliva, President of the Foundation Institute for Economic Research, and Professor Gabriel Demonge, immediate past President of the Game Theory Society. I would also like to extend my warm greetings to all members of our academic community and administrative staff, our students, distinguished guests from Brazil and abroad, and you all, ladies and gentlemen. It's both an honor and a great pleasure to welcome you all to the University of São Paulo for the 4th International Workshop on Game Theory and Economic Applications. On behalf of the university, I want to express my deep gratitude to Professor Sotomayor for her leadership in organizing this important event. Together with the Scientific Organizing Committee and the Scientific Program Committee, you have put together a remarkable, timely program covering the most cutting-edge topics in game theory and its applications in economics. Participating in an event of this caliber is always deeply rewarding, not only for the rich learning environment it creates, but also for the networking and cultural exchanges it fosters. What makes this workshop truly special, however, is its commitment to providing students and early career researchers direct access to the brilliant minds that have been shaping modern economics. Attendees will have the unique opportunity to interact with some of the world's most prominent scholars, including 6 Nobel Prize laureates, whom we are profoundly honored to host. Professors Robert Aumann, Eric Maskin, Roger Meyerson, Alvin Roth, Robert Wilson, and Paul Milgram, thank you so much for your generosity in joining us, whether in person or remotely, and sharing your profound insights. Beyond the academic sessions, I would like to strongly encourage all workshop participants to take some time to enjoy the beauty of our campus and immerse yourselves in the vibrant cultural life of São Paulo. Our city offers incredible museums, theaters, and concert halls. And of course, simply gathering at a local bar in the evening with new and old colleagues will be, in my opinion, one of the best ways to recharge for another day of intense theoretical discussion and hands-on collaborative work. Please enjoy the workshop, enjoy your stay in São Paulo, and once again, thank you very much for being with us at the University of São Paulo. Thank you.
Thank you, Rector, for sharing your presence and your expertise. And we'd like to thank all of you. Thank you very much. And everyone who has taken part of the 4th International Workshop on Game Theory and Economic Applications. And now we will welcome you to stay for the cocktail gathering, where there will be a delicious Brazilian recipe soup service, which will be served on the 4th floor of this same building. And once again, thank you very much.
No problem.